modulator also. There are also hybrid system using organics. That's nice work by KT. That's a lot of possibility for hybrid system also. That we need to make a link, either using optical fiber or directly on-chip communications, using a waveguide or a lot of passive devices to guide the light, to distribute light on the chip. And then at the end, we need a receiver, and then we need many of photodetectors. And this part, we can use several kinds of materials. For this talk, I will speak about a part of the modulator and a part for the photodetectors. That it's applying my talk, that the motivation is already done. And now we start with photodetectors. Which kind of material we can use to detect light at the telecom wavelength range? And we fix the wavelength range between 1.3 to 1.6 micron. That's a typical range for telecommunication. Or we can have also some application for 0.85 micron. And to make the shows of the material is this one. That its absorption coefficient as a function of the wavelength. And the main characteristic for the photodetector is to have an absorbent materials. And then if you look at, wake up. If you look at this band here, 1.3, 1.6, we have two materials which is interesting. The indium gallium arsenide is this one, and the germanium layer. And as we work on silicon-based platform, that we try to use germanium on silicon. But what is good with germanium is they have a very strong absorption coefficient at 1.3, but also at 1.5. That means that the absorption length is decreased down to few micron long, that we can absorb all the light with this in short distance, that it leads a low capacitance. And we can have a high frequency operation. That we have also high carrier mobility, that is not so bad for the photodetector to collect carriers photogenerated. What is the main drawback using germanium? That is, it's the epitaxial growth, that we have to epitaxial growth germanium silicon, that we have a very large lattice parameters mismatch between silicon and germanium for about 4%. That is quite difficult to grow 6 germanium layer with a good quality. And we have a low indirect band gap energy of about 0.66 EV. That it's for the MSM structures, we can have a very high direct current. But after several years, we start this year in 2000, we developed some techniques to grow germanium silicon, and the best one, and it's the one that everyone uses now, is to use a two-step growth process. First, you use a growth of the buffer layer at low temperature in order to absorb all dislocations due to the parameters mismatch. Thank you. Okay. You hear me now? But everyone sleep? Okay. Well, wake up. Now it's time. That's the first layer, the first growth. It's a thin layer in order to absorb all dislocation induced by the different parameters mismatch. And also after you grow a thick layer at higher temperature, 600 or even 800 degrees Celsius, to grow high quality germanium. And we make some thermal annealing in order to reduce the dislocation. That the dislocation means the trap or the dark increase, that we have to reduce the dislocation. So that here is an example, is a schematic view, but as an example here, the silicon, and we have a buffer layer here that you see a lot of dislocation at the interface, silicon and germanium, and after we have a quite good quality of germanium at the end. When we epitaxial grow germanium silicon, what is good and not expected at the beginning, we have a bandgap shrinkage. That means that we have a tensile strain induced during the epitaxial growth. And now we can absorb the light for the full band between 1.5 to 1.6 micron, between 1.3 and 1.6. That is much better for telecommunication, optical communication applications. Okay, for the integration of germanium and silicon waveguides, that we have two possibilities. The first one is the evanescent coupling, or the vertical coupling, that we have the silicon waveguide here, and we put the germanium on the top of the silicon waveguide, and then we have an evanescent coupling of the optical mode from the silicon waveguide to the germanium layers. That here is the silicon waveguide, and the germanium is here, and the light is coming through the germanium and is absorbed in the germanium layer. After about 20 micron long germanium layer, you can absorb all the light at 1.55. The second approach is the bud coupling. That is, the bud coupling is a direct coupling from the silicon waveguide to the germanium layer. And then for that, we have to etch down to the thin silicon film in order to allow the epitaxial growth. And we grow the germanium inside the silicon recess, and we have a direct coupling from the silicon waveguide to the germanium. In this case, we can absorb the light after less than 10 micron long germanium layer, and we have then a shorter length, absorption length. And what is interesting for this approach is we have a flat structures, the flat circuits at the end. There's not a topography here. That if we want to integrate 3.5 on silicon, and we have to control the BCB layer or the silica layer. In this case, it's quite difficult, even impossible. In this case, we can control the layer to bond 3.5 on silicon. And also, the coupling is independent of the thickness, independent of the wavelength, and then we can couple the light. So that we show this approach for the future work. That's what we are working on several kind of diodes to demonstrate photodetections using germanium. And then a lot of people also work on that. That is not an exhaustive list of what is already done, but now the germanium photodetector works quite well with some main players here. We have 40 gigabit operations with quite good quality, low dark current, and so on. That's a lot of work already done on that. That is probably considered as the most mature device in silicon photonics. For the diode, we use several kinds of diode, but this one is a lateral PN diode. That we have the germanium layer, and we make some ion implantations for the PN contacts, and we define the main parameters we have to define is the width here, the intrinsic region width between the P and N-doped contacts. And then if we look at the bandwidth, the cutoff frequency, as a function of this width, we can occur a very high bandwidth until 35, 50, 70. And then we use this width, 0.5, 0.7, and 1 micron with wide intrinsic regions in order to demonstrate this kind of bandwidth. So the work is performed during the PhD of Leopold Viro. It's a common PhD with ST Microelectronics and CRLT. For the responsivity, this one is a simulation, both curves here. But for the sensibility, the responsivity, we see that we can achieve 0.9 amps per watt, even for the narrower width, 0.5 micron. That is quite good, that we can achieve at the same time a very high responsivity and high bandwidth. Now the fabrication on that we use, as already said, that a two-step epitaxial growth. Using reduced pressure chemical vapor deposition techniques. That is a two-step. That we have the silicon waveguide. We etch at the end of the silicon a silicon recess, and we have a very thin silicon layer at the end here. It's about 50 nanometers. It's well controlled. And then after we grow a seed layer, the buffer layer at low temperature, that it's about 50 and 100 nanometers thick. And we grow until here the silicon surface. We have this germanium here. And we go at higher temperature, the germanium. It's a good quality germanium, but we see that there are some facets here. And then we overgrow germanium inside the recess. And we grow, you can see here the different height of germanium. That we see that here it's a buffer and the first growth and the second in order to reduce this facet here. This facet, but there also one advantage to overgrow germanium is to reduce the threading dislocation densities, and when we grow a thick layer, we reduce the dislocations. But we have a very thick layer, and then we make a post-thermal annealing, that if we make that, we reduce the number of dislocation, still to increase the quality of germanium. We make a CMP, because we want a flat device, and we make a CMP until the surface of silicon. We deposit some silica, we make some ion implantation, we anneal everything. And then we have oxidation, not oxidation, is silica deposition to put the top cladding layer, and we make metallization, is a classical stack used in CMOS foundry. And we have that we have a side view, that the silicon, germanium here, the silicon layer is just here, and we have the plugs and the electrode at the end. The top surface is this one, the input waveguide, and the germanium is a 10 micron long device, and we will characterize it now. Here's the dark current and the responsivity. Here it's for three wafers, I guess. Is for 0.5, 0.7, and 1 micron width for the intrinsec regions. So there are about 800 dies tested here. And here is the yield on the wafer. It's quite close to 100% for the working devices. That is not so bad. There are some fluctuation, obviously. But the best results, what is nice, is the dark current. So that now, if you well control the dark current, we can reduce this dark current down to 1 nanoamps. And even with some dislocation, we can have a very nice dark IV characteristics. It's not homogeneous on the wafer because the dislocation is random on the wafers, and the reason there are some variation. For the responsivity, here's the typical IV curve we obtain. For the responsivity, we have 0.5, 0.6, 0.8 amps per watt. Is below, that is one of the main questions, is below what we expect, because we expect very close to 1 amps per watt. And that we have to know what's upon exactly. For the bandwidth measurement, we use a small signal measurement. It's here the normalized response, optical response as a function of the frequency. Here it's under 0 volts. And you see that in blue at 0 volts, we have not achieved the -3 dB until 50 gigahertz. That we can operate under 0 volt. It's too sensitive. We can operate under 0 volt to achieve a very high bandwidth. That is very nice. And we expect, we try to determine the bandwidth. That it's quite difficult when after 50 or 67 gigahertz, it's difficult to determine the bandwidth, but we try to do that using LCA, a light wave complement analyzer at 67 gigahertz, but we see there are some oscillation because there are some impedance mismatch. But we also use a mode beating with the spectrum analyzer in order to see what's happened. But we estimate roughly that the bandwidth is close to 100 gigahertz. And still, again, that there are some questions that why the bandwidth is higher than the theoretical value. That is not useful to have a better results than simulations. And that is if we summarize that, is we have a lower responsivity in comparison with theory. Means that we lost photogenerated carriers, and we have higher bandwidth. That means that we have faster carrier collections. So to keep you awake, I have a question for you, for students. There are not a lot inside attendees, but you have few students. You have to answer the question: why we have a lower responsivity and higher bandwidth? What is the main reason? I have time. My flight is at 2:40. Okay. It's time to wake up. Yes? No? You put your hand? No? I know. Okay. Yeah. Okay, it's a reduction of the absorption with, in fact, if we look at carefully what's happened during the fabrications, when we make the ion implantation for both P and N contacts, we have some diffusions. And then these diffusions induce a reduction of the width we expect at the beginning. That we initiate we design a width of 0.5 micron, and in the end we have 0.3. And if we use this value, which is close to the reality, we have a maximum responsivity of 0.6 ohm per watt. That is close to 0.5 ohms per watt. And the bandwidth is 120 gigahertz. That is very close what we measure. When we make the design now, we have to take into account that during the ion implantations, not the thermal annealing, but the ion implantation, we have a reduction of the dimension. For the data transmissions, that we make a lot of data transmissions in collaboration with TU Vienna, at 10, 20, 30, and 40 gigabit under zero bias, so that without reverse bias, the PN diode, we achieve a open eye diagram at 40 gigabit. That is quite nice because we don't need to bias our detectors. We don't need some extra pads. And that's the results. To summarize that, the band responsivity 0.5 ohm per watt, 40 gigabit, 1 nanoamps under -1 volt, and bias voltage 0 volt if you want to use under zero bias. Now, still one question. Try to wake up now, always for students. How can we increase the global bandwidth of receivers? No, still sleep. Oh my God. Do you have an ID? You can say what you want. You can say no ID. Say something, please. Oh, hello. Microphone work? Is there someone? Yes. Yes, if you make it smaller, you reduce the responsivity. But if you reduce the responsivity, you have to increase the optical power of the laser. Then the power consumption of the global circuits is not so good. Try again. That's good. You are the first. You are the best. Wow. Another one. No. Okay. We should be very late. I will run out of my time, but it's their fault. Okay? We can use multi-wavelength circuits. That it's we can use AWG system. That here it's polarization independent 16 channels receivers with 16 photodetectors. We have a up. We have input a 2D grating in order to be insensitive to the polarization for T and TM. The T and TM, or TT, TM become T, and T here is split. You have two AWG, and each output for the right wavelengths come to one detectors, and then we have 16 photodetectors with this characteristic. And we have this kind of response. It's not flat, but it's not so bad. That the peak insertion loss is below 2 dB. The uniformity is below 2 dB. The crosstalk is 15 dB, more or less. The PDR, the polarizations difference between T and TM is 2 dB. The bandwidth of the photodetectors is 40 gigahertz for every detectors. Under -2 volts is below that what I demonstrated just before because we use 1 micron width. And the total data transmission is 40 gigabit multiplied by 16 is 640 gigabit operations for 2 polarizations. Okay, that is for the photodetector. Now let's speak about the modulators. It's the introduction of the second talk this morning. And the basic system is I have a continuous wave optical intensity. We inject this intensity in the black box, and we drive this black box with the electrical signal, and at the end we have the copy of the electrical signal. That is in waveguides. What's happened? We have input wave here. We propagate in the waveguide, and we have electroabsorption and also electrorefraction. Since we have a variation of the refractive index and a variation of the absorption. And we can play with either one or this, with this one or this one or both together. And 2 possibilities. Electroabsorption is the direct variation of the absorption coefficient. That is, we have a direct intensity modulation. And when we use electrorefraction, we have a phase modulation, and then we use an interferometer to achieve intensity modulation. If you look at the classical physical effect used for modulations, we use this nonlinear polarization equation that we have a linear terms, second order and third order, and so on and so on. In silicon, that's the second order. It's a Pockels effect. It's a well-known effect for modulations. It's used in lithium niobate, but we already seen yesterday with a nice presentation by AMO that as we have a centrosymmetric material, this Pockels effect doesn't exist. We have also K effect. It's a K3. It is a third order nonlinearity, but the K effect in silicon is too low to be used for modulations. But it's quite pity not to use this kind of effect because it's very fast effect. It's very simple effect, and we can try to do that, especially for Pockels effect. And when we see yesterday that to use this Pockels effect, we have to break the symmetry of the crystal in order to lead non-centrosymmetric materials. And that we can break the symmetry using some stress layer to deposit stress layer on the top of the waveguides in order to break the crystal symmetry of the waveguides. That we can achieve a strained silicon photonic. That Pedro Damas here, I saw him, he's here, but he didn't answer the question yet. Work on that he demonstrated by using a silicon nitride on the top of the silicon waveguide inserted in both arms of the Mach Zehnder. That is possible to achieve a Pockels effect that under a reverse bias or a forward bias, we have a very linear response. Here's the variation of the effective index of the guide mode as a function of the voltage, and we have a very symmetric behavior. And he demonstrated that work. The last results, it's the variation of this effective index variations. It's a variation of the effective index of the guide mode for wavelength from 1.3 to 1.6 for different waveguide widths that he can achieve a very high variation, 3⁻⁵. It's still 1 order of magnitude below what we can have in lithium niobate, but there are a lot of routes of improvement. That is quite nice. It's a promising result. To achieve a to go towards ultra-low power consumption optical modulator, because we have no capacitance in this kind of devices, and the propagation of RF signals for the long distance is easier when you have not diodes below. And there are still a lot of open questions, but one is, what is the relationship between the second order coefficient and the strain? And that is quite nice to answer to this question. But it's a work of Pedro. Okay. Now the carrier depletion modulator is the main effect used for modulation. I didn't say a lot on that because Antoine will say that. But here's a state of the art of several kind of modulators. It started in 2000, but the first gigahertz modulator in silicon is this one from Intel, but after we have now 40 gigabit, 50, 60 gigabit operation using silicon modulator. That here is not exhaustive list of the main players on silicon modulator, but it's a few. And that is a lot of kind of geometry, most capacitors, PN diode, PN diode, interleaf PN diode, and so on, so on, so on. That the main goal is to achieve a very low insertion loss, high insertion ratio, high bandwidth modulators using silicon and carrier depletion. But if you would like to address this kind of applications, we have to fulfill some challenges. The first challenge is this one, is we have to develop some photonic devices, and this technology development should follow electronics development. And we want to reduce the cost. That is good to make a lot of devices, but the cost at the end should be very low. And that's what we're working on in collaboration with ST Microelectronics, is to work on 300 millimeters platform. That is only to have a look on the difference. That at the beginning of Silicon Photonics, we use a small die, 1 centimeter by 1 centimeter, and we say, oh yes, it's good, nice devices. After a few years, we say, okay, we use this platform. We say, oh, it's stupid to use as much as silicon like this in the lab, but okay, we use that. And now we use that. That is the 200 millimeters wafer looks like the baby wafer now. And then this one is completely huge, incredible to see a wafer with a lot of devices, and that you have to characterize that at the end. That is quite difficult. That's, you take 10 years to characterize one wafer. But anyway, it's the main advantage is to use this kind of platform is this ones. Is we have a high volume we can have a high volume in production. We can use a sub 65 nanometers CMOS nodes. We use a state-of-the-art photolithography, deep UV lithography. It's an immersion photolithography, and the resolution is sub 50 nanometers. It's very close to E-beam lithography. And the wafer thickness uniformity is what is very impressive. It's for the larger wafer is better than for 200 millimeters platform. That for the resonance structure like a ring resonator, that is good to have a better yield of working devices. And using this platform, we use we demonstrate this kind of diode. It's an interleaf PN diode. It's the work of Diego. I already saw you, but you didn't answer the question yet also. Here it's interleaf PN diode. The principle is quite simple, that when we reverse bias the diode, we have the carriers sweep out the diodes in the longitudinal propagation, that the mode propagate in this direction, and we can sweep out all carriers at the end under a reverse bias. That we obtain these results: a 40 gigabit operation, a VPI is the voltage and the length, so pi phase 2.4 volts centimeter, insertion loss 4 dB, bandwidth 20 gigahertz, but we operate at 40 gigabit with the extension ratio of 8 dB. And we try to make a link. So we have a 40 gigabit modulator. We use the 40 gigabit photodetectors. and we couple with optical fiber, and we have a 40 gigabit operation. It's a point-to-point optical link. Now, come back on the application. As this application, use market applications. And if you look at the HRS, we already explained what is it. It says that, okay, you make a good job, hard work, and so on, that we obtain a very good result, but for this kind of application, it's not very useful because the power consumption is too high, and the voltage we use is not 1 volt, what we expect for CMOS drivers. And that we have to make a lot of work. And that is what we had as challenges, is to reduce the driving voltage of the modulator down to 1 volt, and to reduce the power consumption. For the power consumption, that there's a famous Meyer paper that says that, okay, that if we consider everything, and we put all together and we mix, we can have a global connection with a power consumption of about 5 femtojoule per bit. But this value now is like a reference that we have to focus on and to reach this kind of value. And that if you look at the different parameters for the power consumption of the modulator, there are 2 parameters. One is, as we use a capacitance, we have to charge this device. It's 1/4 CV square, and the dissipation, when you have the light and you have some absorption, we can have a dissipation due to the photocurrent, and that is here. Well, if you want to reduce the power consumption of our modulator, what we have to do? Question for you, I remain. Yes. Antoine, you are not a student. A student, please. I call a student. Is there? Yes. Increase the nonlinear effect. Yes, it increase the efficiency of the physical effect. Yes. Yes. If you reduce the size, what parameters you play with? If you reduce the size of all diodes, which kind of parameters you play with? Yes, we reduce the size. Okay, we imagine we reduce the size. We have better efficiency, but we reduce the size. Which kind of parameters you play on? The capacitance. That's if you reduce the size, we play on the capacitance. It's what we have to do is, when you say, well, I would like to make a very compact devices for modulation. If you want to make a compact devices, it's not mainly to reduce the size on the die, is mainly to reduce the capacitance and then to reduce the power consumption. And obviously, we have to increase the efficiency of the modulator at the end. Okay, great. Then we can start to make a push-pull configurations that we divide by 2 the length of the Mach-Zehnder. That is one. And we can also reduce the capacitance by using some slow-wave devices that reduce the velocity of the light in order to interact more and more with the active region, and then to reduce the length, the total length. Or use a ring resonator also. That is nice. It's what we did. That is, if you have a Mach-Zehnder modulator, we have roughly 3 picojoule per bit for the power consumption. If we use exactly the same diode, but we insert in the ring resonator, we have 0.5 picojoule per bit. Then we can reduce the power consumption like this. But it's not enough. We can reduce down to 1 femtojoule per bit, or few femtojoule per bit. And then we have to increase, as you said, the efficiency. That we can increase the efficiency of the silicon modulator, of the carrier depletion, or using Pockels effect, or using other effect. Using hybrid system, like a polymer, or like a new kind of materials on the top of graphene. Hybrid system, I already said, and also we can use germanium electroabsorption modulators. This is what I show you now. That is this to do electroabsorption, we can use two effects. The Franz-Kalisch effect is the electroabsorption, but in the bulk materials, or the quantum confined stack effect. It's what we achieve. It's the same effect, but in quantum wells. That is, it's what we call quantum confined stack effect. And I will only speak about that. That's what we can do. What happens when we make a quantum wells? That is, we put a narrow band gap materials between wider gap materials, and then we have a well with some transitions. And what's happened in the absorption spectra is that you have a very sharp absorption edge due to these transitions in comparison with the bulk material, which is quite smooth absorption edge. And then when we have a shift of the absorption edge, it's better to have a sharp one. That we can tune the wavelength of this sharp absorption edge according to the materials 1 and 2, and also according to the thickness of these layers. And the principle is the following, that we have a wells, and we have this spectrum. When we measure the spectrum of this kind of wells, we have this behavior, that we have a peak here, which is called excitonic peak, is due to that we have a very strong overlaps of the wave function of hole and electron, and then these very strong overlaps lead to a very strong coupling between hole and electrons, and we have a exciton. That we have a peak, absorption peak here, and very sharp absorption edge. And when we reverse, we induce a bias, we have a tilt of the band, that we have a red shift of the absorption edge, and the overlaps of the wave function is reduced, and then we reduce the excitonic peak. That we have two effects in the quantum confined stack effect. We have a reduction of the excitonic peak, and also a red shift of the absorption edge. That we try to do that we want to make a quantum well like this, using germanium layers and silicon germanium barriers. That we need a quantum wells. We need to induce a bias, that we need a PN diode, that we have a PN contacts here. We want to be strain compensate in order to reduce the loss, the dislocation inside the quantum well, and to have a very nice behavior at the end, that we have to put a relaxed buffer, and you see that the relaxed buffer, the amount of germanium inside the silicon germanium relaxed buffer is equal to the average germanium in multi-quantum wells in order to balance the strain. And we want to put this kind of structure on silicon wafer, and then to do that, due to these parameters mismatch, and we want to have a very nice quantum well in order to know what's happened in this kind of quantum well. We use a gradient buffer from silicon to silicon germanium with 90% of germanium. That is very thick layer, but we have a very high quality of quantum wells. That is what we did in collaboration with LNS in Italy. They use a low energy plasma enhanced chemical vapor deposition. It's EPECVD. It's not a common epitaxial growth, but it's very robust and very efficient epitaxial growth for this kind of structure, because it can move to very fast epitaxial growth and very slow epitaxial growth, keeping a very high quality. And then we grow very fast the gradient buffer, 40 minutes. It's a 13 micron thick. And after we grow around 1 hour the quantum wells with a very nice quality that normally we have a picture here. It's 50 quantum well here inside a PN diodes, and that we have a very nice quality, uniformity of the quantum well. We process the device. It's a quite simple processing that we etch the mesa, we etch down to the contacts, the bottom contacts, we make some silicon nitride deposition, put some metals, and we fabricate this kind of device. There are three kind of devices: a planar waveguide, is a surface illuminated diode, and the waveguide diodes. And then we characterize everything, but we only focus on one. It's a waveguide. And the first characterization is what's happened when you use a TM and TE polarizations. And if we look at the energy band structures, that for TE polarization we can have different kind of transition. This one, heavy hole and light hole, that is allowed. And for TM polarization, the heavy hole transition is forbidden. We have only the light hole transition. That is a work performed by Papi Shayar and Mohamed Said Wifed, that is not here today. That's it we characterize for T polarization. We see this kind of characteristic. We have the, look at the blue curve. It's here. We have two excitonic peaks, one from the heavy hole, this one, and one for the light hole. That we have both transitions of these kind of structures, and when we increase the bias, we see that we reduce the excitonic peak and we have a redshift of the absorption edge. And now for the TM polarization, what is interesting is that we have a light hole behavior, and we have a small redshift and a very strong excitonic peak with a strong variation of this absorption here. And if you look at the behavior we can achieve with this kind of T and TM polarizations, we can use both using quite good performances. Here's the estimated extension ratio we can achieve with both, 5 dB. The loss is about 3 dB, and the device length can be reduced when you use a light hole for TM polarization. That is quite nice. And after we make a waveguide, it's a very big waveguide. It's 3 micron wide, 1 micron thick. It's 90 micron long. Waveguide, we put here the optical fiber, and we put here another optical fiber. It's a 20 germanium, silicon germanium quantum wires structures that we characterize the absorptions as a function of the wavelength. We see that we have a redshift of the absorption edge, and if you look at different wavelengths, we can have an extension ratio higher than 6 dB for insertion loss between 5 to 15 dB according where we are. If we play at this wavelength, we have a 15 dB. If we play here, we have 5 dB. Here, the extension ratio as a function of the wavelengths, we see that we can achieve 14, 13 dB for extension ratio for a quite wide wavelength range, 20 nanometers. And what is interesting is that we can achieve a more than 10 dB extension ratio under 1 volt swing. And we can achieve very good behavior even if you use only 1 volt. Also, for the bandwidth, that we measure the bandwidth, we obtain 20 gigahertz, and that is quite noisy, okay? I agree with you, but it's at the wavelength 1.4 micron, something like that. And at this wavelength, it's difficult to have an amplifier in order to increase the signal noise ratio. But it's not so bad, it's roughly 20 gigahertz for the bandwidth. If we look at now the power consumption, that we have both. This parameters is very important because we have photo-generated carriers. And that if you calculate the capacitance, the energy per bit, it's 70 femtojoule per bit. It's quite low in comparison with what we obtain in ring resonator or Mach-Zehnder modulator using carrier depletions. Now, if you like what we can do now, that is the waveguide I just showed you. That is a mode here. And the quantum well is just here. And what we see is that the overlaps between the optical mode and the quantum well is quite low, only 12%. Means that we have a lot of routes of improvement in terms of efficiency. And only to look at, to estimate this improvement, that if we have 10%, what we have today, we have 10 dB extension ratio, 8 dB insertion loss, and the length is 120 micron. If we increase up to 30%, the overlaps here, so it's not a lot, we can achieve a very short devices with a lower insertion loss, keeping increasing the bandwidth also. That, to summarize that, is a carrier depletion modulator inside the Mach-Zehnder is 3 picojoule per bit, 0.7 picojoule per bit using ring resonator, 0.07 picojoule per bit, but we need to improve that still. And we have to reduce the size and to increase the efficiency. What we can look at when we have electroabsorption, we also have electrorefraction. It's a Kramers-Kronig relationship, and then you can look at this. Here's absorptions. It's a variation of the refractive index. That according to this variation of absorption, we can have a variation of refractive index, and we can try to play with that. It's what we did. Here it's absorption coefficient as a function of wavelength. It's when it's transparent in this region, we see some oscillation due to the Fabry-Perot cavity at the facet. And then we have a Fabry-Perot cavity. And if we focus on that, we see that when we apply the bias, we have a shift of these resonances. And then we can, this shift is due to the variation of the refractive index. And here the effective index variations as a function of the electric field, and we see we can achieve 1 power minus 3 as a variation. That is quite huge. It's 1 order of magnitude higher than what we have in carrier depletion modulator. That is quite nice, and the V pi L pi is 0.46 volts centimeter. That is quite low. That we try to improve that, and still we have only 12% overlaps with the mode. I come back on that, say, okay, we have nice structures, but it's not very nice for integrations because you use a very thick graded buffer here, and we have a very thick, everything is thick, and if we want to integrate with a classical silicon waveguide, it's quite difficult. And that, if we make a good scale, we have that. That we have some quantum wells on the top, but we have a very thick layer, and it's not very easy to integrate. And then the challenge now is to coupling the light from the silicon to the silicon-germanium quantum wells. And what we did, we tried to say, okay, we have these structures, and that work well, the quantum wells work well, and so on. That we try to keep this and say that we have to modify some kind of structures in order to use this relaxed buffer as a waveguide. And that is, say, okay, it's quite simple as an idea, but there are a lot of challenges because if we change the concentration, if you use the classical 90% germanium in this buffer, that is the previous work, this layer is completely absorbent as the working wavelengths. That we have to reduce the fraction of germanium inside this layer, but still compensate the strain of this structure in order to keep a good quality of quantum wells. And that the challenge is to reduce Y here, to reduce the loss, and to keep a good characteristic. It's what we did. We couple a modulator and detector using exactly the same epitaxial growth, and we use a waveguide fabricated in the silicon germanium layer, in the buffer layer. Once we have input waveguide, we couple in the modulator, we modulate the signal, we couple in the waveguide, silicon germanium waveguide, and we couple in the detector, and we detect the light. And we demonstrate this kind of coupling with insertion loss of only 5 dB, that is quite low, and a modulation bandwidth 6 gigahertz, and a photodetector bandwidth 4 gigahertz. It's not the high ultra high speed, but we have a lot of routes of improvement of this kind of devices. The second option is say, okay, we have a very thick buffer, that we reduce the buffer down to a very thin buffer in order to facilitate the coupling with silicon, with all silicon devices already developed. And so what we're working on is to use a classical coupling using inverted taper mod adaptators from the silicon waveguide here to the multi-quantum well stacks. And that we demonstrate, we start the fabrication. It's not finished yet, but it's here the taper, here we have here, It's the second taper to increase the coupling from the silicon waveguide to the quantum walls. And with this kind of integration, we can expect to have a 7 dB extension ratio and insertion loss of 4 dB. That this kind of integration. The first integration was on bulk silicon. This integration is on SOI wafer. Then in my conclusion, the following, that still to have an idea for the modulation to reduce the power consumption, that we have to use a carrier depletion modulator Mach-Zehnder if for some kind of application like telecommunications, optical telecommunication. We can use a ring resonator, but we have to manage temperature dependence. We can use electro-absorption germanium modulator. We can use strength silicon modulators, and we can also develop a new concept, a new kind of devices still to reduce this kind of power consumption. And I would like to thank all my colleagues of the group, the French agency for the national projects on this topic and different work. European project, not FOSTROP, but platform project is other projects start at the same time than FOSTROP on the different platform with ST, IMEC, and LETI, and the other project. Thank you very much for your attention. Yeah.
Which quantum efficiency corresponds to your sensitivity values for the P modulator?
I guess it's 60%. Yeah. We can achieve 80% because we demonstrate for the vertical PN diode 1 amps per watt. That is 80%. But in this lateral diode for 100 gigahertz is 50, 60. We can play on the geometry of the waveguides. Simple. In fact, the waveguide we use. Yep. Which one? This one. When we see that it's a very huge waveguide, that we can reduce the width, we can change the H index, we can reduce the number of quantum wires also. That if you reduce the quantum wire, we can reduce also, we expect to reduce the voltage to have a good extension ratio. And what we want to do is to push the mode up. Okay, that one is to play on the geometry, another one is to play on the layers, so we can make another layer with high reflective index to push your mode up. That's a lot of kind of possibilities to do that. But you see that the only increase 12 to 30%, we have a very huge improvement. On power consumption, the limitation of the power consumption, you mean? Optical input power. For the modulators, no, you can have a picowatt, but if you have the receiver measure at the end, it's okay. But the main part of the input optical power, the minimum is given by the receiver part. Is your question? The maximum. Yes. We expect to reduce the power, not to increase, but as a maximum, it's limited by the two-photon absorption effect. In silicon, it's about 15 dBm, I guess, something roughly this value. For germanium, it should be lower, at 10 dBm, I guess. I never try. That's a good question to see the two-photon absorption in this kind of germanium quantum wave structures. But it should be 10 dBm. We put in general for the characterization in order to have a good signal noise ratio of about 5 milliwatts. Well, 10 milliwatts you should see some two-photon absorption.
So now we move on to continue actually the lecture on Silicon Photonics with Antoine Brimont from the University Polytechnic of Valencia, who is going to talk to us about silicon photonic modulators and switches.
Thank you. Good morning, everyone. Thank you. I'd like to thank Nikos and all the organizers of this summer school. I'm really happy to be here and have the opportunity to talk in front of you about my main field of work, which is actually silicon photonic modulators and switches. So most of the talk you have had so far are based, actually focused on the engineering part. So my talk is more focused on the device part, but I think it might be interesting for you to hear think about modulators. So first of all, the outline. I'd like to talk about basically, well, the engineering part is unavoidable, of course. We need to know exactly where we need silicon in optical communications. And so I'll make a quick overview of this. Then I will talk about the basic principle of operation of silicon modulators. Show you some actually work on how to enhance the silicon modulator efficiency. And then I will extend this talk, this part, and showing you some, let's say, engineering work to enhance also the slow wave operation of silicon corrugated waveguides. And because my talk also is on switches, I'll talk about a little bit about the switches, and I'll draw some conclusion and perspectives. So first of all, this is the optical interconnect roadmap. You already know these pictures probably. So first we have this long haul and metro LAN optical communications, and we already have for this for telecommunications field mature technologies. So to make a basic link, this is very simple, simplified. Of course, you need sources, lasers, VCSELs, DFB lasers, LEDs as well. You need a modulator, optical fibers for the link, and EDFA to amplify the signal. And at the end of the link, of course, you have the photodetector. So basically here the modulator is, what it does is just modulate the generated carrier wave. And well, the EDFA regenerates the wave because of the attenuation. So you have some examples. I don't know exactly what's inside this what is inside this box, but these are long-haul transponders, and some interesting examples of what they are. Basically, this one is based on a lithium Laubet modulator, and this one on indium phosphide. As we reduce the distance of communications, we go down to, let's say, 100 meter down to 1 meter. So we do have a very important field, which is the rack-to-rack communications, as you saw on all the talk you said, and especially the best talk, and also the board-to-board communication. So this already you already know these slides, and of course, in high-performance computing systems, what you have basically is you have two ways of connecting the racks, and basically this is the electrical way, let's say. So you see that it's really heavy because we're using basically very heavy cables to do this. And there's a limited bandwidth of copper interconnects, which is limited to about 10 gigabits per second. And this means that we have a distance and speed trade-off in this. So we are limited in terms of these factors. We also have a complex cable management, which means that, of course, because of the size of the copper cable, which needs to be very thick in order to transport high-frequency signals. And as you compare that to the optical link, which is made of optical fibers with two transceivers and receptors, two transceivers at both ends, you see that the result is really, let's say, looks really light, and so you have much less weight and interconnections. I mean, you have the same number of interconnections, but of course it looks much more, let's say, it's easier to manage all the cable connections, and it actually occupies much less space. So the advantage of this is that you can actually run multiple signals over a single fiber. So we have tens of terahertz bandwidth, and you can reach very high distances and high speed. And also the cable management is really easy. So basically, some example of, well, let's say transceivers. You have two competing technologies. One is more mature, or let's say older, but it's still the dominant one, and it's based on VCSEL technology. And this VCSEL technology basically can reach, well, there are much more optical cables than this, but this one is based on a transceiver, which can transmit up to 100 gigabits per second. This is basically, I mean, inside this cable you have 4 channels transmitting by the use of VCSELs, and these VCSELs are directly modulated at 25 gigabits per second. So in total it's 100 gigabits per second. Also a more recent technology which is based on Silicon Photonics, and the principle is a bit different, because what you need for these transceivers is basically 4 modulators, which 4 lasers, sorry, which are basically externally modulated by the means of silicon modulators. So that's actually the focus of my talk. And so if we need more channels and more gigabits per second, then for Silicon Photonics, it is expected that it's not going to be a significant issue, because we need the same components. The cost is also is not going to scale too much, because we have mass volume production available, and we also, due to the fact that it's single mode, we can achieve longer reach. So for the VCSEL part, of course, if you increase the speed of the modulation, the directly modulated VCSELs, it gets much more, let's say, challenging, because you have higher currents, the temperature dependence also of which affects the performance of the VCSEL, and also the assembly and all the. So let's see examples of HPC's systems, and here you see that you have this was 6 years ago, so you saw that probably on the slides of Bert, and you see that the optics here gets to the board, outside the board, and you achieved with that 1 petaflops. But then when you actually put the optics inside the board, what you achieve is 10 petaflops per second. That means that this is an additional assembly effort, but it means that the optics is really helping in achieving much higher computation power. Also, for much shorter distances, you have this research milestone from Intel in 2011. This is a small transmitter and receiver. I would say that it's more comparable to what we have already, USB and HDMI, which are transmitting at these speeds. And basically, it's Silicon Photonics based. So that means that they achieve the 50 gigabits per second transmission through the link. And the goal is to achieve 1 terabits per second just by increasing the number of channels and increasing the number of modulators up to 40 gigabits per second. So that's really a nice work, but it's still at the research level. Now, as we reduce the distance, the interconnection distance, we get to the point where we need to interconnect cores. So you have had a very nice talk on this before, and also on-chip interconnects, which are where silicon maybe is really a good candidate, very nice, very interesting candidate to achieve this. So for the board-to-board, intra-board communication, there's also a nice research milestone which were presented in 2011, and which is basically a transmitter bidirectional link, which is based on VCSELs, and where the data is transmitted through a polymer waveguide. Regarding the integration of silicon photonics, so we all know that actually the microprocessor industry is moving from single core to multi-core architectures. I mean, it's already done, basically. And what happens is that the clock speed is not increasing. It's much more the parallelism which is dominating the processors manufacturers. So as the transistor gets smaller, much smaller, so you have a much smaller gate length, the size of the transistor is decreasing, sorry, and well, let's say the computation power is increasing as well. The problem is that this is not really a transistor which is limiting the speed of the processor much, but rather let's say the copper interconnect, which is actually a bottleneck for this, and it means that you have much more interconnected transistors, and that leads to higher power consumption, higher RC delay, so you have more latency, higher losses, and you need basically this off-chip data to be really extracted from these cores. So for that, we need energy efficient and high bandwidth solution, which may be made by Silicon Photonics. So this picture is well known, of course, so from Bert Hofrein and also from IBM. So basically what you have here is just the processor layer, the memory layer, this is a stack, and on top of this, the photonic network layer, which actually connects cores between them and routes the traffic. So that's a vision. It's not already, a lot of groups are working on this, because it's a really challenging goal, basically. So to summarize this, where silicon can address all these issues. So on the long haul range, there's already a mature technology, which is basically covered by the VCSEL, by the lithium niobate modulators. So maybe it's not mandatory, but maybe it can find some applications. On the, let's say, shorter length interconnect length, silicon can address well, some min-term imperformance scaling, as you saw before. And on the shorter range, very, let's say, intra-chip interconnects and core-to-core interconnects, it's really, I would say, silicon is really mandatory. It's something that you can't avoid if you want to scale, if you want, let's say, optical interconnection to be feasible. So what are the challenges and to that? So basically, Silicon Photonics-based photonics require lots of components, laser, driver, modulators, and many passive components. Also amplifiers and detector and TIA for the photodiode. So really the fabrication assembly depends on the number of components. You know also that the reliability and repeatability is really challenging for Silicon Photonics, but it's being studied, especially in the platform project from Laurent. And so we'll have out of this project probably nice, very interesting information on the reliability of, let's say, the Silicon Photonics components. But of course, the large volume and chip level integration will allow a lot of components to be integrating on the same wafer. So that means a very low cost for each, let's say, transceiver or component based on Silicon Photonics. So as a result of more than a decade of intense research in Silicon Photonics, we have most of the critical components that have been designed. and actually fabricated. So we have very nice results in the field of silicon photonics. And additionally, well, let's say that it will help in simplifying the assembly or whatever. Let's say avoid the fact that maybe we have to assemble many fibers and many by hand, many components by hand. So for a silicon-based optical link, what you need basically is a laser, modulator, waveguide, amplifier, and receptors. So you already see that well, there are many nice demonstrations of lasers, germanium-based lasers, let's say indium phosphide lasers, in gas also bound into silicon, which is with all the references here. Regarding the modulators, we have also many demonstrations, the pure silicon modulators, germanium and silicon modulators, also 3-5 and silicon modulators. All the passives are really basically the building blocks are already available in libraries. The amplifier is maybe a harder part. I'm not very experienced in amplifiers, but I know that if you include the erbium into your silicon waveguide, you can amplify the signal. And also the receptors, which are as Laurent said, based on germanium as well. Well, you have many different technologies, but the most mature is actually germanium and silicon. So, silicon modulators, I'll show you a little bit of an overview and trends. So let's get back to the basics. To modulate a signal, what you need is it's a modulator, of course, and what this modulator does is actually changing or altering the properties of, let's say, a beam of light propagating through free space or guided through a waveguide. And so it modulates the phase, the amplitude, the polarization. So it's all called, all these are called modulators. What you do, for instance, in an optical waveguide is modulating the refractive index via electroabsorption. This is the real part of the refractive index, electrorefraction, sorry. And if you want an electroabsorption modulator, what you need to do is modulate the imaginary part of the refractive index. So here's a basic example of Mach-Zehnder interferometer. This is an amplitude modulator. So what you have is an incoming wave coming into injecting into the waveguide. You have a splitter here, a 3 dB splitter, and then if you don't apply the voltage, what happens is that at the output of the modulator, what you will have is just constructive interference, which is the on state, which in the digital world is 1 basically. So you have a constructive interference and on state. In the case of when you apply a voltage on one arm of this modulator, what happens is that you shift the phase by pi phase shift, and at the output of the modulator you will have a phase difference of pi, which means that you will achieve a destructive interference state, which is 0, an off state. So that's really basic, but that's what you have to know. And basically, there are many parameters which are defining the modulator performance. First, the extinction ratio, which is the difference between the output power in the on state and the output power in the off state. So that's a very critical parameters to get nice bit error rate figures. Also, you have the insertion loss. This is the difference between the output power in the on state and the input power in the on state and the input power in the on state. So you have here the insertion loss defined as this difference. The phase shift, which is actually dependent on the change in the effective index, model effective index that you achieve in this region, the active region it is called, and at the end the drive voltage. Additionally, you have also the data rate, which allows you to know what speed can reach your modulator, and the modulation efficiency, which is a global figure of merit of your device, and which helps actually to make a comparison between all the modulators in the literature. So in silicon, you have many different, well, let's say many, not many, but there let's say, different effects that can be used for modulation. So the Pockels and Kerr effect, which, I mean, the Pockels effect was actually described by Laurent, which is a very nice work. And if it's really, let's say, if you can achieve modulation efficiency comparable to what's currently achieved in, let's say, carrier depletion, carrier injection, or maybe more carrier depletion, that would be a very, very good candidate for on-chip integration because of the, let's say, the simplicity, the ease of making these kind of devices. So you would avoid all the implantation steps, and that's very interesting. Also, you have the quantum confined start effect, which is similar to Kranz-Kalisch effect, which is also which was given in actually in Laurent's talk, but I'm not going to extend on this part. You have the thermo-optic effect and the plasma dispersion effect. They're all different effects. They have, let's say, different drawbacks and advantages. One is, for instance, the thermo-optic effect is really efficient, but it's really slow. The plasma dispersion effect is, I mean, complicated to implement, but that's the best effect so far for modulation in silicon, and it's also CMOS compatible fully. So I'll leave you just take a look at the table. You have my presentation and the USB key, and you'll see all the. So what is the plasma dispersion effect? You have basically two different approaches. The first one was Drude model. It's an old model, classical model, let's say, and the empirical approach, which is the Sorev model. And here you have the change in refractive index, real refractive index, and the change in absorption, which is the imaginary part of the refractive index. So these two values are dependent on the change in density of holes and electrons here. So same thing here and same thing here. So you have two separate contributions, which are basically the contributions of the electrons and the holes. So if we plot actually the curves based on these two models, we see that there's a kind of difference. So there's a kind of, let's say that Drude says that electrons are slightly more efficient in changing the refractive index than holes, and Sorev says basically the contrary, and up to a certain concentration of free carriers, up to 10 to 19 centimeters per centimeter square. So also regarding holes, and you see there's also one of the magnitude difference between the two models. And actually, Drude says, electrons absorb less light than holes, and Sorev says, holes absorb less light than electrons. So overall, we can say that holes produce a stronger refractive index change and less absorption. But I recommend you to follow Sorev model, which is empirical, and it's let's say it's the model that everyone follows now in Silicon Photonics. So let me show you some, let's say, the three major mechanism of plasma dispersion effect in silicon. It's pure silicon, so I'm going to focus here only on silicon, pure silicon. So you have the most capacitor devices. So here in the middle of the p-n junction, that's in the p-n junction in the waveguide, you have an oxide layer, thin oxide layer, and as you actually apply a voltage here, you inject carriers through the waveguide, and they accumulate at the boundary here. So that gives you a change in a carrier's density, which allows you to achieve a change in refractive index inside the waveguide. So then, as you release the voltage, carriers go back to the initial position. Also, if you just remove this oxide barrier, what happens is that you inject the carriers through the waveguide, and you have a current flow inside the circuit, which means that this is a minority carriers mechanism. So you're injecting holes in the N+ region, and you're injecting electrons in the P+ region. That's why it's called a minority carrier, let's say, mechanism. And to end up with, you have the depletion reverse bias mechanism, which is based on a p-n junction. So you apply a reverse bias to these electrodes. So you apply the plus on the n plus region, and you apply the minus potential on the p plus. So that means that basically your electrons are attracted towards the plus, and the holes are attracted towards the minus. So that your carriers tend to be swept out of the p-n junction. So you achieve also locally a change in the depletion area. So I'll focus on the carrier depletion mechanism. So you have an example here. But basically, this is your waveguide. Your basic. Let's say the optical mode is propagating through this waveguide here, and here is the change in density of holes and electrons. So I go back because I don't know. So you can see that as you apply the voltage, the depletion region tends to open up, which means that you achieve a change in density, in carrier density. So here are the early, let's say, waveguide-based, waveguide-based carrier depletion modulators at 40 gigabits per second. So I haven't been through the whole state of the art because there are many realizations. But these were the first realization, a very impressive result at the time. So the first one was made by Intel, and you have this nice eye diagram at 40 gigabits per second. It was back in 2007, so a long time ago. And you had this nice eye diagram with a very low extinction ratio, but still they demonstrated 40 gigabits per second. So the extinction ratio here was 1 dB, so it was very low, but still the eye diagram is really well open, and so that's because the bandwidth of this modulator was basically extremely high. It was 30 gigahertz at the time. Then you had the paper from Dave Thompson from the University of Surrey, now Southampton, which was within the project IDIOS project, and also in parallel, nice work from Monica Siebel, which was in Laurent Vivien's group. And both modulators were published approximately at the same time, the same year, and achieved 40 gigabits per second, which was a nice result at the time also. And thirdly, the Frederick Gauss modulator, also from the University of Surrey, now Southampton. I think they moved to Southampton. And these were the basic, the first devices. And since then, there have been many similar devices with, let's say, optimization and doping, electrodes, everything. So you have a lot of them, basically. So it's quite difficult to go through the literature and know exactly what is the advantage of each of these modulators. But I'll let you go through the whole table if you want, because it's a nice table that I found recently in this paper. But still, we know we can modulate at 40 gigabits per second up to 60 gigabits per second. I think I saw a paper on this. But still, there's still some challenges that we have to address before saying that, okay, we can integrate our modulator in interconnects, because we need to reduce the power consumption, we need to reduce the losses, we need to do a lot of things. So there are issues. I mean, it's always when you read the paper, you go through the paper, you can see that it's either the modulator has a large footprint, or either it requires a hard drive voltage. So the challenge is increasing the modulation efficiency, as Laurent said before, and this can be done either by increasing the doping concentration, but it means also higher loss, and it's also limited by the fact that as you increase the doping concentration, then your depletion region gets really narrow, so it doesn't really well overlap with the mode, the optical mode. And also you can increase, in a, let's say, a clever way, the interaction between free carriers and optical mode. And this can be done through the slow light effect, which I was working on during my PhD thesis. So I'm going to introduce a little bit, let's say, about things about the main aspects of slow light. So what we need to produce slow light, that's basically we need the periodic, let's say, waveguides, which allows the light to actually propagate and reflect back and forth multiple times and then form an interference patterns that has, let's say, a higher group index or, let's say, lower group velocity than conventional RIP waveguide. So it's like slowing down the light, but as it was, you were slowing down the light, because you cannot really slow down the light, of course. So just decreasing the group velocity of the light. So let's say the group velocity is related to the pulse propagation. So you have a superposition of this light, let's say back and forth reflection, and you form a slow wave pattern, which is called the block, which are actually called the block modes. So you have many applications for slow light devices. You can make compact optical delay lines, filters, highly sensitive Bayer sensors, enhanced active components, switches, modulators, and all devices that require an enhanced light matter interaction. So here we're focusing on, especially in the one-dimensional waveguides, which are basically called corrugated waveguides. Well, I call them this way, but you can call them the way you want. And you have also these two-dimensional photonic crystal slab. A lot of work has been done, but now it's a little bit, I would say, decreasing. But there are very nice work on two-dimensional photonic crystal slab, and the three-dimensional photonic crystal. It's well, let's say a basic example of a wood pile photonic crystal, but it's much more challenging to achieve these structures in terms of fabrication. So we chose that because it's easier to fabricate than this and that. Also, okay, so how to, let's say, what is slow light basically? What you have is, this is a dispersion diagram of this waveguide, one-dimensional waveguide, and you have the optical modes. I mean, depending on the k vector. So you have the frequency as a function of the k vector, and these are the bands. These are the first order modes, second order, and third order, and then you have much more modes, which are actually, let's say, above the light line. So a light line is the green line here, and all the modes that propagate below this, above this line, are called leaky modes. I mean, they are leaky, so they're not propagate, or they propagate over very short distances. And what happens is that at the Brillouin zone edge, what you have is that your bands are actually flattening. So that means that your group velocity, which is the derivative of the frequency on the k vector, tends to go to zero. So as you move a little bit away from the slow light, from the zero group velocity region, your group velocity is increasing a little bit, and what happens is that the group velocity is not zero, but less than what it would be in, let's say, a conventional waveguide. So that means that you achieve a slow light pattern with very high field density inside the waveguide. So that's, and this interference pattern propagates much more slowly through the waveguide. So that's the way, the way we'll be using this, let's say, mode to increase the interaction with free carriers and optical mode. So here is, let's say, the passive characterization of these waveguides. So what you can do is that you integrate one waveguide in one Mach-Zehnder, a symmetric Mach-Zehnder interferometer. So what you have is, this is the fast light region on both sides, and as you get closer to the band gap, what happens is that the FSR, let's say the free spectral range of the Mach-Zehnder, is actually decreasing, increasing first because of the particular geometry of the waveguide, and then decreasing. So here you are in the slow light region, and if you compare that to a straight waveguide, straight slow light waveguide, you can see perfectly that you have a nice photonic band gap in the middle of this. So photonic band gap, it's let's say band wavelength range where you don't have any propagation. So light is actually do not propagate through the waveguide. It's just reflected back or absorbed. So here you can calculate from this spectra actually the group index or the group velocity, which is clearly increasing as you approach the photonic bandgap edge, and you have different modes. This is the fundamental modes, which is the one you will be using, and the first order mode. So about the simulations, So what you do is basically you take how to simulate this. Well, basically what you do is you first use let's say electrical simulator, semiconductor simulator, and you just draw this actually waveguide. You actually see what happens when you apply voltage and which carrier density you achieve as you apply the voltage, as you increase it, and then you convert this back to let's say I had a MATLAB program which converts this change in carrier densities into a change in refractive index and absorption. So as you increase the voltage, actually 2 volts, 6 volts, and 10 volts, this is directly the effective index change, the refractive index change inside the waveguide. So you can see that as you apply the voltage, that the refractive index is changing quite much. So for a slow light modulator, you can do a 2D model, 2-dimensional model with the thin section and the wide section, and then what you get at the end is that clearly, as you increase the group index, so you're working close to the band gap edge, you really increase the efficiency of the modulator by a factor of 10 for a group index of 50. So that's really interesting to achieve low power consumption modulator. But first, we had to work to show that our modulator, the modulator is working, and that actually, as you go close to the band gap, you actually also increase the efficiency, and that's clearly shown here. So as you experimentally, we achieved a group index of 22. That's the maximum group index we could measure, and we clearly see that there's an improvement of a quite important improvement. So what we did is just what you do is just modulate close to the region where the efficiency is much higher, and this allowed us to actually reach 40 gigabits per second modulation with actually 5 volts, extinction ratio of 6.6 dB, and insertion loss of 9 dB. So depending on the operating point here, you achieve an extinction ratio or another, but then you also increase the insertion loss of on the one level. So here is the device. So you just apply the signal here. This is the fiber which is coupled to the waveguide through a grating coupler, standard grating coupler, and then here you have the Mach Zehnder, and then this is a traveling wave modulator, which means that as you apply your signal, electrical signal is traveling along the optical signal, and then you reach much higher bandwidth. And then at the end of the silicon modulator, what you have is 50 ohm low, which absorb actually the electrical signal. So it don't get reflected back to the input probe. So at the time it was a nice result, and we achieved a very high efficiency compared to other, let's say, conventional modulators, with the drawback that we had a little bit more insertion loss, but still comparable to the literature. And we had the good point is that we had a very short device, which was 0.5 millimeter long. Also, you can use this modulator, make it a little bit longer, and achieve and then using this longer modulator, you can get closer to CMOS drive voltage requirement, and we had a modulation at 10 gigabits per second with 1.5 drive voltage and 2 volts basically. So the problem is that, of course, as you get close to the band gap, you increase also the losses as more light gets scattered through the waveguide. So you can directly plot the the insertion loss as a function of the group index, and in our case, we actually realized that it was linear dependence. So at a group index, let's say moderate group index, you can achieve 12 dB insertion loss. That's the insertion loss of this modulator, the 1 millimeter long modulator. So there's actually we should find a trade-off between how low should be the group index and what efficiency at the end you want to achieve. But this figure can be really improved because also you have the problem of the coupling from the fast light waveguide to the slow light waveguide, And this is actually, in our case, let's say the taper wasn't really optimized for this. So you probably can really optimize this. You can really optimize this loss figure by actually optimizing your taper from the fast light mode to the slow light mode. So to actually decrease the impedance mismatch between the two. Another, well, let's say, very nice low drive voltage modulators, which are based on silicon ring modulators. And this is another way of achieving low drive voltage. So you have this realization here from P. Dong from, I think it was Couture at the time, and it was published in Optics Letter in 2010. And they achieved a very nice 12.5 gigabits per second modulation with only 1 volt peak to peak. Also here, a more recent paper, which is based on interdigitated PN junction and 25 gigabits per second with very low insertion loss and low drive voltage. And the last one is more recent, but this one is based on PIN injection, but it goes up to 50 gigabits per second, but I think they use a pre-emphasized driving signal, which is quite complex to implement and real systems, basically. So they reach a very high speed. It's really impressive in terms of speed. Well, the eye diagram is not really well open, but still it's a modulation. So, and they achieve also low drive voltages. So the drawback of this is the narrow optical bandwidth, of course, that you have to then, if you want to integrate that in the real system, this device, what you need is a thermo-optical tuning system like thermo-optic systems, and this can increase your basically your power consumption. Well, let's say you can also, it's an alternative way of achieving modulation using rings. You can just increase, you can insert your ring inside the Mach Zehnder and not playing, well, here you play basically with the phase response of the ring, and you don't want to work it at the critical coupling region, which is all ring modulator designer wants to do, is just working at the deepest, let's say, extinction ratio possible. But here you don't need that. You just overcouple your ring, and this is enough actually to achieve a phase shift inside between the arms of your Mach Zehders. So this was a work realized in collaboration with Laurent from ParisSud, and this is their PN junction basically, and actually worked pretty well. Although the eye diagram looks quite noisy, but that was because actually the RF electrodes weren't really well, let's say, optimized for this, and we had a lot of reflection to the driver. So we achieved 10 gigabits per second for this. And also, yes, this is nice because you don't have that much sensitivity to fabrication deviation, and actually because you work in this regime, and you don't need to meet the very sensitive, let's say, critical coupling condition. So, okay, I talked about rings modulator, which actually have a very narrow bandwidth, and also silicon slow light modulators based on one-dimensional correlated waveguide, and they have also a narrow bandwidth, which can be estimated to about 1 nanometer at a group index of 10. That's the group index we were working with, basically. So this is very small, and for real application, it's really challenging to use. So here, I can show you. I took basically the same waveguide, and I just pattern hole on it. It was quite. I don't have a clear model for this, but basically what I realized is that as you increase the hole diameter, you also just you flatten, let's say, the band at the edge of the Brimont zone, which means that you have a section. It's not the edge, basically. It's so you have a kind of inflection point, which can be approximated by a straight line. So that means that your group velocity is constant, because this is a derivative of the frequency on the k vector, and that gives you a constant group velocity in a given frequency range or wavelength range. So that gives you a nice U shape like this. So this is the group index of the function of the frequency, And you have this region here, depending on the hole size. Here is the hole size. And what you achieve is constant group index in a certain given wavelength range. So this was the early design, and actually we included this waveguide inside a Mach-Zehnder interferometer, and we were able to calculate a group index of 13.5 over a 40 nanometer range. So that's much better than the conventional, let's say, corrugated waveguide I showed you before. And basically, the problem is that, of course, because the mode is centered inside the holes, is, let's say, you have lots of out-of-plane scattering, and also the coupling wasn't really, let's say, optimized. But at least you have a proof of concept that it's working. And then we improved this waveguide, and so this was done with E-beam lithography. That's why you see here sharp edges, and here it's a kind of rounded off. That's because basically it's deep UV, and then you have proximity effects, optical proximity effects, which I didn't correct in the GDS, but still you have this periodicity, which is the main, the important point for this. And you have this nice transmission curve of a Mach-Zehnder, and actually we calculated, based on the fringes, the group index as a function of the wavelength. This was also, let's say, characterized via an optical phase measurements. So it's just measuring the phase directly in a straight waveguide, so you don't need to use these fringe measurements. It's much more, let's say, accurate. And there's a good agreement between the two methods. So it's confirming, using two methods, that really you have this U shape here. So you have a nice, let's say, 7, 8 group index of, group index of 7 or 8 across a very large bandwidth, which is higher than 30 nanometers. So that is very interesting for applications. So you can use that, for instance, in a wavelength division multiplexing system, and you can couple multiple wavelengths, and then you can work in a wide bandwidth, because your Mach-Zehnder actually have a bandwidth of more than 30 nanometers, which is probably, I would say, enough for applications. And then you have less sensitivity, and then you get higher, let's say, you get higher efficiency in all your modulators, so shorter modulators or low drive voltage modulators, whatever you want to for your applications. Okay, so I will talk about the switches. Also, it's let's say most of my work was realized in the modulator field, but switches are quite similar to modulators in terms of mechanism. So there are differences, but I mean the mechanism is the same, but there are differences. Actually, the switching speed is not as high as for modulators, for instance. So you don't need really to achieve a very high electro-optical bandwidth, and that's why most of the switches published in the literature were based on PIN diode, which is an injunction-based mechanism, or a thermo-optic effect, which is a very slow but very efficient. Because what you need also for switching applications is full pi phase shift, which is usually not achieved in silicon modulators, high-speed silicon modulators. I mean, this is to avoid, when you have a 2x2 switch, you don't want much power to go into the port, let's say the cross ports or the bar port, depending on where which signal you are switching. So the power consumption is also critical, and it has to be decreased down to very low values, and the same for modulators. And also, what you have in the switching matrices is that you have a lot of switches which are cascade, and this means that you need really to have very low loss devices, and efficient devices as well. So that's you have no choice but achieving this low loss figure and efficient device, let's say modulation efficiency figures. Here are very nice realization. I mean, these are recent work on the 4x4 switching matrix that basically shows you all three of them are based on the PIN injection mechanism. So you have the 2x2 switch, which is the same as this one, and I mean this was done by IBM and this as well. And this was done by a group, was made by a group in China, I think. So actually here what you have is you transmit the signal through the 4x4, and then depending on the voltage you apply to the switches, at the output you get the signal here, depending on, you route the signal basically. So here you have, for instance, a nice realization, 40 gigabit per second signal transmission through the switch. And this was only characterized in the static regime and showing a power consumption in the static regime of 7.1 and to 20.4 milliwatts, depending on the path the signal has to follow. Here also, no gigabit signal transmission, only static transmission, similar value of the power consumption. And here is the more recent, very nice realization, which was actually characterized, published in GLT, and made by IBM, and also it was connected to a PCB, so you have it was very nice results. And they also characterized the switch, estimating the dynamic power consumption at 47.4 milliwatts at 9 megahertz switching rate. And you have, this is mainly actually due to the thermo-optic tuning they're using to actually tune the phase inside the Mach-Zehnder interferometer, and also the driver power consumption inside the circuit. So basically in Foxtrot what we want to do is the same. So we have designed 4x4 matrix based on Mach-Zehnder interferometers and also ring resonators. And what we want to reach is a very high switching speed and also a very low power consumption. But the difference is that we will be using the carrier depletion mechanism instead of using the injection regime to achieve very low power consumption. And that's the goal of this project. So devices are under fabrication right now. We have modeled all the basic building blocks in terms of passive components, and we can see that, of course, the results are quite in good agreement with the experimental ones. So this was a collaboration between NTC, UPVLC, my group, and also CERT here in. We have many different components, Mach-Zehnders, symmetric Mach-Zehnders, and 2x2 cross-shape switches, which are collaboration also with the CERT. And, well, let's say basic functioning of a thermo-optic switch to show that it's working, and it's been published also in Photonics Europe 2014. So what are the conclusions of all this? Is that we have a lot of work has been done in silicon on silicon modulators and switches, but still I think for real application we really need to lower the power consumption, which means that we need to lower the drive voltage. We need to increase the modulation efficiency. So slow light is just an example, but that means that it's possible. I mean, we have to find a way to get to this point, and that's really, I think, necessary for real application, especially for interconnects where you need very low power consumption figures. We also need to decrease the overall modulator switch loss, or switch loss, and basically without compromising the performance, their performance. So all these aspects are currently under study, and promising results have been already obtained. You have many different mechanisms that you can use, especially the Pockels-Effect silicon, which is really promising to me. And so we need really to try to focus our research on harnessing light matter interactions, and that is to push forward the limits of active photonic devices. Thank you very much for your attention, and I acknowledge Elias Project, Foxtrot, and European Commission, and I forgot my group. Thank you very much. You're welcome.
So, any questions? I have one regarding the thermoptic switches that you showed at the last slide. What was the speed, actually, the power consumption that you could reach with
Which one? This one?
no,
Yeah.
your thermoptic switches?
Yeah, the power consumption was, I think, 3 milliwatts. But we didn't characterize it in in highest. It was just a static characterization. So as you apply a voltage through the pads, what happens is that you got a current flowing through this wire, and this is actually just by measuring the currents you get. We reached, I think it was 3 milliwatts for just the 2x2.
And is there any special reason for having this asymmetric mass center layout?
Yeah, it looks like actually a camel or something, but this is basically actually it's for let's say asymmetric layout. It's easier to characterize the phase shift you achieve using just the asymmetric design, let's say design, because what you have is on the spectrum it's not symmetric, so you can actually estimate much easier in an easier way. Sorry. The phase shift you achieve, just looking at the spectrum, which is not as easier in symmetric configuration.
Any other questions? I think that everyone knows who they are. So, thank you very much, everybody.
You're welcome.
The next talk now comes from Ralph Meyer from the Technical University of Munich, who is going to talk to us about actually the backbone of the transmitter technologies, about VCSELs in optical interconnects.
Thank you, Nikos, for this kind introduction and for inviting me to this summer school. And hello, everybody, to this talk on light emitters, especially single-mode emitters, and the different technologies, how to realize them. During the last days, we heard a lot of presentation about the ideas we have, how to set up new or larger metro networks and to improve the data transfer between different servers. But today I would like to step back and look more into the details of the connectors, especially the elements with which we can produce the light itself, the technology behind, and also the material issues we have to face when you want to realize these kind of devices. So first of all, why surface emitting lasers? And one major point is already, if we have a look at the beam shape we can get from these kind of lasers. Here you see a comparison of an LED or an edge-emitting laser because of these very thin layers we have in an edge emitter, but a wide width of the ridge. We have elliptical shaped beam, and only the VCSEL itself can give you a low divergence circular beam. So this will give us a lot of help in coupling this light into glass fiber. So we have simpler optics, and with this we of course have some kind of simpler packaging. And together with the possibility of wafer scale fabrication and testing, this will end up in lower costs for the overall process. And here you see a 2-inch indium phosphide wafer where we have 24,000 VCSELs on top of it. Furthermore, since we have a system where we have the light emission to the surface of the structure, the integration of arrays in 1 or 2 dimension is feasible. And here you see a structure where you have 19 surface-emitting lasers. Each can be separately addressed so that it's easy to fabricate devices with a high degree of parallelism. Furthermore, since we have these very small active volume, the power consumption of these type of devices is quite low, and the efficiency is very high. So this is also a device for some kind of green electronics. And of course, this small size also helps us to achieve very high speed modulation already at very low currents. But since obviously this talk is the only one dealing with the emission of light, I would like to develop the basic building blocks we need to fabricate the surface-emitting lasers from some basic physics of single-mode lasers. Afterwards, I would like to show you how the short wavelength VCSELs are fabricated, and at that point, gallium arsenide is the material of choice. However, if you then want to go into the longer wave regime, meaning 1.3 or especially 1.5 micrometer wavelength, you have to change from gallium arsenide to indium phosphide, and this is a major change in the technology you need to realize these devices. And in the last topic, I would like to comment a little bit on the laser dynamics and what kind of optimization processes we have to undergo if we want to fabricate real high-speed devices. So let's come to the first point, the basic physics of single-mode lasers. So I think we can take it as granted that your epi foundry or your epitaxy department is able to supply you with some decent material that give you the gain for the optical process. In fact, you will have something like this spectrum if you do photoluminescence experiments or some kind of electrical-driven luminescence, but the shape of this function is mainly dominated by the density of states of your material and the Fermi function, so which states are occupied by the electron in the conduction band. The width of this line is, of course, depending on the kind of structure you use. So in case of a bulk material, you will have something like 45 MeV at room temperature. If you go to quantum well, this is already smaller, but nothing that you would call useful for single-mode emitters. But of course, this material is not infinite, but if you have a finite piece of semiconductor, the surface between the semiconductor and the air, for instance, this interface already gives you rise to a reflectivity of around 30%. And so if you have two of these surfaces, the light will be able to travel between these surfaces, and this will cause a Fabry-Perot resonator. And from the length of this resonator, we can get several modes that can travel if they fulfill this condition. So at least the wavelengths have to be twice the length of the resonator. This gives you a compound structure. So this would be the modes that will be traveling through this device. And from this gain profile, we will end up with something like this. This would be the mode profile of an edge-emitting laser. And the distance between two of these modes is on the order of 2L divided by I squared. This will mean if you have an edge-emitting laser of a length around 1 millimeter, you will have a delta lambda on the order of half a nanometer. So if you want to improve our spectral purity a little bit more in edge emitters, black reflectors are implemented. This means mainly we have a corrugation in the refractive index. So for a certain thickness, we have a higher reflective index and here a lower one. And at each interface, part of the light that is traveling parallel to this corrugation profile, part of the light is reflected. And if we do now our mathematics quite fine, and we fulfill this condition, then you will end up with a filter function that will give us only one single mode, and the other modes that may arise from the rest of the Fabry-Perot resonator will be suppressed to a certain extent, so beyond 30 dB will be feasible. So the Broeke wavelength that we define here is mainly determined by the effective refractive index and the thickness of the different layers. So far, the story is also correct for edge-emitting lasers, but for our surface-emitting lasers, we shall keep in mind that the intensity, the reflectivity of this laser, of this structure, will depend on the step height of this profile, so the difference in the refractive indices and the number of interfaces we have. So if we now want to fabricate a surface-emitting laser, we can start with an active material. So now the light should go in this direction, but in this case, the thickness will be limited to something on the order of 100 nanometer. To give you absolute values is not really helpful at that point, because you have to look for the optical thickness in these materials, and everything has to be looked at in respect to the wavelengths you are aiming for. Okay, so the light has to be in the perpendicular direction. So this active region is to be placed within the cavity, and with this we can address or realize the modes we want to achieve. But now we have a cavity length in the order of a micrometer. And this means that the delta L between different modes is so far away that we will not have additional gain for other modes. So with these short cavities, we will be able only to achieve one lasing mode in this direction. But since the thickness is so low, only 100 nanometers, of course we will need a very high reflectivity, because laser as a light amplification system needs light that should be or that can be amplified. So each light that we can use is lost for the laser. This means if we have only 100 nanometer thickness, the amplification is of course much lower than in the case of an edge-emitting laser where we have a millimeter. So a reflectivity of the mirror of 30% is by far not sufficient. What we need are mirrors that are exceeding a reflectivity of 99%. Most helpful values 99.5, 99.8 at the bottom. So, and how to realize now these reflectivities with one single layer? This is not possible, and there again our DBR comes into play. So if we fabricate a layer stack of different materials, we can increase the reflectivity to the values we need, depending thickness, numbers of interfaces, as we would like to have. So with this, we can end up with a system where the light is mainly traveling around between these different mirrors, and only a part of this light is going out of the cavity, but this is the light we're interested in. As we already heard, because this is very thin, we will only have one mode in the perpendicular direction. However, in the area, nothing is confined. So if we look at the transverse fields, we have, depending on the radius and the angular, a lot of different modes that are possible. But however, we are only interested, of course, in the fundamental mode, where we have this Gaussian-shaped profile. This is what we would like to have. But which of these modes will come out of your laser will depend on the size of your aperture. So this means we are able to get this fundamental mode only if the aperture, where we have some light amplification, will be on the order of a few microns, and this means that we need a current aperture to restrict the light amplification to a very small volume. So by this, we already have the most parts we need for a VCSEL. Just to comprise it here, we have an active region where we can get some current flow from the top through the mirror into the active region. We create some light, and on the bottom, the current will leave the structure. We have some Broeke mirrors on top and at the bottom, and we will end up with a transverse intensity in our optical field like this, and in the vertical direction we have this kind of standing field pattern. But the point is, what is happening when we apply some current to our structure? Of course, it will heat up. So we should keep in mind that we would like to operate these lasers already also at elevated temperatures, not only at room temperature. And here we have to think about that some values for 1.55 micrometer material, that here you see the shape of the reflectivity profile of our dBr. And then we have our gain curve, and you see the fundamental modes and the higher order modes, and here you see, okay, these will not laze anymore because we don't have any gain. The problem of temperature is now that if the temperature rises, the dBr will shift and also the gain curve will shift, but with a different speed. So if you look at the shift of the dBr, this is on the order of 0.1 nanometer per Kelvin, and for the gain profile, we have a shift as high as 0.5 nanometer per Kelvin. This means that we have something like this as a net effect. So when the laser gets warm, the gain will go down, and it may happen that the laser will be switched off and not lasing anymore. So to get lasers that are able to emit light also at temperatures as high as 80 degrees or more, we should optimize our structure, we should optimize our structure in a way that for room temperature we don't have the optimum situation, but in case the laser gets warm, we run into the optimized state, giving us the possibility to achieve higher temperatures. Okay, so much about the building blocks of VCSELs. And now let me come to the short wavelength material, where gallium arsenide is a material of choice. Here you see a map of the gallium arsenide of the 3-5 world, the energy of the different compounds and the lattice constant. And here you can see gallium arsenide with the energy and a lattice constant. So all binary compounds are a dot, the lines are ternary materials, and all areas are quaternary alloys. If we have a look where we will find 0.85 micrometers, you see this is very close to gallium arsenide, and this is what makes life so easy in the gallium arsenide world, because as a gift of nature, aluminum arsenide has nearly the same lattice constant than gallium arsenide, so we can play around a lot in varying compositions. We have a very large difference in the energy, giving us a very high difference in refractive indices. So we have all ingredients we need to fabricate a very good laser. So since this was already achieved years ago, decades ago, I think we can take it as granted that gallium arsenide VCSELs will work, so we can directly concentrate on how we optimize it for high speed, for instance. And if we look here at the active material, to start with, a small quantum well of gallium arsenide will be already sufficient to supply light emission at 850 nanometers. But if we add some indium, gallium indium arsenide, it's also possible. But with this, we increase some strain, and this is helpful to get more differential gain and more light out of this structure. So what the colleagues in Sweden from Chalmers, where I get these information from, realized was a structure. If you look at the gallium arsenide system for the active region with the 8 nanometer thickness, you will end up with a certain differential gain. And calculations made in Ireland showed that if you now increase the indium content, you will double the differential gain, and this gives you 30% less threshold carrier density. So this means you will need less current to reach carrier inversion, so the lasing will start earlier. Furthermore, since you are restricted in the thickness of this material, you have to, or you can use smaller thicknesses. Of course, you have a difference in band gap, so also you have to cope for this. But this means that you are able to increase the number of quantum wells, giving you more light output. If we have a look at the cavity that can be used in gallium arsenide structures, we see that it's beneficial if our quantum well structure have a very high overlap with the optical field. And what was done here is that the cavity length of 3.5 lambda was reduced to only 1/2 lambda, and here you can see the overlap will be increased by 20%. The optical confinement factor is higher, so we have an increase there, a transport, and a reduced diffusion capacitance. Coming to the next point, the current aperture. And at that point, I have to mention that there is one major drawback of aluminum arsenide because it's not stable in air. It's easily oxidizing. But at some point in history, people come to the idea, can we not make something useful out of this fact? So this might not be a bug, make it a feature. And the point is that if you open the aluminum arsenide layer at the side of the structure and you put this into some steam oxidation oven so that water vapor can affect this material, then the aluminum arsenide can be transferred to aluminum oxide. And this is a very perfect current blocking layer. It's an isolator. So in this case, we can define a current aperture here. So the current will flow in this direction to the center, and we can define the width of this insulator by temperature, by time, and also by the concentration of the aluminum arsenide, because it has to be close to 100%, but we can play around a little bit with it. If we now have a look at the mirror that are used on gallium arsenide structures usually, we see because of the problem of the oxidation of aluminum arsenide, usually combinations of aluminum gallium arsenide is used, but with avoiding 100% aluminum arsenide. But on the other hand, the thermal conductivity of ternary materials is much lower, as you see here, than for binary materials. And therefore, they tried, at least in the lower part of the laser structure, to use some aluminum arsenide layers, and with this, they were able to increase the thermal conductivity of the overall DBR structures by 40%. So, to end up the discussion of the different building blocks, this is an overview of the structure for 850 nanometer gallium arsenide-based datacom VCSELs. And as I already mentioned, they used strained gallium indium arsenide layers with the LGAS quantum well structure. Then here we have these multiple oxide layers to define the current aperture, something I did not comment in detail. Due to a very fine doping profile, they were able to reduce the resistance in the DBR, and also the surface was optimized to photon lifetime to a short cavity system, so that high speed is really achieved. And on the bottom side, this high thermal conductance NdBr is used. And with this structure, they achieved the following values. If we have a light current voltage diagram here, you see the onset, the threshold current densities on the order of a milliamp, and with these devices, 4 micrometer oxide aperture, they will achieve something like 5 milliwatts output power, but the lasers already worked until 85 degrees and higher. But what you can see also, since the current is going through all these mirror layers, this gives rise to some resistance. And here you see the voltage onset is on the order of 2 volts. So the differential resistance is something 160 ohms. If you increase the oxide aperture, of course, the power you will get out of the structure will be higher, and the resistance will be reduced to 80 ohms. Looking at the small signal modulation results, you see here the modulation response with a resonance frequency here. And if you look where you have the highest 3 dB frequency, you will find that 28 gigahertz was achieved at 25 degrees centigrade for this 4 micrometer aperture, and even for 85 degrees, 21 gigahertz was achieved. So this is state-of-the-art, at least on the side of gallium arsenide, but now I would like to go to the longer wavelength side of the spectrum. And the next step would, of course, be 1.3 micrometers. But at that point, we have to face the fact that there are different strategies to achieve this. Of course, 1.3 micrometer can be reached on indium phosphide. An edge-emitting laser is the indium phosphide, the well-known material of choice. In surface-emitting laser, it's difficult to use indium phosphide. I will show you in the next slide. But for 1.3 micron, there are some strategies to still use gallium arsenide. The main problem is that you cannot use only indium with this concentration. This would be by far too high strain, so the active region will crack and you will get no light out of the structure. But to handle this strain, there is a point where if you add this very large amount of this big indium atom, you can, on the other hand, implement some nitrogen, with, on the other hand, is a very small atom, and by this you can handle the stress in this layer. So with these diluted nitrides as the active region, you can have a technology where all other building blocks can be the same. You have, of course, to adjust everything to the other wavelengths. But the strategy behind can be the same, and as you see already, high data transfer was achieved with these devices. But since this is the intermediate regime, I would like to now make the full step to the long wavelength VCSELs, meaning the step to 1.5 micrometer. Here you see we have the possibility only to get these lasers on indium phosphide based materials. But the point now is that we have to have a closer look into the heat removal of this system. So what are we really doing when operating a laser? We are injecting some current, and with this current we are injecting some carriers into our active region. If we have a carrier density succeeding the threshold value, we will have stimulated emission of photons, and all of this is governed by rate equations. But we have to keep in mind these are all restricted to the thermal parameters of our system. What I mean is the following. Above threshold, the number of carrier inside our active region is fixed. This means that if we increase the current, the additional carriers that are injected are immediately transferred into additional photons, increasing our optical power, and that's what we are interested in. On the other hand, this increased current will lead to a temperature increase, giving a higher threshold current we need. So this difference, in this difference, we cannot take the threshold current density as a constant value, but it's subject to the operation conditions of the laser. Because the temperature in the active region, and I mean really the active part of the laser, not of your heat sink, it's the main point we are looking at, and to remove this heat to a heat sink will depend on the thermal resistance we have between the active region and the heat sink. And now, this heat usually has to be transferred via the DBR, but if the resistance is too high, no lasing at all will occur. And in the early stages of developing long wavelength VCSELs, also the large companies had to face the fact that there is no idea to circumvent physics. Yeah? So in the early stages, devices were fabricated that when you switch them on, they got warm and they get off. So a device that, when it's switched on, gets off. Not very useful. At that point, you have really to think about which material you want to implement in your device. And here is a diagram of the reflectivity of Broeke mirrors and some values here, aluminum arsenide, gallium arsenide, and you see we have a quite nice high difference in the reflective indices, and you see that with a decent number of dBr pairs, we can achieve quite high reflection. But if we now go to a system on indium phosphide, so the other border in this diagram, we see that the difference in the reflective index is only half of it. This means we have to double the number of pairs to achieve the same reflectivity. And as I already said, for a bottom mirror, 99.8% reflectivity is a good value. So this means in the case of gallium arsenide, 20, 21 pairs will be sufficient. But on the other hand, for indium phosphide-based material, we may need up to 40. From the number of pairs, including the wavelength, we can now calculate the thickness we need for this reflectivity. And of course, the number of pairs directly will be shown here, 5 micrometer for aluminum arsenide, gallium arsenide, and twice of this value for the indium phosphide material. But now we have to take into account the thermal properties. And if we now include in our calculations the thermal conductivity of the different materials, then you will see that this mirror will have a thermal resistance for one special design of only 300 Kelvin per watts. On the other hand, a mirror with the same reflectivity based on indium phosphide will have 1 order of magnitude higher thermal resistance. And my comment before, the laser will not be working if this value is too high. So the resistive heating cannot be dissipated through the epitaxial mirror, at least for the indium phosphide-based material. So we have here a summary of the issues we have to solve when realizing lasers based on indium phosphide. The first point is we want to reduce the heat generation, and this means we have to reduce the series resistance of our structure. Second point is we have to use some kind of current aperture. But how to define a current aperture on indium phosphide? Because, as I already mentioned when talking about the aluminum gallium arsenide structure, the steam oxidation works only for a high concentration of aluminum arsenide. This means close to 100%. The highest value in our material system here is aluminum indium arsenide. It's roughly 50%. So by no means we can oxidize this material in a way we are able to do this on gallium arsenide. Next point would be the implementation of thinner mirrors or the usage of materials with a higher thermal conductivity must be possible to a certain extent to improve the heat removal. And another point, optimized wave guiding would be helpful to achieve a nice optical design. So something like 10-15 years ago, a concept was developed that is called the buried tunnel junction concept, and with this concept you are able to fulfill nearly all issues at once. This structure is mainly a laser structure without any mirrors. It's meant for testing the electrical properties of this kind of device, so the idea is to really have a current aperture to define the current on this small area. And here we have to look in the band diagram of this structure. What we here use is a heterostructure of very high doped N plus P plus layers that are located in this area. And the doping of this material is that high, and we use low band gap material, that the band is shifted so far that the Fermi levels lie within the band. So at that point, the electrons can directly tunnel through this very thin barrier, giving rise to a really ohmic contact. On the other hand, if we now have a look at the outside area, we have this low-doped indium phosphide on this P plus layer. And this means we have, as usual, a depletion region in this area, of course, with a very much higher thickness. So tunneling is not possible in this area. And if we now look into the electric properties of this structure, we will see that if we use a structure where the diameter of the tunnel junction is exactly as wide as the full mesostructure, we have a very nice current flow, and we achieve very low ohmic resistances on the order of 10 to the minus 6 ohms per square centimeter. On the other hand, if we don't have this tunnel structure at all, so giving us a 0 for this structure, we have only this blocking part, then we see that at a certain voltage we have something like 3 orders of magnitude lower current flow, and this means that the current flow is really restricted to the inner part of this tunnel junction. So with this, we are able to circumvent the problem of the mirrors, and we can use dielectric materials instead of epitaxial ones. So a laser structure for a 1.5 micrometer wavelength can comprise an epitaxial mirror on the top. You see here for these materials, since we use MBE system to fabricate these materials, an arsenic-containing material is quite helpful, but we have this very low delta N. This means for this reflectivity, we need a high number of pairs ending up with a very thick layer. For the bottom, we can use materials that have a very high delta N, even better than aluminum arsenide, gallium arsenide. We use only 3 pairs, an additional a half one here, to achieve 99.9% reflectivity. The thickness is lowered to, this is not micrometer, but microns. So here we have 8 microns and 1.6 microns for the bottom mirror. To look at the full structure, we will see here the epitaxial mirror on top, together with the N-side contacts. We have here the strained quantum wells, the tunnel junction, and the dielectric mirror at the bottom, and everything is on top of an electroplated heatsink. Or in more detail, on this side here you see the standing wave pattern, and if you look in the inner part of this, you will see the tunnel junction, because it's made of very low bandgap material. It has absorption, therefore it's placed in the node of the standing field pattern. On the other hand, the active region, of course, in the antinode. Here we have the dielectric mirror, and the current is now flowing from the side into the structure to give the amplification here, and the heat is transferred via this direction. The design elements in the full structure, if you go for more 3D version and high-speed application, you see here we start the fabrication with an N-doped DBR. Then we have some cladding layers and the strain active region that gives us the high differential gain. And then the tunnel junction is fabricated. What I want to point out at this point, you have to structure this tunnel junction. So in fact, this whole fabrication is flip chipped. So when starting, the substrate is on top. So this is not anymore here, but this is the indium phosphide substrate. Then you have the growth, you have the fabrication of this tunnel junction, and afterwards you turn around everything and remove the substrate. But this also means that we need a 2-step overgrowth. So in a second growth step, we will deposit our low-doped indium phosphide, and afterwards we can finalize the whole structure on the front side. So we apply the bottom mirror and the gold heatsink. We have this very small chip size because the whole semiconductor material is not much larger than the aperture of our structure. For high-speed applications, we of course use the passivation by BCB. And we have a design with a via contact, so we have the P-side contact and the N-side contact, both on the front side, so that you can apply high-speed experiments. In fact, this device is a gold foil with some plastics around and some incorporation of semiconductor material, some impurities. You may think about if this is still a semiconductor device, but not by volume. So let's now have a look how we can optimize this structure to high-speed applications, and therefore I have to explain some basic laser dynamics properties before. So the frequency response of our laser is described by this formula, and to make it easier just to have a look at it, this is a second-order low pass with a damped resonance. Here you find the resonance function. Here you have the 3 dB function, and you can now push the resonance into the higher frequency regime by increasing the bias current, and at the same time also the 3 dB frequency, so the bandwidth, will increase. In formulas, you will see that the resonance frequency depends via a square root function of the difference between current with respect to the thermal current, threshold current, at the same temperature. And then you will find that in this content, some parameters will be included. Here, the confinement factor. Therefore, when talking about the gallium arsenide structure, the number of quantum wells is helpful. If you can increase the confinement factor, you will end up with faster devices. Here you will find the differential gain of your material. So also the epitaxy already defines the speed of your final device. And the damping rate that should be low is governed to a certain extent by the photon lifetime. So you would like to reduce the photon lifetime in your structures to end up with high-speed devices. And now let's have a look. How can we reduce the photon lifetime? What possibilities do we have? And here again, a sketch of the structure as depicted so far. Here we have our bottom DBR, the active region, the epitaxial top DBR, and the standing wave pattern. And since we have so small difference in refractive index, the standing field pattern penetrates quite far into this top mirror. And therefore, we have to implement something like an effective cavity length. So not the geometric value that you define by epitaxy is the important point, but you have to take into account how much of the mirror you have to add at that point. And you may think about to improve the speed of your laser by how often the light will go through this active material. So if this distance is large, the number of times the light is passing the active region is lower than in the case that you reduce this length, and you will find that the effective length will be proportional to the photon lifetime, or inverse proportional to the resonance frequency. And therefore we came up with other design so that we replace also the top DBR by a dielectric top DBR, and as you can compare from the penetration into the mirrors, this will reduce the effective cavity length quite strongly. And this is meant in our term the short cavity VCSEL concept. So the high-speed design elements in our structures are this tunnel junction for the current aperture. We have 2 dielectric mirrors, and we have the strained region for high differential gain, and of course our excellent heat management by the gold heatsink. Nevertheless, of course, we have a lot of parasitic effects. Here we have the BCB and the contacts on the top side, but since we use BCB at this part in the parasitics, it's not a dominant factor, so this is a part we can neglect. On the other hand, if we look in the inner part, so maybe mainly here, then at that point the current aperture relies on the width of the depletion region. But this gives rise to a certain capacity, and this may be a limiting factor in the overall design, so you should use here a low-doped indium phosphide to reduce the parasitics, but on the other hand, this material also is used in the inner part, increasing the series resistance if it's low-doped. So you have to find an optimum way or value for this. If we now have a look at the performance of these devices, we see that we get output powers comparable to the gallium arsenide value of 4 milliwatts, and also we are able to operate these lasers up to 90 degrees and even more. What you can also see is that the onset of lasering is on the order of 1 volt. And if you keep in mind that 1.5 microns will be transferred to 0.8 volts, this means for all series resistances, we need only as low as 200 MeV, 200 millivolts to get the system running. The very low currents we need for the threshold, it's on the order of 1 milliamps, but also this is comparable to gallium arsenide. And if we now look at the parameters of quantum efficiency, then you see that the temperature dependence of our differential quantum efficiency is quite high, on the order of between 30 and 50%. The wall plug efficiency is on the order of 20%. And if you look at the threshold current, then you see what I meant in the beginning. You see the increase of the threshold current with temperature. And we already used in this structure, at least this was the idea, an offset of 25 nanometers. So the active region was shifted 25 nanometers into the blue. And to have even higher operating temperatures, this minimum should be perhaps there. Of course, then we have, at room temperature, less performance, but we can go to higher temperatures. The spectra of these lasers show that we have a side mode suppression ratio of more than 45 dB, and also the polarization suppression is more than 30 dB, so we can really talk about single mode lasers. And the S parameter measurements that were done with a VCSEL and a photodiode that were connected to a test set showed that we have a high resonance frequency giving rise to a 3 dB bandwidth of 17 gigahertz at this point. We have no relaxation overshoot and a high modulation bandwidth because of our reduced cavity length and the reduced photon lifetime. So with this, I would like to come to the end of my talk, and instead of a real summary, I just want to give you a list of the different parameters that are achieved with the lasers I presented in this talk. But before closing this talk, of course, I would like to acknowledge a lot of people that helped me in compiling all these information, especially Anders Larsen from Chalmers for all the data he supplied for the gallium arsenide VCSELs, and for the indium phosphide material, my colleagues from Munich, Markus Ortsiefer from Vertilas, and Markus Ammann and Michael Müller from our institute, and of course the European project Mirage for funding all of this work. Thanks a lot for your attention.
Hi. First of all, thank you very much. Very informative presentation. It was the first time that I had a chance to understand how VCSELs work. I have a couple of questions, though. If you go on slide 28, when you show the chip around VCSEL, yeah. What's the dimensions of this structure, and how close can you pack them together in an array or something like that?
So usually the aperture is on the order of a few microns. You want to have a single mode, and therefore you are restricted to 3, 4, 5, 6, 7 microns. If you go beyond 10, you need some perhaps strategies, but this is not used normally. Yeah? The MESA width itself is more on the order of some 10 micrometers. Something like 20 will be sufficient. And the overall size, of course, will depend on your setup. This is mainly something like, I think, 250 microns.
Okay, thank you. And second one, by 2020, is it safe to say that we can have VCSELs single mode operating at 1550 that can go up to, don't know, 40G maybe direct modulation.
At that point, you have to think about what do you mean. If you say about the resonance frequency, then it's something different than the modulation you may apply. Because if you look at the function I have shown, the transfer function, of course, if you drive the VCSEL at higher speed, this is possible, but of course with limited output power. So the question at that point is, what is your system capable of to detect? The resonance frequency itself is not the value that you will use in your system, but this is the one and only value to compare different devices. Right. So the resonance frequency is specific for the VCSEL, but not for the setup. Of course, if we have a higher resonance frequency, this will be helpful to you.
Okay, thank you.
Sorry, I also have several questions. Can you go to page 31? There's two effective cavity lengths you mentioned. That you said it's a shortened cavity for your vessel, but my question is how you calculate this kind of effective cavity length, and in your laser, what's the relationship between this effective cavity length with your spectral wavelengths?
So the cavity length is, of course, first given by the geometrical length at that point. And then you have here the penetration into the mirror, and you may use here this value where the intensity is lowered to 1 over E.
1 over E, okay.
Yeah? And if you do this on both sides, then you can add up all these three values.
Okay. Yeah, I get it. Another thing is to make it a single mode laser that you reduce the aperture of BTJ. And what's the shape it looks like? It's a kind of circle shape or it's rectangle?
No, it's not rectangular. It's circular shaped. Usually, the point is, if you look a bit more into polarization, a topic that I did not stress at the moment, then you need some kind of imperfection that might be helpful. So, despite circular-shaped ones, also elliptical might be helpful to give you a better polarization stability.
Okay. And on page 14, you mentioned the phase refraction adjustment in your system, but I'm not clear what kind of phase reflecting adjustment it is.
Sorry?
Page 14.
Yeah.
I think in the presentation you said there's a phase reflection adjustment.
No, this was for the final device at that point. The point is that the colleagues in Sweden want to optimize the photon lifetime. Yeah? This means they want to have a low photon lifetime, and from this point of view, it might be helpful if this mirror is not as high reflecting as usually.
Okay.
Yeah? And they made a small recess at that point, giving a little bit more output, so that the lifetime will be reduced, and they can optimize the mode profile with a small recess on the very first layer.
Okay. Yeah. And the last question is simple. It's is it possible to give a kind of like a slope efficiency for your laser, or because the slope efficiency of your vessels? Because I didn't see it in the last part. You said you has an excellent heat management, right?
Do you mean what value do you mean in detail?
Yeah, I like the slope efficiency of your laser. So the transfer, how much energy we need to produce? Yeah.
Okay.
because I think for me it's much more obvious to see the
Okay.
heat management.
Let's have a check. As far as here you can see some values for gallium arsenide. For the VCSEL itself, for the gallium arsenide based, it's below 100 femtojoule per bit. And
Yep.
for our 1.5 micrometer, I have in mind a product, at least with respect to length, of 24 femtojoule per bit and kilometer.
Okay. Yeah. Thank you.
You're welcome.
From what I understood from your presentation is that the crucial section in the design of the VCSELs is the Broeke mirror that you are using for the VCSEL. In order to make, radical enhancements of the speed of VCSELs, so the focus should be on the sandwich of material that you are using for the Broeke mirrors. This is what I understood from your presentation. Is it true, or it is just my impression?
In fact, it's true, but the main point is that if we do thermal calculations or simulations of this whole structure, we will see that we are forced to use these dielectric material that are restricted in the area. So the size will be quite small. And despite the fact that we have high conducting material, the heat flow will not go through the mirror itself. But the point is, as the simulation show, the point is the heat is created here. We have mirrors that are better in the heat management than the epitaxial ones. However, the transport properties of indium phosphide are much better. So in the end, the heat will not flow through the mirror, but aside of it. Yeah. So we changed the mirror because we was forced to do this, but we had an additional advantage that this mirror has a limited width, and therefore the heat can leave the active region at the side and not through the mirror. But in fact, if you come from the gallium arsenide situation, the mirror is a problem.
To my understanding, you're suggesting the VCSEL as a solution for silicon photonic platforms. Is that correct?
Sorry?
The VCSEL is a suggested solution for silicon photonic platforms.
It's a suggested solution for high-speed data transfer and for coping with the power problems we have. Because a DFB laser is usually much longer and needs higher currents to be operated.
Definitely. So in the considering Foxtrot, it's a solution for silicon photonics as well.
Yes. In Fox, yeah.
Most serious problems in this type of configurations in silicon photonics is the matching of the emitting wavelength with the resonance of the passive components on the platform, on the chip. As far as I know, there's a high dependence on the emitting wavelength of VCSELs on temperature.
That's true, yeah.
Is there any mechanism for tackling this problem in a single mode emitting VCSEL?
You mean to get rid of the temperature dependence?
Yes, or to reduce the temperature dependence.
As far as I know, you have to circumvent physics. This can only be done if you avoid the temperature rise.
Okay.
Yeah, or the question is, what temperature shift is allowed?
Minimize, yes.
Yeah.
Not to completely eliminate it.
So the main point is you have to get rid of the heat of the active temperature. That's the point. So if you improve the heat transfer, this will be beneficial.
And in the shorter cavity configuration that you showed, wouldn't the thermal effects be more significant as
I don't think so, because this part has no connection. Here we have the light output, so there's no heat sink at all. So the heat flow will be anyway on the backside, and the bottom mirror was not changed.
Okay, so the effect is the actual part that causes the problem.
It will not change the thermal properties.
And what about the polarization stability of the single mode?
Okay. Polarization stability is a topic for these high speed, for VCSELs anyway. The point is, of course, these lasers can also be used, for instance, in gas sensing, and then the problem are not that high, so they are still used there. But if you want to use this in case of some grating couplers, of course, polarization is a dominant effect. And as I already mentioned to the other question, since we have a circular-shaped aperture, we don't have any predominant effect so that the TE can be in this direction or the rectangular one. They are either allowed. So we have to implement some imperfection. But this imperfection has to be strong enough to give you this mode selectivity. And what we use to stabilize the polarization is something that is known for quite some time, the high contrast grating. So the high contrast grating is really something, just lines. But the width of this structure is below the wavelength. And this structure will give you reflectivities on the order of 100%. And you have a strong difference between the TM mode and the TE mode. So if you look at the overall reflectivity, this is in dB, this means something like 99.9. Yeah? So this structure is able to really give you the polarized VCSEL emission. The main point is that this high contrast grating works best if it's surrounded by air. This makes the fabrication much more difficult. So our attempt was to use silicon dioxide as a layer underneath and amorphous silicon to form the grating. This is not the optimum solution, but one we could realize. And if you look at the data of these lasers, you see the spectral purity is really great, because if you look at this mode, the polarization mode is suppressed by more than 30 dB. So this shall be fine. But the main point is that these materials have also some absorption losses. And we did this experiment only once up to now. And if you look at the parameters here, you see the currents are much higher and the output is much lower. So with this first attempt, we have one order of magnitude less power. But we have the fixed polarization, so it works. And if you look in the case of gallium arsenide, this is known also for quite some time, it's 2006, they used on top of their mirror just some additional stripes. And this also helps in stabilizing the polarization. We wanted to have this grating structure together with the mirror. So to have the ultimate thin DBR structure. This was the idea. And this is something we have to optimize, but this is possible.
Thank you very much.
You're welcome.
To my understanding, that in optical interconnects, commercial ones today, 99% or 100% of those that are using VCSELs use gallium arsenide-based VCSELs. So what is, in your opinion, what is missing in order to reach a broad commercialization of 1550 indium phosphide VCSELs?
I think it's depending on the application. And so the width or the distance you want to send your signals. I think as long as 850 is sufficient for your applications, I don't see any need why you should change to indium phosphide, because the gallium arsenide has really a lot of beneficial material parameters. Yeah, but you have to look if the data rates that can be achieved are higher on the indium phosphide side, but the values you showed for gallium arsenide we have first to achieve.
So I was thinking, for instance, about that people have been showing in talks here today that they would like to have WDM. I mean, very short distances though, but then maybe 1550 would be more useful than 850.
Yeah,
So I
but
have no problems with
this is what I
dispersion.
mean. Then here the wavelength itself, depending on your application, is the main topic. So 1550 is not possible on gallium arsenide-based materials. So from this point, I think the use of the VCSEL is application-driven.
Actually, you mentioned during your talk that one of the major problems is drift of the gain spectrum with temperature. Is there any possibility to apply some kind of gain material which can provide very broad spectrum and probably help to resolve the problem with drift of the gain? So, I mean, for example, if we can use quantum dots instead of quantum wells, would that be useful for...
Quantum dots are used based on gallium arsenide. And this is an alternative to these diluted nitrides I have shown. So if you use gallium indium nitride arsenide to achieve emission at 1.3 microns based on gallium arsenide, then quantum dots based on gallium arsenide are an alternative. They are used.
Okay, thanks.
But to have quantum dots for 1.5 emission or quantum dots based on indium phosphide, it's a completely different story.
Okay.
Mm-hmm. Is it possible to observe any modulation performance? Yeah. These experiments are done, for instance, by Connie Chang-Has-9 in Berkeley. She's doing a lot of work in this direction. And can you tell us some numbers about... Sorry, I don't have the numbers, but she can achieve really high frequencies with this. By far higher than what I've shown here, but this is injection locking then. Okay, let's thank the speaker again.
Hello everybody. Now we are continuing this day's presentations with the presentation from Matteo Cherchi from VTT in Finland. And the title of the talk will be Micrometer Scale Silicon Photonics Technologies. Matteo?
Okay, thank you, Kostas. Thank you all. I hope that you will... I have plenty of things to talk about here, so I hope there is enough time we can see what is the most important part and maybe skip some of the slides. But anyway, so I'm talking about this microscale SOI technology, which is probably not very well known to most of you because the submicron is more popular and more in the mainstream. So I will introduce the concept of this microscale SOI technology to you and compared with the kind of more common known submicron. And I will show to you our recent breakthrough, which was done within actually a project which is led by Nikos, which is this RAM Plus project, which I will talk about also a little bit during my presentation. So how we really reduce the size of the circuits in this micron-scale silicon platform. And then I will show some devices, passive devices, and their performances. Especially I will talk about these spiral waveguides, which are really something that can be done in a unique way in this platform. And I will talk about how you can filter light, which is important when you want to do some telecom application, and how you can manage the input-output coupling to these waveguides, which are the approaches. And then I will talk about hybrid integration of, let's say, for example, 3-5 elements in this platform. How can it be done? And I will also talk about a little bit about active devices that can be developed based on this platform. I will just mention a little bit about this just started European project, which is called Rapido, which is led by VTT, my institute, and by my boss, direct, Timo Alto. And then I will talk about the MPW run that we offer in our fab for fabricating these micron-scale technology devices. Okay, so let's try and start quickly. Probably most of you are used with this kind of this kind of silicon waveguides where you have sub-micron sizes in order to ensure single mode operation. You can have also some versions which are a little bit thicker where you use the rib configuration. And this helps reducing the losses and also having less polarization dependence. But anyway, usually there is a huge polarization dependence, and this kind of strip waveguide is used only for TE. So you use this kind of polarization rotation or polarization diversity approaches with these waveguides. And so the pro of this approach is that you can have very small circuits, basically, and very small devices, and you can sense very well because the field is going outside quite much of the waveguide, so you can really sense whatever is on top of it. So for sensing is very nice, but this is not the main topic for this school, which is about telecom, so the sensing part is not quite important for us. And you can have very small devices with very small volumes where you can have very fast operation, basically. The drawbacks is that this sensitivity of these interfaces, which is good for sensing, on the other hand, means that you are sensitive also to any kind of fabrication errors. So whenever you do a micro ring, and you do 3 micro rings in the same place in your mask, in your fabrication, they will never have the same resonant frequency, basically. They will be shifted by a few nanometers, or maybe a little bit less than 1 nanometer, but still, it's not possible to do identical devices. So you need to control then, for example, resonators like a micro ring must be controlled, thermally controlled, in order to pick the right operation wavelength. And on the same issue you have also with the losses, because you are sensitive very much at the edges here, where you have a lot of roughness due to the etching process. And basically this means that the losses are relatively high for a waveguide. I mean, if you compare with glass waveguides, you are really way off, because we are talking about dB per centimeters, but they are talking about less than 1 dB per meter. And clearly for having these small gaps, small sizes, you need, usually you can use various approaches like electron beam lithography, but the most common use to be scalable to production is the deep UV approach, which is not at all straightforward, because you go with features which are sub-wavelength actually, and there are tricks you have to play to get what you need. So it's not at all easy to fabricate this kind of stuff. It requires very expensive tools and very expensive process. Okay, and then clearly also couple the fiber mode to this kind of small size of modes is quite a challenge. People usually use this kind of grating approach, but they are anyway quite lossy. You can have some result which is maybe 1 out of 1,000, which is very low loss. But if you look at wafer scale, you never have losses which are below 3 dB, basically, which is quite bad if you want to have a network based on this kind of devices. And so many companies are pursuing research on the topic of these submicron waveguides, silicon waveguides, including Intel, Oracle, HP, Samsung. And there is, as far as I know, there is only one that is in the telecom market, at least, that is offering products based on these devices. And as far as I know, they are just providing a modulator and not very high integrated stuff, as far as I know. I mean, I'm not the biggest expert in this field. So as far as I know, this is the only one, and with a limited product portfolio. Instead, the micron scale silicon platform has the advantage of having a mode size which is much closer to the fiber mode size, and is perfectly, for example, compatible with lens fibers or taper fibers. And you can easily have this rib and strip waveguides. The rib is the one that ensures single mode operation. And the strip is not at all single mode in general, but you can find ways to suppress coupling to higher order modes and just to effectively have it as a single mode waveguide. And this is what I will talk about, especially when I will present the band in this platform. And you can have very low losses. You can have very low losses. As for example, the waveguides that we fabricate have this kind of level of losses, which is at least 1 order of magnitude lower than the submicron waveguides. And this is due to the fact that basically the field is very much confined inside the waveguide, so you feel much less the edges and the roughness. And actually, we have to play some tricks in our fabrication, as I will explain also afterwards. We do also some thermal oxidation to reduce the roughness. But I mean, there are also other approaches that we are pursuing at this moment. And okay, you can anyway do micron scale bands, which is it was not possible until a few years ago. Actually, we did this breakthrough 2 years ago. And you can have crossing with very low loss, just easily. Just take the right waveguide cross section. You cross the waveguides, and the losses can be very low. You don't have to play any trick, and it is very high. It's not something that is a limited bandwidth. Also, you can, if it is 0.2 dB. If it is 0.2 dB, 1550 will be 0.02 dB also 1300, for example. You don't have to design a crossing with words for all, for each wavelength range. And you can have really small polarization dependence. You can work with bulk polarization in general, unless you really need very fine control of the relative phase of the two polarization, which is the case in some kind of format which exploit polarization diversity. And you can really handle much higher powers here without seeing any nonlinear effect. Before you really reach the level of nonlinear absorption of silicon or four-way mixing or whatever, you really need a huge power here. we're talking about at least 2 order of magnitude bigger area in the mode. And you can just use very much cheaper tools, standard UV lithography and stepper lithography, and you don't need very small features here. You can really work with much cheaper tools, and much cheaper processes also. And the tolerances to fabrication errors is at least 2 order of magnitude better. So I can really tolerate what is not tolerable for the submicron waveguide. The only issue is that if I design some, for example, a directional coupler based on this edge depth, then I don't have a perfect control of edge depth. I can have variation up to, well, let's say, plus or minus 5% usually. So this means that some the devices that are based on the RIB waveguide have to be designed in such a way they are not affected by these edge depth variations. And actually, there are ways to have much better control of the edge depth, and we're working on it. And cannot make really small couplers because the RIB waveguide coupler, by definition, will be big. And if I want to couple to strip waveguides, because of a high confinement of the field, I should put them really a few tenths of nanometer distance, and this is not possible with the technology. It would require something which is challenging even for electron beam lithography. So I cannot really do a small coupler with this technology, which is a big limitation, and we will see that in some example. And clearly, the response time of a kind of electro-optic thermo-optic devices will be affected by the bigger volumes in this case, and so also energy consumption. I have to be careful not to excite high-order modes when I excite this kind of strip waveguides, which are highly multi-mode. Usually, they are micron size. So you can imagine you have plenty of modes in both direction, vertical and horizontal. Okay, so this kind of technology was pioneered since 1988 by the former Bucam technology, now Oclaro. And in my organization was started in early in 1997 by my boss, Timo Alto. And there exists some players, so basically Coutures is the main player, now is part of Mellanox, and they are really doing devices and products based on this technology. And we have also a collaboration with this MedLumis company, which is pursuing medical application based on this technology. Okay, these are 3, for example, publications you can check if you want to learn about this kind of technology at VTT. We will see details about all those stuff very soon. And so just to give a kind of a sketch of what kind of technology we use. This is the VTT process. It's not the standard process. For example, I mean, I think Couture is not using the same process, or whoever, or Bucam didn't use the same. So this is what is really done at VTT. And so we have this thick SOI. We do 2-step etch, one to define the RIB topology, and a second one to define the strip. And the nice thing that they use the same, they share the same hard mask, so they are naturally self-aligned. There is no alignment issue. And after that, we apply thermal oxidation, so we oxidize silicon, and we remove this part of oxidized silicon. So we basically enlarge the gaps and narrow down the silicon features, and we then deposit our silica cladding. So we are limited in our feature size because, first of all, our process engineer, he doesn't want to push the machine to the limit. The limit of this machine is about 380 nanometer resolution. But when you push to the limit, then the yield goes down. So you can have a region in the wafer where you can have good devices, but then you risk not to open even the mask in some other places. So just to be safe, we don't use the 380, but we stick to this 600 as a number that allows to have opening all over the mask, basically. So we are limited in resolution to the 600. We never do features smaller than this. And then we apply this thermal oxidation. So we reduce the width by 450, and we enlarge the gaps by 450. So the minimum gap we can have is about 1 micron. And the minimum, let's say, waveguide width we can have is 115 nanometer. Okay. Now I will talk about this breakthrough we did in the last years, how to reduce the size of the circuits in these big waveguides. So basically, when you have a real waveguide, the index contrast is very limited laterally, because it's just the difference of the index of the thick slab and the thin slab, basically, which is minimal. So the bending radius of real waveguides, for example, of different thicknesses, you see, if it is a 10 micron thick SOI, so the waveguide is 10 micron thick, you have 10 centimeter bending radius, and if it is 3 micron, which is the one that we mostly use, it is about 2 millimeters, assuming that you are doing 50% etching here, but clearly this depends very much on the depth of your etch. And if you go down to 1.5, you can have about 600 micron. But so still, we are talking about quite big size in the bending radius. So this limits very much the size of your devices. Usually devices have bends, and if it takes millimeters or centimeters to bend your waveguide, then the device has to stick to it, with that. So we try to find a way out. And so, again, if we talk about the submicron waveguides, they can bend very sharp corners with, for example, typical microring radii are in the order of 3 micron with negligible radiation losses. And so you have so in this platform you have these very small bands that you can have, but on the other hand you have, as I mentioned already, the challenge of a coupling, because if you compare a single mode fiber to the mode size of a silicon nanowire, it's really you see the orders of magnitude here. So what we claim, we have a platform that is much more suitable for coupling the fibers, for example, but we have this problem of size that is not at all comparable to the bending radius that you can afford in this submicron. Here the problem is that whenever I have a big core, if I want single mode, I have to basically I have to do a very low index contrast. A very low index contrast means very big bending radii. So it seems that there is really no way out here. If I want big sites, I have to accept big radii and vice versa. What if we get rid of this requirement of having single mode operation? Okay, so if I have big core, high index contrast, small bending radius, in general, what I can do a small bend, but you see that if I start with a fundamental mode, I will excite in the band higher order modes, and I will have effectively losses here. So excitation of higher order modes means that I'm anyway still coupling modes that are guided modes. Okay? So the power is still inside the waveguide. So I have an advantage compared to radiation losses. And radiation losses is power loss forever. I don't have any chance to recover that power. But maybe in this case, if I'm smart enough, I can try and get it back. Because the light is still there. It's only in the wrong mode. Yeah, in fact, already in 2003, Professor Melloni from Polytechnic of Milan proposed the concept of matched bands. It was originally actually meant to reduce coupling to leaky modes, so kind of almost radiation modes. But I mean, you can apply in every case, also when you have very high order modes waveguides. The idea is that you have to do your you have to pick up the right radius and angle to have a right length in such a way that you couple back the light to the right mode. There is kind of an oscillation. There is a beating between, let's say, usually it's just two modes you have to take care of. So the first and the second order mode, there's a beating of the two. At a certain point, there are always points where you are coupling back all the power to the fundamental mode. So if you pick up the right choice of radius and angle, then you can have the power, all the power back, basically. So basically what happens is that you have the fundamental mode of this multi-mode waveguide with zero curvature, and then you couple to an arc with a finite curvature, and back to a zero curvature waveguide. So you have these two abrupt transitions, which in general excite higher order modes. And the higher order modes, they propagate with different phase constants, and this means that sometimes they can be in phase again, and you can have the whole power back. Okay. So you see, for example, if you consider a strip silicon waveguide which is 4 micron tall and 2 micron wide and 90 degrees arc bend, you couple from a straight waveguide to another straight waveguide. This is the radius, I'm changing the radius, and this is the coupling to the different modes. So this is the fundamental mode, the first order, high order mode, etc. You see that when you are really small, bendy radii is quite a mess, and you are coupling to many modes, and there's no way to recover the power. But already here, when I have three main modes, there is a point which has a decent coupling back to the fundamental mode, but still is lossy. But if you look at this point when only the first higher order mode is playing an important role, from here on, I have many peaks where I have this matched band condition. And at a certain point, I can say is adiabatic enough not to couple too much the the higher order mode, and I can regard this as an adiabatic transition, and I don't care anymore about the matched band condition. Okay. Clearly, this is a kind of a resonant solution. It's a kind of you have to find the right ratio between the two modes, and it has a limited bandwidth, relatively limited, depending on what you are looking for. I mean, 140 nanometer for most telecom applications is quite much already. But in our application, considering the transparency region also of the silicon, which is from 1.2 micron to about 7 micron, it matters to have a broader band operation. Yeah, what I didn't mention is that our rib waveguides, by definition, and also strip waveguides, by definition, they can operate a single mode. The rib waveguide can be single mode in the whole transparency region of the silicon. It's quite a unique property. So you can have a waveguide which works fine from 1.2 micron to 7 micron the same way. This is not affordable by the sub-micron approach, where you want to have the single mode condition, so you have to shrink the waveguide and scale it according to the wavelength. Okay. Again, we have seen that the main cause of these oscillations is the fact that I'm coupling through these abrupt transitions. Zero curvature 1 over R, and then zero curvature again. But, I mean, every day we experience these kind of transitions, and how they are managed, for example, in highways or in railways, is simply you have a zero curvature, you do a track transition region where you change gradually the curvature, and you reach up to the constant curvature, and then you keep going with that constant curvature, basically. So this is quite a common trick in civil engineering, and it ensures that when you, for example, drive, you don't feel an abrupt change when you start steering. So we can try something similar, and from a mathematical point of view, there is a curve which is called Euler's spiral or Cornu spiral, which has the property that the curvature is just proportional to the length, which reads 1 over R, which is by definition the curvature, which is the derivative of the angle with the length, is proportional to the length. And this is how it looks like. So you start from zero curvature, and then you go to more and more curvature. And it has very nice properties, mathematical properties you can handle very easily. So, for example, the length of a piece of the curve is just twice as the length of the arc having the same minimum kind of final radius and the same angle. Usually, for a circle, you have that the length is r by theta. In this case, it's 2 times the final radius, because the radius is changing. So if I stop here, I took the radius here, and I have a certain angle. I do 2 times the radius times the angle, and it's the length of this. And this means that clearly, you can easily calculate that this leads to this proportion here. And the way in practice to draw this curve is using the Fresnel integral. So you can just draw x and y based on the Fresnel integrals. So based on this curve, we can draw bands this way. Simply, we start with 0 curvature, we go to a maximum curvature, so to a certain minimum bending radius, and then we go back with the same pattern, basically. So we do a mirror symmetric replica. The same clearly holds with whatever angle you want to do. And you can also have this kind of S-bands where you do the first Euler band and then a second Euler band which is point symmetric. So if we compare what happens with so this is the arc that we have seen already, and this is the Euler band. You see that immediately that is quite advantageous to have this gradual change. Sorry, I didn't introduce the concept of effective bending radius. So you have here a minimum bending radius, but you can see easily that I'm not reaching up to 2 here, but about 2.8. So the effective bending radius actually is 1.38. So whenever I have a minimum bending radius, which is a certain value, I have to multiply by 1.38 to get the effective bending radius of this U band. And in the case of a L band, the factor is 1.87. So the minimum bending radius doesn't tell me immediately what is the bending radius of my effective bending radius of my. I have to multiply by a certain constant number. Okay. So, but taking into account also this scaling factor. So here I'm plotting the effective bending radius. So really, what I have to compare with the arc. You see that I'm dropping much faster in this case, so I'm not coupling to the second order mode. And I can really get very small bands. Even if I go in the kind of adiabatic region, we are already talking in this case about, let's say, 100 micron easily with a 2 micron wide waveguide. And if we check the numbers here for the first peak, is about 15, 16, I don't know. But anyway, it's less than 20 micron. And you can also compare the spectral behavior of this Euler band. You can see that it has superior bandwidth compared to what you can have with a matched arc. So you can take, for example, a matched Euler band and see what is the, if I define the operation bandwidth with whenever I keep the coupling to the higher order mode below 20 dB. Similar, so you can really see that you really can clean up very much the spectrum. yeah, it's interesting to notice that when the wavelength is so the higher, the longer the wavelength, the better the Euler band works, as you can see easily in this graph. Just because the multimode behavior gets better and better, basically. The longer the wavelength, the less multimodal I am in the waveguide. So it is maybe a little bit counterintuitive, but so the longer the wavelength, the smaller the bands I can do. And sometimes I can have wider bandwidth of operation with smaller bands, because this oscillation become higher with higher frequency when they have a bigger band. So you see that with an effective radius of about 40 micron, this is the period. But when it's about double that, the period of this oscillation is almost doubled. So sometimes it's better to keep a small one of the smaller matched bands, basically, instead of a bigger matched bands. And interestingly, also that we were able, both theoretically and experimentally, to do what, as far as we know, is the smallest optical band ever done with low loss. It has effective radius which is 1.3 micron, and experimental losses I didn't report here, which are 0.1, less than 0.1 dB per 180 degree for both polarization. Okay. So, but so we chose this Euler spiral. First of all, because it's a nice mathematical function you can handle easily. But if you can find many papers in the literature where they show that it's not the optimal one. Every waveguide you should take a heavy numerical approach, and depending on the waveguide cross section, calculate which is the optimal transition from the zero curvature to the non-zero curvature. But this means very impractical. Is a very impractical approach, because every time you have a different waveguide, you have to take your numerical simulation and start doing all evaluation and see which is the right path, and you have to design your waveguide on a mask based on the new design. At the end, it's very nice theoretically, but in practice, it becomes quite a pain in the ass. So, the Euler band is a good trade-off between smoother transition and ease to use the design, because it's mathematically well-defined. You can always draw it easily. You just use series expansion of on the Fresnel integral, which you just use 2 or 3 terms of that sums, and it's already quite accurate. You don't need more than that. And so, in fact, you have closed form formulas that you can use, and you just put on your mask, and you fabricate it, and that's it. And you can also easily calculate what is the length of your waveguide, of your section. And can be easily and efficiently simulated by the overlap integral of tilt waveguides, which is the approach we're using the commercial software FinProp by Photon Design. It takes seconds to do this kind of simulation varying the radius, especially because in most cases you can just use a 2D model, which is perfectly matching the 3D. But also doing a 3D simulation is really fast. I can scan whatever parameter very easily. So basically, this Euler spiral is not the best ever. It's quite good. You could improve it. It's much better than the ARC, but it's still practical to use. So these are the results that are published on Optics Express. You see that these are the losses for the ultra-small band with 1.3 effective bending radius, T and TM. And basically, with most of the bands, we couldn't really measure the loss. You see that so red, green, and blue correspond to 4, 24, and 44 Euler bands. So the differences are within the experimental accuracy, and we really cannot tell what is the loss here. For sure, is below 0.02 dB per 90 degree. Okay, and as a reference, I'm putting here what happens when we use this total internal reflection mirror. I didn't talk about actually. I can go quickly back and show to you, maybe. Is basically this other approach for bending the light that we used to use before the introducing the Euler band, which is based on total internal reflection of light. So you just do at this trench at 45 degrees. Actually, you can do also different angles. But the limitation here is very nice. I mean, it's very small. You see that if you want to define a bending radius, is comparable with the waveguide size, basically. The problem is that even if you simulate this, and whatever size you do, the waveguides, you can find we measure many times different thickness, different approaches, but the losses are always 0.3 dB per 90 degrees, which means if you start to do 10 of these bands, you have already 3 dB loss. So sometimes the advantages is very easy, but you cannot really abuse it. You cannot use it too much. So it was quite a change to go from this 0.3 to less than 0.02 with a kind of similar band size. Okay. Okay. So I show you here what became possible thanks to these bands. Some of this stuff will be maybe seen in detail, more details afterwards. So let me mention again that this was done within this RAM+ project with band development, because there we have this integrated device. We want to integrate very densely, and it was quite a breakthrough and very helpful. So we did kind of these ring resonators using MMI couplers, and I will talk about this later. I will talk about also these cascade Mazender interleavers, but I mean they are very compact devices thanks to these kind of bands, and not pushing them to the smaller size in these cases, just to be safe. And this is a small part of a RAM+ chip, of a second RAM+ chip we did, and this all based on these bands everywhere. Also for active alignment of the chips to fiber arrays. Here you have loops to back reflect the light. Basically it's this kind of structure where you have 1 by 2 MMI Euler bands everywhere, and you couple back. You have a back reflector, which is based only on dielectric waveguides, not metals required. And you can do also a version which is more pushed in size. a bit is somewhat lossy, because it's using that very small band in here. These are ring resonator back reflectors, for example, similar to that one, but instead of having a loop, you have a ring resonator, so the reflection is dependent on the wavelength. So when you are at resonance, you reflect. Can be used for lasers, for example, as a back reflector for a laser. These are, for example, the very last chips that came out from the clean room a few weeks ago. They look like pictures, but they are actually real photographs. They are a little bit photoshopped, maybe too much. But anyway, they are real devices. It's not like a rendering. Okay, so let's now see what is inside these circuits, what we can afford, what we cannot afford in this platform. And okay, so we are using the strip waveguides. We are trying to use the strip waveguide, this multi-mode strip waveguide, in most of our circuits at this point. So we just have input-output the RIB waveguides, we couple single mode, and then we try to keep single mode also in the strip waveguides in the circuits. And for example, we measured the properties of our 2x2 MMIs, which are based on the strip geometry as well. It's not RIB waveguide, but it's a fully etched silicon. And in this case, they are meant to work only one polarization, which make it possible to do it smaller MMIs, because in this RAM Plus project we are basically using a single polarization, so we wanted to keep the sites as small as possible. And they are typically a length about 120 micron, and we have very low losses. The bandwidth is the standard bandwidth of an MMI, typical. And partition ratio imbalance, they are quite good. Okay. We developed also double MMIs to have any wanted splitting ratio. It's basically a kind of a Mach-Zehnder, where we have a minimum phase shift here. The minimum order phase shift is really so it's the largest bandwidth basically. You can check this paper that was in Optics Express this year. And we also showed many years ago, in 2006, this concept of, they are very long with couplers, but they're really broadband. You see, it's something that you cannot afford otherwise. For I mean, here it's just limited by the source we use. We don't know which is a real bandwidth here. If you compare with an MMI, you see that the MMI, which is known to be quite wide bandwidth, looks really bad. And so now the spiral waveguides, having developed these bands, we have tried to use it in the spiral waveguides. So sometimes there are applications where you need small footprint and long propagation distance. And for example, for delay lines, or sometimes for sensing applications. The important parameters of a spiral is the length. So I have to care about propagation loss and bending loss. Footprint has to be kept to a minimum, so the bending area should be small, and the waveguide size and the waveguide pitch also. It's important parameter. Then have a chirality. So sometimes it's needed to have a non-zero chirality, which means I have to ensure also low loss crosses, But if I don't need any chirality, then I can do this trick and kind of wrap and unwrap the spiral. Okay, so there are many advantages in different platforms. Silicon waveguides can do really very, very long spirals because they can get really amazingly low propagation losses. But the size of this spiral cannot be small. If we use the submicron high-index contrast waveguides, single mode waveguides, and then the losses are too high to have very long spiral. So where this breakthrough is really important is here, because we can have very low losses and very small bands. And so in general, people do this kind of round spiral where they change smoothly their bending radius. Instead, we are keeping the same bands every time, so we are doing this squarish kind of. So this is what we fabricated in the first attempt of doing spirals. And you can see that, for example, this is 1.5 meter long in a quite small footprint. And then, okay, we characterized them. We found out that the propagation losses also in the strip waveguides is quite low. It's anyway about this 0.1 and something dB per centimeter. But so the problem that we have seen is that, okay, when I have this kind of Euler band, if I have just one of them, I accept, I can couple, let's say, 1% of the light to the higher order mode, to a higher order mode. But if I have plenty of them cascaded, and I couple 1% in a coherent way, then I can really have huge changes, wavelength dependence of a spiral operation, basically. It's like a kind of like when you have gratings. You have a very small reflection from each section, but if you accumulate in phase main reflection, then at a certain wavelength you will have a peak of reflection. Similar in this case, you can have wavelength when you're really coupling high to a higher order mode, so you're having losses, basically. So sometimes some of the spiral had really bad spectral behavior with peaks. So you have to use very big bands, basically the adiabatic bands, in order to keep the, but now I'm going very fast through it. So we found, for example, yeah, these bands, anyway, you see that we couldn't really measure the losses of the bands. They are within the accuracy of the experiment, so we cannot really tell. So, but so we try to exploit some of the best spirals for some devices. And this is an example of a delay line which cost us measured in our labs. And so he was able to do some demodulation at this strange 7.2 gigahertz signal, because I did a mistake in the length of the spiral, basically, when I did the mask design. I didn't count some of the bands in the size, so it turned out to be longer than expected, than meant. So anyway, we are correcting this. But the good thing is that the losses are really small, and you have this about 1 centimeter propagation here, and the losses are really small. You can see from the fringes here. In the Mach-Zehnder, you have a Mach-Zehnder here. One arm has 1 centimeter longer waveguide. If you do this with a submicron waveguide, you cannot see these fringes, basically, because there you have like kind of 3 dB more losses in this section than in this section. Okay. Now we have fabricated new spirals, also trying to reduce this wavelength effect. We found some tricks. We have still to check if We also did some spiral with crossings, but in order to do that, we have to check the crossing loss. And when we did the first time, we couldn't get any better than 0.05 dB per crossing. But now in the second round, we found that with the right strip waveguides, with 6 micron wide strip waveguides, we got something about 0.016 dB per crossing. We start to be quite interesting. Okay, they tell me that I have to be very quick here, so half of the presentation will be probably lost. So I prepare many things here about filters we can do in our platform, but okay, I will skip that. And since we have just 5 minutes remaining, okay, let's go further. Okay, so just quickly, this is how we plan to couple light from single mode, 10 micron mode size to our waveguides. We just plan to have kind of a 12 micron SOI, where we have V grooves for the fibers. We couple the fibers in a V groove. We reduce the size mode till about 3 micron, and then we couple to circuits with 3 micron devices made out of our platform. And we can also think of coupling our 3 micron waveguide to the 220 nanometer SOI through the kind of inverse taper approach. And we can flip chip the 220 nanometer SOI to our platform as a board. And I mean, this was to mention that there exist also some grating couplers for this micron scale waveguides in the 1.5 micron thick waveguide. This group from Malaga University, they did this nice work. You can check it. And I just mentioned very quickly that we do this hybrid integration on our platform, so we can put 3-5 elements like laser, SOAs, whatever, SLEDs, with sub-micron accuracy. So we do it, we integrate detectors, we just pick and place at wafer scale. We have machine to do it quickly at wafer scale with passive alignment. Then this is probably still the world record in thermo-optic switch speed. 700 nanosecond was done in 2004. And this is just to mention that this 3 micron platform has also some active devices possible using silicon germanium and germanium. They've been developed by Cotura, based on Franz Kendlich, the electro-absorption modulator, and the germanium detectors, simply integrating germanium on platform. You can also have a look at the view of Cotura and Oracle in this nice Nature Photonics paper they did in 2011. So VTT is also leading this project aimed at doing interconnects for high-performance computing, for supercomputers, and is trying to revolutionize some concepts. And basically, they have been playing 5 state-of-the-art demonstrator. They use advanced modulation method, use of optical packet switching, and to prove scalability till the petabyte per second. And so these are the partners with their roles, and you can see it in the presentation when I will give to you. And so the main message is that VTT offers these MPW runs. If anyone is interested, we are going to launch, it's going to be launching these days. The deadline for kind of subscribing will be mid-June, and probably the end of June. The deadline for submitting a mask is the beginning of August. Okay, we provide design kit and support, and this is the plan for future MPWR we would like to have on our platform. Okay, so okay.
Questions, please? Yes.
Yep, thank you for your presentation. I would like to know about the bendings. So for the design of your bends, you're using this Euler spiral, right? And for the design of your bends, like how you calculate the trajectory, you're using the Euler spiral, and the losses you expect, or the bending losses you expect, you're getting out of simulations, or do you have kind of a loss model for those bending losses?
The bending losses are modal losses, basically. So it's coupling to higher order modes. It's not radiation losses. So what you see in the pictures I've shown, you're not having any loss more than the kind of roughness induced loss, basically. And so you measure the loss by looking at the level of coupling to, for example, the first order mode here. So in this case, I have a little bit more than 1% loss. Okay? And this matches really with experiments.
Yeah, okay. What I wanted to know, like, you don't have no theoretical model what exactly describes your losses, depending on the bend.
I mean, basically the loss comes from this coupling. This is the theoretical model. So the simulation tells me that I'm losing power because I'm coupling power to the to this higher order mode, and then this higher order mode, when I have the strip to rib conversion, will be radiated away, basically.
Matteo is doing his simulation with FIMPROB, so
yeah,
he can extract this kind of figures from that software. Other questions? Yes.
I have a question to the fabrication process. I didn't quite understand. Why are you thermally oxidizing? So you're getting silicon dioxide, then you're stripping the silicon dioxide, but putting silicon dioxide again afterwards.
Because by thermal oxidizing, you reduce if you do with 200 nanometer, 200 and something nanometer, you can really reduce by 1 order of magnitude the roughness. So your loss is from 1 dB per centimeter pass to 0.1 dB per centimeter. So it's quite an advantage. There are other techniques to reduce the roughness, which are not affecting the line width, but we are exploring a little bit also those. But at this point, this is the most effective way we have found to reduce the impact of fabrication roughness on the waveguide loss.
And why not just keeping then the thermally oxidized part?
If we don't do the thermal oxidation, then the roughness is high.
Exactly. So you do the thermal oxidation, yeah, but then why are you stripping the?
Because the thermal oxide is very stressful. It induces too much stress. You cannot leave it there. So you change the properties of your waveguides. There's also the Barry fringes and whatever. So if you do a strip, sometimes it's risky. You can break your strip just because of the stress that is induced by the thermal oxide.
Do you have any idea of how much stress you're talking about? Numbers?
No, I don't have numbers. We know in practice that you can break stuff. Even the rib waveguides can break sometimes. Or you can peel off the SOI layer from the box.
Excuse me, I not fully understand the two devices. One is that you make a reflector with 1 × 2 MMI together with your spiral band. But why not you use just use your spiral band?
Sorry, could you please repeat your question?
In your presentation, that you mentioned a reflector. You put 1 times 2 MMI, and also a spiral band after that.
Oh, he's meaning the Ramplas chip, where you put in the reflector for the active alignment.
You mean this active alignment feature? This one?
Yeah. Why not just use Euler S band immediately?
In that case, you will need an external circulator.
Yeah, but if you just use a band, then it can also give you reflector, right?
No, sorry. What would you like? Are you proposing instead of using?
Yeah, I don't know what's the necessity that you put a MMI in front. I mean, if you just use the band, then it can also play a role as a reflector.
I want to go from. I have a single waveguide. I want to have a reflection from that waveguide.
Okay.
Because basically you have a fiber array.
Mm-hmm.
You want to align the fiber array. Usually you can do a loop between the two outermost waveguides of the fiber array. But in this case we cannot, because we will intersect, because we have 2 fiber arrays, one side, one the other side.
Okay.
So we will have intersect all the other waveguides in order to have a loop.
Yeah.
So we have to have a local loop in that very waveguide, the outermost fiber, to see if it is aligned with the waveguide.
Okay. And another question is, according to my knowledge, I cannot understand why the power fraction, the curve always looks like oscillations. That it means when you change the radius of your band, that the fundamental mode coupled to other modes, and also it has lost radiations.
No, because it's very well confined. In this case, you have a much wider waveguide, so you don't have radiation losses. They are not leaky modes at all. They are all guided modes.
Okay, but why the curve looks like damping?
Because of the beating of the. If you think you have a coupling to one mode, like when you have a directional coupler, you have the beating of the super mode, and
okay,
it's the same concept.
Okay, thanks.
Any other questions?
Is all that stuff that I wrote at the beginning, the advantages. So, as I mentioned, if you do a micro ring, you do 3 micro rings which are supposed to be identical. They are not identical. In this case, we can have, so you have to tune them with some heater or some electro-optic approach. In this case, we did, for example, this, I didn't have time to show, but we did this cascade of Matzender interleavers. We did, 3 stages, 3 filters, and they were perfectly aligned. We don't need to heat anything. If we did the same, now submicron approach, we would have to heat them in order to align all stages to each other. So here we have really a tolerant, very much tolerant, so the yield on wafer and whatever is much better. So you don't care about the footprint that you increase? But now we have shown that also the footprint can be kind of shrink. It's not the same, but still it's quite a big improvement. But the idea that you shown for the bands could be used for a small waveguide. Sure. It doesn't give this huge improvement clearly because you have already there some. But if you want to do a racetrack resonator, for example, you can use the same concept. And the other part is the coupling. Coupling to a small waveguide, as I've shown, is quite difficult. If you use the grating, even the best grating, that maybe they have reported 1 dB, let's say, which is 1 all over the wafer, because the other are 2 dB. And anyway, let's assume that it's 1 dB, but it's over a 30 nanometer bandwidth. When you try to enlarge the bandwidth to 100, then the loss becomes 6. In our case, we can have much lower than 1 dB overall losses in coupling all over the bandwidth of so if you in principle, if you have some special fiber that can couple also kind of mid-infrared, we can couple that as well as we can couple that 1300 or 1550, whatever. It's the same approach. We don't have to design anything.
And also it's very convenient for flip chip bonding of actives. So you don't have to overgrowth 3/5 like the approach of Sealeti or other groups. So you can take the bare die, the bare SOA or laser, just you can test it before and then flip chip bond it on the micrometer scale, and you have 100% yield.
And also the propagation losses are quite, you see that sometimes you cannot do this long spiral when the losses are too high.
And one last question from me. Any plans for AWGs?
Yes, there was some slide about AWGs. We did already some AWGs in the past. They were huge. We did this in this MPW run. We did some AWG which are small, but we don't have any data yet. But anyway, this is the layout of the AWG we did. So they are quite compact now. In the past, we used to have this. For example, this is 2 centimeter by 2 centimeter, and but it was a ESA project for doing some transmitter receiver for them. But now we are pushing much smaller stuff. We don't have any characterization yet of this, but it's all based on this new band concept.
So, yes.
I hope your presentation were included in the...
Yeah, it will. Sorry, I just finished 10 minutes before lunch. So yeah, I will give to. I mean, they have it now, so they can share it basically. Okay.
Okay. So let's send Mike again.
Okay. Now, our next talk will be from Ronald Broeke from Photonics. And Darius Bucket's talk. And the title will be Designing Photonic Chips. So it will be more about masks and how we should design a component in silicon.
Everything.
Everything. So how we can design components. Okay.
Yes, that use Windows computers. If you want AWGs in 50T, we made one the last run as well. Is there a clock here? No, so I have to use my phone as clock. First one is Phoenix, and then later I start or maybe you can open it already. I don't know here. Which one you will start? I will start with Phoenix. It's a PDF. Oh, for the statistic, yeah. Okay, good afternoon. I'm Ronald. First of all, I would like to thank for the invitation and the very smooth and welcoming organization here for the last few days. I have to say that I did several winters in the Netherlands without a coat, but I got sick in Thessaloniki, so I didn't expect that part. But no, go back. This is the presentation of Phoenix. I will present on behalf of Arjan Bakker. And Phoenix makes software tools. And actually, I saw during the poster presentations that most of you actually are already experts in any kind of photonic circuit design.
So I hope I can add something. But actually I saw many people used also Phoenix tools. So the main focus of this talk is why we would need a design integration, and I think for some people this is new. I will have a second talk for Bright Photonics, and that will show in extension to Phoenix that you can add modules, and that will save you time in designing. So it will not tell you anything new on the gory details of components, but in the way of working basically. So first, introducing Phoenix. Phoenix supports customers all over the world, and they want to enhance research output and improve the quality of research, and you can do that by having stable design environments. So they offer an integrated set of tools like mask layout, process flow, and also a simulation environment, and you can also keep track in a database of your processing in clean rooms, and the data coming from chips you can integrate again the things you measure into your design tools. They have process design kits for most fabs, and it will come later in the presentation. And they have a lot of training courses, and as I will explain, if you have generic technologies and generic design platforms, you can also train people at the same time, so it becomes all more efficient if you do it in generic approaches. Phoenix is founded in 2003. And the team dates back to 1991. They had BBV, maybe people, old people in the room may still know that. And they serve more than 180 customers for different kind of companies, small companies to very big ones in the Fortune 500. And their, well, basically their focus is long-term stable cooperations. So you won't see them disappear next year. They've been in the business for 20 years, and they're in more than 10 European projects. And I think actually the majority of people in this room must be some way a project partner of Phoenix. So what are the kind of products Phoenix has? Field Designer, Opto Designer, that is for cross-sectional simulations, Opto Designer for kind of BPM simulations. ASPIC is from a company in Italy, but Phoenix also supports that, is doing circuit simulation design. Mask Engineer is to make mask layouts. Clearwin for looking at your GDS file, and Flow Designer, you can simulate your flow in a factory or in a clean room, and you can see if anything strange happens by seeing cross-sectional sections based on design flow parameters. So you can see if there's cavities in your flow, and you slowly do all your process step by simulation. Process design kits, I will show later in this simulation. Manage your clean room, that's another product. So if you have a clean room, you have to keep track of your wafers and the batches, etc., and there's a database system for that. Main topic, photonic integration, so that's the introduction of Phoenix. The tools can handle various type of technologies, silicon insulator, 3-5 materials, triplex, and similar to triplex, polymers. And these kind of materials are now finding their way into all kind of markets. Some for Foxtrot is about optical interconnects, and that may be a very big market if all this research that we saw last days like PCB will work. And there are smaller markets starting now. For instance, there's a lot of small sensing companies, and sensing as a whole may be a big market, but you see a lot of small companies in all kinds of niche markets, so that's completely different kind of dynamics. And microwave photonics for things like antennas. Short explanation, but I think, as I said, there's already a lot of experts in the room. Integrated photonics is based on building blocks, if you do it the generic way. And actually what we try to avoid in the generic way is the very legitimate questions we got in the last presentation, because it's about technology. And in generic, we want to have solved the technology questions already, about stress, etc. You can basically plug and play in the ideal case, based on pre-tested building blocks, to be faster and to be working more towards production and reliability. So in electronics you have resistors, you have, I think even I have a thing that, yes, light, yes. We have resistors, capacitors, and amplifiers, and in optics we have waveguides, phase shifters, amplifiers and polarization control roughly, and you can play with them to make bigger circuits like this. You can make MI couplers, etc., etc. We saw in the last presentations already beautiful examples of all these devices. If you have an amplifier, you can make all the kind of thing. One of the more important ones would be multi-wavelength laser for WDM systems, for example. And ring lasers are pretty often used for all kind of interesting applications as well. Phase modulators, you can do phase shifting, data modulation. So with all kind of different combinations, you can make all kind of different chips. And these are examples from the JePPIX project, FP7 project, which ran between 2009 and 2012. And this project was to demonstrate the feasibility of the generic approach in indium phosphide. So this is what you can do with all those building blocks. More explicit examples, in this case indium phosphide. And this is a chip designed by Katarzyna Lawniczuk, who will do the next presentation actually, so she knows more about this chip than I do. But the important part here is that in the design environment, you see on the left side, it's a subassembly of an indium phosphide chip, of a fiber array head, of a daughter board for electrical packaging, and all those parts of all those different chips can be embedded in the same program, can be used in the same design environment. So in the Phoenix tool, in this case, you would have here the packaging fab would be the CRP in this case, would implement how the lines are running. The designer knows exactly where to connect. They can make their own circuit design in indium phosphide in this case. So you don't have a situation that when you combine the different things that suddenly someone made a mistake. You have the whole thing at once in one design environment. Another example in triplex, this is an optical beam forming network for antennas. Made in the Lawniczuk fab cooperation with UoTwente, Mesa Plus and Satrax, and this system can be used for antennas in airplanes or in boats. Whenever your antenna is moving, you can actively steer with this kind of devices. Another example of mass design in silicon on insulator. This is a research project from TU Eindhoven, and they published some papers on this as well. It's not included here. This is an example of a chip on IMEC, so all done in the same design environment. So photonics IC design is not the same as CMOS design in electronics, and there's several reasons for that. Because the number of wafers you process in photonics is not even remotely comparable to the number of wafers you process in electronics. So less than 1% of the wafers is for photonics. Typical line width sizes are way bigger in photonics, 0.2, 0.3 micrometer. The tolerances are too high for photonics. If you have electronics and your metal line is a little smaller or wider, it doesn't matter, but in photonics that can be disastrous for phase conditions, for example, or loss roughness, so a completely different way of looking at your process. Few components per chip, and it's more analog behavior than digital behavior in photonics. And in the bottom, an example of a product in Silicon Photonics of a AWG. Another example why CMOS is not photonics or photonics is not CMOS is it's more analog. It's actually basically the last point from before. Here you can see a design. It's not like digital and straight. It's very smooth and organic. So you need specialized simulation tools. You cannot just use a electronics tool and try drawing an optical circuit. For example, if you would use an electronics tool, they would not be able to draw an accurate bend. You will not get the right discretization. And those sound like very trivial things, but if you start designing in the wrong tool, you will end up with a lot of those trivial things and actually be designing your own design tool, and it will take several years, of course. So you have to be aware that photonics is a different ball game in a design environment. So in photonics, you need to accurately and also flexibly be able to design your shapes. So for example, all those bands. You need the connectivity and smart routing. A lot of the work in photonics is always in routing of your chip. In electronics, it's all automated, but in photonics, it's a little harder because it's not Manhattan type structures. So chip fabrication, what is needed? So how can you make the chip, and which process do you need between the designer and the fab? The fab is the guy on the right, or the girl, I don't know, I cannot see from this picture. And they want to have a compatible, manufacturable design. They want to have a GDS file compatible, they put it in the machine, and there's a chip coming out. The designer doesn't want to see all the technology, they just want to see functionality and make their design with that functionality. So you need some kind of interfacing, and here's an example. You can make a library of building blocks, and that can be an MMI, for example, or straight waveguide. And the designer uses the library, and the fab makes the library. That's not the whole story, because you would have to do circuit simulation. The designer has to generate a mask layout. He may have to do some physical simulations, because he wants to use a different kind of waveguide. And that has to be sent again to the fab, the mask layout. And all those tools have to talk with each other. Now, in the end, you have a design, you send it to the fab fabricates the chip. The chip is measured, so you get data back. And the data can be fed back into your library. And the next time you know better how your circuit will perform. Only if you have no good management of this whole process flow, then it may get complicated, as the title indeed says. Because you have to keep track of all kind of versions, different wafers, so it becomes a little messy, and it's hard to get very stable designs this way. So you would have to embed it in some kind of design environment. So what would the design environment look like? You can use process design kits, PDKs. And the reason to use PDKs, to stabilize all the different arrows in all the different design parts as in this picture, the reason is that the chip development is becoming very expensive if it isn't right the first time. If you do research, you always have to do different tries and things go wrong, but that's because it's research. What this aims at, although you can use this for research as well, but the next step is, what we're doing right now is to use it as prototyping. So the software, and people using the software and using the multi-project wafer fabs, they don't want to waste money in a lot of different runs. So you have to get it right the first time in the multi-project wafer ecosystem. And in that case, designing and testing become the main cost. So in a design environment where you can design faster, actually, that's where you get the cost reduction, because ideally you only have to run one wafer run. So for design kits, the advantage would be cost sharing, and this is actually the way it should not be. I will explain it in the next slide. So if you standardize, you can also standardize training, so things become more efficient, and you can design together because everybody's talking about in the same way about the same technology because it's been standardized. So what you don't want is that all the designers talk one-on-one with the fab, because then the fab will not do any manufacturing anymore. They're only answering all the emails of the designers. So this is a situation to avoid. And there again, you have the design kits and a broker. In the next presentation of JePPIX, we'll explain what is a broker. So the foundry will make sure that the process is stable. They provide a design kit, and the design kit can be shared by all the designers. Also, if designers have something to report, they can do that in another way. The fab will improve the design kit, and all the knowledge is being shared. And it makes sense to put way more effort in building blocks now, because building blocks get reused. If you only use it once, it doesn't make sense to put a lot of time and money in it. But if you reuse it, you can actually add years of effort into a building block, because it gets used for years as well. And let's say the real connection is here always the PDK or design kit with the building blocks. So this concludes this part of the talk. The chip development is not affordable when you don't do it first time right. So you need a good environment from which you know what elements you use in your design. Large-scale photonic chip is difficult without automated PDK. So 20 years ago, there was research on one MMI or one AWG, but nowadays you get very complex chips, and I will show some of them as well. And a smart designer may be able to keep track of all the details, but he also makes a mistake, and you don't want to have it depending on someone being able to remember all the details. You want to have automation that will do that for you as far as possible to avoid mistakes, because in the end mistakes will cost money or time. So it's essential to use these systems nowadays, and it simplifies your design and your work as well. So that's definitely some advantages. And something important, training and support are crucial for new designers. And what you see, there's a lot of different trainings right now. So instead of a university group, for example, having to train, everybody has to train his own people, you can now send them to generic training, and they get some idea already. You can still train them as much as you like, of course, but it's definitely an advantage to be able also to combine trainings. What does a PDK actually look like? Inside the PDK is a building block, but a building block has different, let's say, views. So there has to be layout information of the building block and process, which kind of GDS files are used in the building block. There have to be design rules, verification rules. There can be measurement data, ideally, if you had a lot of processing, so you know what the loss, what the tolerances are of your building block, and the way that affects your design and your performance of your circuits. You need models, simulation models, for example, for lasers. How will they behave with different signals in there, different injection currents. You need to add all the simulation settings, and you need IP information, because if you go to VTT, for example, and they have a nice Euler band as we saw, it's probably IP'd, and you have to know if you can use this block, or it has to be licensed, and you have to pay for this block. So a library is more than just the technical information. It can also contain the conditions by which you can use this block in your design. You need not only the technical design of your chip, because in the end you want to package it, because not everybody has a measurement setup. Usually university has one in the lab, but typical company doesn't have one, an optical setup. So you need to be compatible with your packaging. So the design environment will also provide you with packaging standards for packaging companies, and it makes sure that if you have a chip in the end from the fab, it can be packaged also in a generic way, and it doesn't cost you thousands and thousands of euros, because it has to be completely custom. So this information has to be in a PDK. So then we have the similar situation as before, but it's way more organized. So the design kit is the center. So there's the different views of building blocks. So there may be, for example, an MMI here, or an MZI, and these building blocks have different views. So you can look up different kinds of information for the block. It has a circuit description, it has a layout description, and in the end the designer interacts with that design kit, which is just more than just layout. And you can send your mask to the foundry, and the design kit also makes sure that it's compatible with the fab, GDS compatible. So you don't have bouncing up and down between designer and fab, because the critical dimensions were wrong, or the angles of your GDS were wrong. These kind of things are typically solved after a few runs in the design kit. Also important for design kits is that if you have different software companies, which of course, or providers of building blocks, which of course there are more than one out there. This doesn't have to be per se a company. For example, TU Eindhoven develops a lot of building blocks themselves, and they may decide to let others use it on whatever conditions they decide. But they have to be compatible with all the software. So the PDA Flow Foundation has been launched, and this is there to make sure that there's an open standard. So all vendors can actually exchange building blocks. So if you are a designer, you have several tools, you don't have to redesign your building block from scratch in a new tool. You can export it and import it again, and that should go smoothly. This is something not 100% in place yet. But it is definitely the long-term goal as well, to make it very compatible between vendors and tools. Write once, used by many, I guess that's the slogan for it. And in the end, you get a lot of collaboration to extend the design kit. So for the end user, you get simply more power out of the same tool, and more building blocks. So standardization means you need some kind of layer in the middle. So you have all the fabs with all their design kits here, Foundry 1, 2, 3, 4, 5, or for example, design house or university group or a packaging company, and they all have their information, and there's a software layer in between, an API, application programmable interface, and that can access in all the tools, different tools, circuit simulator, this photon design, this is Phoenix, this is another tool. So they can all talk with each other through a abstraction layer. And another way to look at it is there's the center is the PDA flow API, and here are the different tools of the different vendors. And to extend it even further in the future, because there's also something like electronics, there's an interaction with open access, which is a big organization making standards, defining standards for electronic design flow. So this is quite huge compared to what we do in photonics, and of course already longer around. So the PDA flow foundation is also making sure that what we do now is at least aligned with what is being done in electronics. So in the future it becomes easier to connect those two worlds together, and then you can make a full integrated electronics and photonics design. So that collaboration is with SI2. They use open access for that. I'm not sure how many people know open access here. Anybody? Close it. Does anybody know open access here? I'm just wondering. Nobody does electronics, so. But this, so we have to be compatible. Want to be compatible with the electronics design flow. There's several PDKs available, many actually on silicon, IMEC, CA Leti, VTT, HIP. There was OPSIS, but they stopped services as they mailed last week. InP phosphide, you have IDG, Claro, Smart Photonics, TU Eindhoven, Triplex, there's Lawniczuk kits, and for packaging kits there's Kuchen Hausco, Xio Photonics, Linkra, so there's already many options. And this is also the advantage of having one environment, because all those different fabs, all those different packaging now are combined in one environment, and also supported by different software vendors. So what is the present status of the PDK? This is an example slide of Leti. So in the beginning your PDK will just do some basic testing. Later you get some, they call it average test vehicle, so this is the complexity of your design, and this is the technology maturity. So for example, Leti is close to getting a design kit compatible to demonstrators, and the next step would be for commercialization, and then you have to focus on yield and reliability. That's not where it is now, that's where photonics is moving. This is the status for design kits for different fabs, and these are different vendors. What did they implement? So across means they have an implementation of this fab in their tool. So in summary, the PDKs lower the access barriers for making design, and they decrease the costs. They simplify your design, and they save time, and they're available now for all the relevant fabs. And to make this more powerful in the future, there's the work on standardization also towards electronics. So I guess I can answer questions if there are any for this part of the presentation.
Any questions?
This is more or less the second part, but more focused on photonic circuits themselves. It's also called designing photonic circuits. Small outline, introduction of what is bright photonics, then some examples of PIX and MPW, and I think you saw a lot already, so we can go fast, but it gives an idea, and I will put some more detail on what we haven't seen. Then some technology comparisons between silicon and indium phosphide, at least the concept behind it, and why that can be quite difficult. Then which kind of building blocks should you use and how can you extend them when you need more, and then some slides with design examples. So first introduction. Bright Photonics is a fabless design house. We have been designing for over 20 multi-project wafers, more than 100 circuits, and more than 15 years experience in this kind of work. We also provide design modules, so we have more than 100 modules installed with users, and we are involved in several projects, but they will come back in the next slides. What kind of things do we do or make? We help research group or customers or universities to turn an idea into a prototype or in a chip when they don't need a package. And the chip here is an example of a sensor which can make attometer resolution wavelength measurements, so it's extremely accurate. First thing what we would do is see if what you want to do is actually feasible in integrated photonics. And typically feasible also means that if you would have to hire your own fab for a year, then it's too expensive, then it becomes research. That's what most of you guys do, but there's someone with a very big bag of money behind you somewhere, which you don't always see. And if you want to make your own chip, then this is a very important part of the equation. Materials we work with are basically all the materials around which you have seen in the past days. We make building block extensions, and I show more in the other slides. Examples are MMIs and AWGs. These devices by itself are not per se new, but it may take you a lot of time to make a reliable design or change whatever the fab had, and in this case I will show how you can do that actually much faster and still in a reliable way. This is just a short overview picture from design to mask layout to packaging, and these are typical. These are type of designs we have been making. So we are partner or sponsor in projects. For example, JePPIX. JePPIX was programmed to demonstrate that the generic approach is possible in the first place. Well, it was possible, so there was a second project called Paradigm, which I think more than one in the room have been using facilities of Paradigm, getting wafers from there. And it's developing the full infrastructure for MPW for indium phosphide. And there's the Foxtrot project, on which this summer school is based, and it wants to demonstrate next generation data center and high-speed computing platforms. And of course, part of Foxtrot is all the different kind of technologies which you can use in the demonstrators. There's Dutch projects we're involved in, IPC Photonica, Memphis, and STW. So after 5 years after the start of JePPIX, the foundry model seems to work pretty well technology-wise. Chips are working, and they're working very well, state-of-the-art chips. So it's becomes more and more time to spread the message that everybody who has an idea or wants to make a chip, they can now get it. The environment is ready, it has been tested. And that's the reason why we participate in a lot of conferences. The next one is next week in the Netherlands. And we're also active in papers also for the same thing, to show what is possible. And people don't need their own fab anymore and can basically get the same access to the same technology and knowledge. This is some kind of mind map. So photonic circuits are now can be found in more and more applications. So before it was always telecom. It was quite expensive. You could not do that much with chips, well, amplifiers and receivers and transmitters. But nowadays you can combine them with all the building blocks in a whole range of different applications, from antennas, medical. For example, if you would have a laser which generates a whole spectrum, you could put it on your skin. If you can make it in the pen size, it can read out your skin and you can get the right cream for your skin. So this kind of applications are not there yet, but it may be the kind of applications actually that are mass production. All optical cable is of course one of the type of applications. You can find a circuit, photonic integrated circuit. These are examples of chips with the variety of applications. There's optical switching for these chips, fiber to the home chips. There's fiber sensor readout chips. There's optical RF generator, terahertz generator actually. There's the QAM receiver. There is a laser modulator. I think I saw this one on a poster as well last week or 2 days ago. There is beamformers. There is steerable beams here. So there's an enormous amount of different variations you can make, and it's all on the same platform. That is the power of the generic approach. And as most of you know, the things inside those PICs are the building blocks. This is an example from the Cobra platform. And the basic blocks are an amplifier, the shallow edge waveguide, there, the deep edge waveguide for higher contrast, phase modulators, there, some polarization controller is in the research stage, and you can have all kind of gratings and mirrors. So these are the high level type of building blocks. In practice there are way more building blocks, of course. For interconnects you can have waveguide bands, you can have all kind of different bands, you can have tapers, you can have all kind of different tapers, crossings, power splitters and so forth. Mirrors, so you have, well, this is just a very small selection, so you can have many building blocks, and each fab has different subsets of these building blocks typically with different specifications. And there are also the electrical building blocks, because you need to contact your phase shifters, for example, with DC or RF lines. You need to cross your electronic lines with the optics. And something we saw last day many times, not so much used in integrated optics, I would say, is the TSV, to have holes through substrates, and bond pad kind of thing. So there are many different kind of building blocks. We'll come back to that in the next slide. What is the implication of that? But to go to that those building blocks are used in the generic fab. So we now can consider the technology, the budget, time, and do we need to have volume ramp up? And then you get some answers to realize this, which is you need a generic process, you need to do the cost sharing, you need to design automation, as in the last presentation from the Phoenix. You need to connect with packaging, and they have the terminology MPW. So what is MPW? I would say, strictly speaking, it's only the wafer, it's a multi-project wafer. But in practice, you can consider it the whole flow sometimes, including the design automation, including the generic packaging. So MPW for me would be the whole thing. Although, and again, strictly speaking, it's the fab which generates the wafer. How do we get the cost reduction in an MPW? If you would make, this is the price per square millimeter, and this is the number of square millimeters you produce. If you make one device of 1 square millimeter and you need to build your fab, then it will cost you €500 million. So that's not very practical. If you have a big fab, you need to have very high volumes, and then the price per millimeter goes down. But then you need a very big fab. So for most of us, that is not an option. But if you share real estate on that big fab, so the big fab is still making 10 million square millimeters, but we only, for ourselves, we use a little bit of it, and the rest is used by other users. And then you can share the process development. It's the same thing. The more millimeters you make, the lower the cost per millimeters. And in the end of MPWs, you only get one part. So this is the fab. You share the process development. Then you share the small space on the wafer. And this is an example of a PIC. So you only, photonic integrated circuit, you only have 20 square millimeters. So you only pay for 20 square millimeters based on a 10 million square millimeter process. This is an example for an indium phosphide chip. And these are the samples, so there's some copies. So you get more than one sample. So you have to, nowadays there's a luxury position, I would say. Before, it was already luxurious when you had a fab in your university. And, well, that still is luxury, I guess. But nowadays, you can even go to all kind of different fabs. But the problem is you would have to choose between different fabs. You have to choose between the technology, which one is best. And each technology has its advantages and disadvantages. So many times, like now, you see this kind of slides, like indium phosphide is not so good in loss, very good in lasers. Silicon cannot make lasers, or soy triplex cannot have lasers. So if you need a laser, you're down to indium phosphide or hybrid. Of course, modulators, now you can have for all components this kind of tables. Footprints, chip costs, compatibility, packaging, so you can include a lot of things. In practice, these tables are nice, high level, but they don't really help you making a decision, because it all comes down to the details of the building blocks. So you may have a modulator, but this doesn't state which wavelength or which polarization, and that's maybe something very important for you. Or the passive components, there may be some kind of crosstalk effect, and that may be the most important thing for your design. So in the end, it comes down to all this kind of details, and then the situation becomes actually rather complex in the sense of making an educated choice, because we have all the different applications. So you may have a certain application, you want to go to an MPW. Okay, you need a laser, let's keep it easy, so you only can go to indium phosphide. Then there's several fabs, so you can go to a certain fab for indium phosphide. They may have several processes to choose between. Each process may have different kind of waveguides, for example, high contrast, low contrast waveguides, and you can use them both for similar building blocks. And in the end, you have the actual building block with specific specs for the number of channels or the channel spacing. So if you would extend this plot in all the building blocks, you get still thousands of building blocks, like of hundreds, at least very many. So it's still very hard to make a good choice based on all the low-level details. And that is also part of the story which I want to show now, because the fabs may not have all the building blocks that you need. So this is represents your photonic integrated circuit, and if you have to design it, you have to fill it with all the building blocks and all the functionality. So you can start without thinking about a fab. You need an amplifier, I need a power splitter, I need a filter, so you can add all the building blocks, and then you can try to find which is the technology which fits best to my chip. Apart from considerations like when is a multi-project wafer running and what are the costs, but let's restrict to technology and specifications here. So you have a PDK, process design kit for that fab, so you fill it up with the building blocks you can find. And if you can find a building block from the fab, then use it, I would say, because they have been tested. Typically, they're guaranteed by the fab. Ideally, and they're ready to use. It's just a solid, established building block. However, you may not find all the building blocks. As I said, for example, there's an MMI on the official fab PDK list, but it's not spec'd for TE explicitly or TM explicitly, and depending on the fab, that may be different geometry. Or AWGs, no fab will offer you an AWG as standard, because there's too many variables there, so it's very hard to guarantee it technology-wise. And a fab typically not yet, that may change. They don't offer, these are combined building blocks. For example, MZIs, you can have an MMI, but they may offer a complete modulator, or they may offer a complete multi-wavelength laser, and they are not offered yet. But they may still be available, but not from the fab at this point. So you have to make now let's assume for now you have to make a new building block. So you design your building block, and I think many of you design building blocks. So you may recognize the feeling. So, well, you make something. In this case, the building block is in the black box. So you're not sure what you have yet because you have never tested it. You're not sure if all the indices were right. So it feels all good, but it feels a little strange. So you don't have enough feedback to be sure that everything is correct. And when you would open the box, it's not that nice rabbit, but it's a furry spider, and most people don't like spiders. So it's probably not a good situation. So you want to avoid this kind of surprises because a mistake costs money. You lose characterization time because you may already have fabricated it. It doesn't work, so you may lose a lot of time there. You may have to wait another half year for the multi-project wafer. You have to redesign with personnel. You may have to buy software licenses again. And of course you have to pay for the new multi-project wafer. So by avoiding, to avoid surprises, first thing you would have to do is use the fab building block. They are typically the most secure ones. Then you can use PDK extensions. I will show in the next slide. Then you can use design libraries. I will show in next slides. Or you can design from scratch. You can always design from scratch, but if you want to have the most reliable output, it may not be the smartest thing. If you want to learn it, design from scratch. But if you are in a hurry and you have no time to waste and you just want to have first time right as much as possible, then this is not the best solution. And as said in the Phoenix presentation, the designs become more and more advanced. So you would have to probably design a lot of details from scratch. You get confused, and there's just too many details to keep track of. PDKs. Actually, it's repetition, so I can skip here. So back to the elements of your photonic integrated circuit design. So this is what your photonic integrated circuit. The black square has to be filled with functionality. So there's building blocks missing. Now there can be, for example, in the case of Bright Photonics, we have also designed blocks because you make a lot of chips. We test the chips, and we may have building blocks the fab doesn't have, and we can also put that in a PDK extension, let's say. So you can load the PDK of the fab in the tool, and you can also load the PDK from Bright Photonics, or if you have a design group, you may have developed your own building blocks, and you load your own PDK. So it's very flexible. You can load not only one PDK from the fab, but several PDKs with all the functionality you may need. So that may give you some extra functionality you need for your design. I would say the PDK extension is GDS based and can be tested, so that feels like still secure. Actually, when it is also possible, like in electronics, that designers, or if you worked a lot with a building block in your group, that you know more than the fab about this building blocks. So it can be that an extension for you is actually more secure than the fab building block, because you look at specific specs. But if they're not available either, you would have to design, and then there's the option for design modules. And design modules have all the fab information in there, but they're highly parameterized, so you calculate the building blocks. So it's a new building block, but all the rules and logic have been tested before, and the last one is from scratch. And in this case, luckily, we don't need any building block from scratch. So there is different advantages and disadvantages, of course. If you take the PK from the fab, it's not flexible because it's just a fixed building blocks, at least not flexible if it doesn't do what you want. If it does, then you're done. It's very fast and very reliable. PDK from your own group or design house would be slightly more flexible because you can ask to change. For a fab, that would be slightly different because they're bigger, having to deal with a lot of designers, as showed in the Phoenix presentation. So the more you go down 1, 2, 3, 4, the harder it gets. More flexibility, but less reliable. So this summarizes some advantages of those building blocks, but let's go to more examples. So these are, let's say, real chips that have been designed and manufactured, and this shows the kind of building blocks that may not be offered by the fab, but you may need in your design. So this design shows several building blocks. Let's go to this one. This is a DBR laser. The fab may offer a gain section, but not all the mirrors attached to it. So you would have to design all the lengths of the mirrors, lengths of the laser. Well, there could be a building block tested with all the details and isolation sections already, and you can put it in. This may not be available in the fab, may be available, but it could also be available from design house or another group. Diode array, and a design house, a fab may offer you a single diode, but you would have to draw all the things. And there's design libraries which you just specify, I want to have 20, I want to have this pitch, and it will automatically draw the whole thing for you. So instead of working days or weeks, it's a matter of a few minutes, and you get this whole layout. There is delay lines, like here the spirals, so you just specify delay in time or in length or in free spectral range. MMIs, ribbons, these are the interconnects. Interconnects tend to be very labor intensive in reality when making a design. So in this case, these interconnects are based on all kind of rules. So you can say connect from here to here and with this kind of bend, and then you get quite nice looking interconnects. Same for the metal lines, so it doesn't become a messy spaghetti-like structure. It becomes very well organized geometry. AWG, very important one, because that's a hard one to do. You can find all the papers, but there's a lot of work to get one correct, and there's a lot of variations, bond pads, etc. Just a very short overview. So there can be all kind of different design modules for AWGs, MMIs, diode arrays, etc. I will show some more details on MMIs and AWGs. So how does it in functionality work? Let's say in the case of Bright Photonics, we implemented the modules in the Phoenix software. So the green part would be the Phoenix software, and then you load this module. What you do next, the red line means you select this fab. This could be, for example, IMEC fab. And then inside the module, it has all the information of the fab, the technology, the material properties. So it will design the AWG. You can say, give me a logical AWG design, and you get the correct AWG. If you would say, now select fab 2, could be VTT as well. I think we had some designs on run 1 for AWGs. It would just, as a matter of seconds, you would get a VTT AWG. And you can also say simulate or export it to the circuit simulator. So this is the basic functionality of the building block. All the logic for this particular component, AWG in this case, is inside the library. These are examples for the fabs that are included in those design libraries. So all the multi-project waiver fabs, and also in projects there's more fabs supported, but they're not open, available in the software. But it's easily extendable. So in practice it looks like this. You define the AWG with optical specs, wavelength, channel spacing, FSR, etc. You put it in the module and you get all the different designs. So here for IMEC soy, indium phosphide, Oclaro, Heilighet, you can also do triplex or whatever. You can immediately simulate, immediately compare. And now based on the amount of data you get for the fab, that's not included here. The noise is just simulated noise, so random phase error. The more data you get back, the more accurate you can also predict this kind of noise values. So as soon as you make more runs on different fabs, you can get actually a very accurate comparison between different technologies here. Without a lot of time, you just say, now do me this fab, do me this fab, do me that fab. So that makes it very fast to design. I can skip this. So just to give an example what it would solve for you, this kind of modules. AWGs have many parameters, like 100 or something. Now you can access all the parameters as a designer, only as a typical AWG, you don't need to change any design. You can just use the default. So the idea is it will hide by default all the complexity, but if you want to dive into it, you can do that. This is an example of the Phoenix software interface running the AWG design tool. So you specify here in some script the free spectral range, etc. You say draw it and simulate it, and you can get all the data back, and you get all the results for the simulation. You can find all the fields here, the fields in the waveguides, powers in the arms, etc. So you don't have to extract all the information yourself. It's already offered after you do the simulation. You get all the kind of feedback to be sure if your design is what you thought it would be, like the index, is it the correct index? You can compare different designs. There's fast analytical simulation tools, and there's BPM. BPM, for example, is very nice because you visually see what happens. So sometimes an analytical tool may give you nice results, but you don't understand them, and a BPM may give you a completely different kind of feedback, and it simulates the real structure. This is an example of, say, an AWG in even more fabs. It will take care of design rules. You can test all kinds of different geometries. This is an example of Leti AWG. This would be, as an example, all the code you need for the layout and the simulation. So these lines are the full program basically for making this AWG, including two simulations, BPM and an analytical. And then you compare those two, and the difference may be physical or grid-related. These examples from real chip processed in Memphis run. Based on this tool. Building blocks here are the photodiode array. So you just generate up, give me 20 ribbon, connect the AWG to my diodes. So then you get this quite fast in the AWGs, as I showed before. Another real life example. This is a very nice wafer from Heinrich Hertz, 3-inch, from the last paradigm run. And here you see this design on the wafer. There's a 100 channel receiver. This has been measured and submitted, so it worked. Actually, the results look exactly as the simulation, but I don't show the results because they have to be published. This is actual measurement of one of the AWGs. So dotted lines, dotted lines are simulation, solid lines are measurement. So very accurate results, and some principle of the device. MMI is the same thing. You may not get the right MMI from the fab, so there's standard MMIs defined in script or in GDS, so you can take the script, just plug and play, or you use the script-based version and you can modify it as you like. And this is then what it looks like. So you basically say, I want a 2x2 MMI according to this theory, and then you get the right estimate already, and you can do the scanning. And the scanning you don't have to set up, you can just say scan between this and this, and it makes it possible to get very fast and completely new MMI. It's still reliable because all the logic has been tested. Almost there. This is an example of a package. This is an Heinrich Hertz chip. This is a package version. This is a wavelength meter, so there's basically simply an MZI. So you get a periodic behavior. And in this case, when the balance on the y-axis changes, this corresponds to a wavelength change, and so you can measure the wavelength. This is based on a similar principle. This was made for a customer, and this one has been shown with attometer resolution. So this is extremely accurate. I think commercially you can get to 1 picometer right now, maybe 0.1 picometer, and this is basically 100 times more accurate. So integrated photonics has, as you all know, very not only potential, it's now really demonstrating that it can do the job, and this is supposed to be a product over the next year. Some other examples of chips we made that have been packaged: bidirectional optical subassembly, laser receiver, a sensor, F5 to the home receiver. We already summary. So, well, I think all you know already what MPWs are, and by now, and yes, they offer you a very good, fast way, including all the tools to get access to your own chips. And right now, projects like Paradigm for many people have been very useful. And after Paradigm, this whole principle will continue. It cannot only be Paradigm, you have of course JePPIX and JePPIX Fab as in the presentation after the lunch. So you have the PDK kits, PDKs from the fabs, but you can do more than that, so you don't have to design everything yourself. If you want to do so, but if you want to be fast and tested logic, there's other options as well. So the conclusion is your pick can be next.
Questions? No questions. Nico.
Could you please explain us better about the principle of relation for the wavelength made out of design?
It's a balance detector on the end. So the MZI gives one port gives a normal signal, the other an inverted, and you use those two. So it's not the response of the one photodetector. This is already the calculated balance between two, P1 minus P2 over P1 plus P2, to compensate for input fluctuations. Yeah.
I have one question by myself. I have seen that you are using for the simulation of the AWG's BPM. Not many people, favor BPM. Is there any limitation that you want to use FTDD compared to BPM for the design of the AWGs, or BPM is enough for all kinds of AWGs?
So typically, I don't use BPM. It's possible to do it. So there's an own model. There's another simulation model. It takes 2 seconds to simulate the whole AWG. But BPM is nice to check your design. Okay. So I would use an analytical solution. You can simulate very fast, but you never know if the model is completely correct. And then you do the BPM to check on your structure. So you may have reflections on your FPR walls, and you don't see that in an analytical simulation, but you do see that in a BPM.
So we are not using any kind of FTDD for your simulations, only your analytical model.
I think FTDD is more for very small.
Yes.
It doesn't add anything to the quality of your, in this case, of your simulation.
Yes.
Can you comment on the IP management between the building blocks from the Eindhoven, the designer, the
Yeah, so at this point, fab building blocks, for example, a laser, as a designer you cannot see what is inside. So you get an outline, you get the connection ports, and when you send it to the fab, they will replace it by the real structure. So you get a description of the block, but you don't see the layout. So they protect their IP in that way. At this point with the project, so this work was still in the Paradigm project or JePPIX projects, for example, or Foxtrot project. That IP is not an issue yet because it's a research project. This year there will be, and for EPIX Fab there are already commercial runs. In that case you sign a DKLA, a Design Kit License Agreement, and basically it's like an NDA. It's clear who owns the IP. For MPW it's a prototype, so that will not be an issue. MPWs also don't make money for the fabs, it's more a marketing tool. So if you really want to have chips, you go back to the fab, and then the IP will become an issue in the sense that they may ask you to pay for their building blocks. So it's people are protected in the software environment because you cannot see inside the building block. So for a fab, it's easy to give you the building block because you cannot delve into it anyway. Well, for example, we use also the Oclaro or Heinrich Hertz platforms, and they use the same building blocks as they use for the commercial products or the spin-offs. So these can be extremely state-of-the-art 80 gigahertz receivers. For the project, again, this is not that much of a problem. If you say now I want to have 100 chips, you have to negotiate with the fab. Or they have to negotiate with their customers or whatever, where the IP issues are, and that will be different for every building block. Or you would have to design a new building block, or take a less good building block which has no IP problems. But this is a very good question, and it has not been, as we said, that has not been generically solved. And the second thing is that there's a lot of IP, and someone has to defend the IP. And I think this is one of the problems, as far as I understood. Opsys stopped last week with providing services. They use IME, so that fab still runs, so you can still get access to the same technology, but not to their PDK. Or maybe they will license the PDK, I don't know. But they always said, or Michael Hochberg always said, and it makes sense, that the fab has to take the ownership of the IP, because they're big and they can defend the IP if someone claims IP. And if all the small users get sued for IP violations, then the whole system will not work. And in electronics, they use, I think they call it an IP umbrella, and then the big fab will basically have the IP. If you sell the IP to them, you license it back to yourself, something like this, and then the IP is safe in that big company. But this, in photonics, this is not solved in this way yet, and it's still very researchy. So that over the next year, this question will come back over and over again, I think. And maybe the presenter from VTT as a fab has another vision, or has a vision from their point of view on their IP. So every fab will be different as well.
Any other questions? Okay, so let's thank Ronald again. So now we can have 20 minutes break, and we can be back at 4:30 for the last session of this summer school. Thank you.
So let us now start the last session of this summer school, which is actually dominated by women. So the first talk will be given by Katarzyna Lawniczuk, who is the coordinator of JePPIX, on indium phosphide-based photonic integrated components and circuits.
Good afternoon, everyone. Thank you for introduction, and also thank you very much for inviting me for the summer school in Thessaloniki. So, with my presentation, I would like to focus on indium phosphide-based photonic integrated components and circuits, and with this, thank you. And in particular, I would like to give you an overview of photonic integrated circuits and how we develop them in a generic fab model. I will show you how we can actually make those photonic ICs, starting from an idea and motivation, and having ready to use photonic integrated circuits. I will show one of the case studies. It will be a multi-wavelength transmitter realized as a photonic integrated circuits. I will also show a few of other examples of photonic ICs made on indium phosphide for many different applications. And as a part of our JePPIX activity, I will introduce you what do we do with JePPIX and how our multi-project wafer runs are organized. So you all know what's inside of photonic integrated circuits already. So these are all the components that you may need for light propagation, light amplification and light generation, as well fast modulation. But what's specific about generic foundry model is that we call those components building blocks, which means that these are standardized and parameterized components. They're also verified by fabs and by the users, which means by using those components, we can win and we can reduce on design time and number of fab cycles needed before this photonic integrated circuits or our application will be brought to the market. So you already know also, you've seen this slide on the previous presentation, what kind of building block we need for fully integrated and fully operational photonic integrated circuits. So these are SOAs, which are basically used as a gain medium or also to form lasers, phase modulators, shallow and deep edge waveguides that will allow for light propagation, as well as polarization elements to maintain and hold the specific polarization of the light. And recently we also introduced another element in our portfolio. These are DBR gratings. So the basic optical building block is of course optical waveguide, which allows for light propagation. You all are very familiar with the operation principle. Then I will just skip this slide. I would just like to show you that this is example of a shallow edged waveguide, which means that the guiding layer is basically placed in this position, and the simulation of mode distribution in such a structure is presented here. And if we compare this kind of optical waveguide with the human hair, then we can see already what kind of dimensions of photonic integrated circuits we are forming on indium phosphide. So how do we fabricate those chips? We basically use butt joint regrowth, which means as a first step of our epitaxial growth, we grow all the layer stack, including the active section, which is here presented as a red stripe. This can be both the bulk material or quantum well active material, depending on the foundry, on the processing steps you choose. The next step is defining passive and active areas, which means we need a mask layout for definition of specific components with our circuits. When we have it done and we have etched a specific area in our wafer, we go to the next step, next epitaxial step, which provides the regrowth of the passive layer stack, as you can see here in the slide. The third step is the regrowth step. So we basically provide the cladding for our structure, and the finished butt join you can see here as a SEM photograph. So this is the active part and the regrowth passive part with the cladding for our structures. This processing might look a bit easy, but if we compare and if we sum all the steps, including the deposition, etching, lithography steps, when we add all the necessity for checking preparation of the structure, we need actually 240 steps to make a full active-passive integration on our TUE platform. But if we have this technology elaborated and operational, we can think of more sophisticated circuits made using from these building blocks. So actually, what can we do from these building blocks? All kind of passive devices. So these passive devices, as you know, they can be done on indium phosphide-based platforms, on silicon, and the triplex. And the triplex here are low-loss dielectric waveguides. And from those passive components, you can actually make plenty of passive devices, including MMI couplers and splitters, as well as MMI-based reflectors, array waveguide gratings, or kind of ring filters, ring structures. If we additionally combine them with polarization handling components, we can think of polarization splitters, combiners, and all kind of differential delay lines, also independent from polarization. If we think about modulating and switching, then the right choice of the platforms will be indium phosphide and silicon. When we can think of phase modulators or kind of amplitude modulators, intensity modulators, we can form space switches or polarization independent switches. If we combine them with the polarization maintaining components, we can also form ultra-fast switches and WDM cross connects or edge drop structures. But if we want to have it integrated with active elements like SOA and to form lasers, for now the only efficient and effective choice is to go for indium phosphide-based technology platforms. And using both passive and active components, we can think of forming Fabry-Perot type of lasers, for example, combining it with MMI reflectors. We can form tunable DBR lasers, multi-wavelength lasers when we have them done with AWGs, picosecond structures with saturable absorbers, or kind of ring type lasers. And these photonic integrated circuits then can be made using single processes. So basically, the versatile designs for versatile applications can be made on a single wafer, and these are the examples of such kind of photonic integrated circuits. The previous presentation already addressed some of those applications, so I would like just to shortly summarize this part of my talk. So these days, to make a photonic integrated circuit on indium phosphide, we combine well-defined, standardized, and parameterized photonic building blocks. we win then on the design time and the number of fab cycles that we need before we bring the prototype into a market, and the fabrication. So we can these days do multiple designs on one process, but we have to keep in mind that this fabrication is not that easy. So how do we get from an idea to a photonic integrated circuits? This is actually a job of JePPIX, which is also a broker. So here we cooperate with the photonic IC design tools and design companies, as well as photonic design houses that provide us with dedicated photonic design kit to have your photonic chips developed and designed. We also collaborate with foundries that provides us with the fabrication facilities, and we also can package those devices, as you will see a few examples later. So having on board photonic IC design companies, and this I mean Aspic Design, Phoenix Software, and Photon Design, with implemented building blocks and building block models, we can do all kind of simulation that is needed prior to having your design developed. And what's interesting for all our foundries, both the indium phosphide and the triplex foundries, we have the design kit implemented in all those three design tools. These design tools will also develop basing on the characterization data provided by the users and provided by the foundries. Together with the software companies, we also offer training for the users so that they can directly go into their circuit development and design after having such a training. If you, in any case, would need a design support, for example, from a design house, we also provide such a possibility, and we have a few design houses on board, experienced designers from Bright Photonics, Effect Photonics, and VLC Photonics. In terms of foundries, how do we actually provide such a fabrication? So this is similar way that it was done in electronics in late 70s. So here you can see a silicon electronic integrated circuits with multiple designs placed on the single wafer. And these days we do exactly the same, but with indium phosphide. And here you can see an example of such a wafer for multi-project fabrication. And this multi-project fabrication, this is example of a Claro wafer that was fabricated in one of the European projects. It's composed on several different designs. Each designer has a dedicated place within this wafer where it actually designs its photonic integrated circuits. Then the whole block with the photonic integrated circuits is repeated along the wafer so that the user can get several copies of the same device for his or her further testing possibilities. And for now, on board we have 3 indium phosphide-based platforms, and this is Fraunhofer, Claro, and Smart Photonics indium phosphide platforms, and Lawniczuk for triplex technology. And at the moment, these 4 technologies are complementary, and as a semi-commercial activity with the Fraunhofer, we offer high speed up to 40G receiver platform. Oclaro and Smart Photonics there offer full transmitter receiver platform for photonic integrated circuits, and Lawniczuk is focusing on high quality passive waveguides. So we have all active and passive components integrated on chip, including lasers, modulators, all kind of passives, DBR grating, photodetectors, and spot size converters. For the packaging, we also have some solutions available for basically for all our users, and these are, for example, solutions provided by CIP, Gucci, and Hausgo, and Linkra, and these 3 are also elaborated within the framework of European projects. Some examples you can see here. This is a data board where the photonic integrated circuits was flip chip bonded to such a data board. We have examples from Linkra package with the RF connections on one side and DC connections to connect with the photonic integrated circuits on the other. And here is a multi-port solution offered by Gucci and Hausgo to package the chips. So as a summary, how actually do we need to develop such a circuit? First of all, we need a motivation. Then we need the design tools, which means a simulation and mask layout design tools to implement our circuits. We need a facility to fabricate those circuits, and this these days can be done by multi-project wafer runs. And we also need the facility to further measure and test our circuits, and this can be done either in the lab at your university or research institute, or by having a chip packaged. So as a case study for such a photonic integrated circuit, I would like to present you a multi-channel transmitter. So where this kind of multi-channel transmitter could be used, it could be used at the central office, for example, in fiber-to-the-home access network that will provide basically downstream and upstream data to the end users. So the requirements for such kind of multi-channel transmitter should be a C-band operation range. It should be compatible with the ITU-T grid. It should generate both continuous wave signals, which will be later used by the user as an upstream data, and as well it should provide downstream modulated signals at the data rate at least 10 gigabits per second. It should be small, scalable. It also should reach at least 20-50 kilometers, thus its output power should be relatively high, and preferable it should operate on a single mode. The conventional approach is just by using a bulky elements like the one presented here. So by combining a stack of them, we can basically form a multi-channel transmitter. But in our case, we prefer the integrated approach, which means we have a compact, highly integrated and multifunctional devices. But you have to keep in mind that we still need to package those devices, so they will not be essentially that small. So how can we make actually such kind of multi-channel transmitter? There are several approaches to make such a device. One of them is to take advantage of AWG laser, which means we will have AWG acting as a wavelength filter to make a multi-channel source, and as a multiplexer to combine all the continuous wave and modulated downstream data. Another approach is to use an array of DBR lasers and the modulators, and then use AWG just as a multiplexer of all the signals. Another more sophisticated idea is to basically combine those two elements and form AWG DBR-based lasers, so where our laser will be formed by two filters, which is the DBR and AWG, and then we can also use another AWG that will act as a multiplexer of all the signals. Just as a showcase, I would like to present you a multi-channel that is based on an array of DBR lasers. So basically we will have a array of lasers that is combined of a rear grating, front grating, phase section, and of course SOA. Then we'll have a modulator to form downstream data, and AWG to couple all the signals into common optical output. So first of all, we may need to choose a parameters and the size of our laser and size of our building blocks. And in terms of DBR laser, these are basically the length of the front and the rear mirror, also the pitch of the grating, which will determine the lasing wavelength, and also the size of those gratings for a purpose, for example, of tunability of those sources. We also need an active region and the phase section, and the phase section is on the purpose of fine-tuning our source to the most appropriate mode of our laser. How can we do it? We can, for example, use a photon design software, which has implemented Foundry building block models. So we have here two gratings, a phase section, and an SOA. And with these tools, we can simulate the whole laser in the time domain. We can choose the parameters that suit your application most. We also can determine the threshold current, efficiency of such a laser, and also output power. And for the purpose of this multi-channel transmitter, we chose the rear grating of 500 micrometers, which provided the full reflectivity 50 microns of the front grating, and SOA of the length of 500 micrometers. And in this case, after the simulation, we obtained the threshold current in the range of 20 milliamps, and side mode suppression ratio significant, it's more than 30 dB. So having all those building blocks parameterized and simulated, we can go into mask layout design, and this mask layout design can be done in Mask Engineer of Phoenix software that also has implemented Photonic design kit and building blocks. So what we usually do with the Phoenix software, we choose the die, which is usually the fab that we want our photonic integrated circuits to be fabricated on, and we choose the package which will provide us with the template that the packaging company is using. And having this and working with the Phoenix, we can design the whole mask layout with the indicated specific building blocks. So going into details, for example, of this photonic integrated circuit, this cell of 6 by 4 millimeters has actually integrated several multi-channel transmitters. This is the 8-channel device. We have here the array of 8 dBr lasers with 4 modulators and AWG that will combine all the signals into common optical output. This is a similar device, but the 4-channel one, and here is just an array of dBr lasers for testing purposes. So if we go into details of this mask, so we see that we used all kind of passive elements, including passive waveguides, both the straight and curved and bends, AWGs, and multimode interface couplers and splitters. For the gain element, we used active elements, but also dBr sections and phase tuning section. And for the modulators, we use electro-optical phase modulators with combination of passive elements, MMIs, to form an intensity modulator. What is also relevant for designing such a circuit is the right choice of the coating of the circuit. And in this case, since we don't want any reflection back and any interruptance in our circuit, we go for anti-reflective coating for our device. So this device, in particular, it was fabricated in one of the multi-project waferun at Oclaro, and it was placed among other circuits on a die at the fab. And here is the photograph of the fabricated chip. For the further testing purposes, we may need to have it packaged or bonded. So not every approach is good enough, as you can see, or easy to work with. For example, this one was quite challenging to reach all the DC pads with the needles and also with the fibers. So another approach that we can do actually is to use other type of assembly. For example, flip chip bonding, when we design a data board for such a device with the dedicated RF tracks to connect to our modulators and DC tracks to basically maintain all the lasers within the structure. And this is an example of such a flip chip bonded circuit on a data board. So this is basically the back of the chip, and the chip during measurements, it still does not have the fiber attached, but this is the next step while having it connected to a motherboard that will have the silica waveguides provided with the optical alignment. So let's go to some measurement result from this chip. So what we first did is all kind of spectral characterization of those transmitters. So both the 4-channel transmitter, which has a channel spacing of 200 gigahertz, so you can see the spectra, part of the spectra here with the output power in the range of 1 milliwatt, and the 8-channel transmitter with 100 gigahertz. And the example is here. The threshold current of these lasers is relatively low, in the range of 18 milliamps, and the output power, it's in some cases it's still more than 1 milliwatt. For the dBr tuning itself, we found out that this kind of lasers on a standard generic platform, they can be tuned up to 9 nanometers by current injection, and this is an example of such a measurement which we provided on a set of DBR gratings and DBR lasers. And with the phase tuning, we are able to fine-tune our laser within 1 nanometer. For the dynamic operation of our transmitter, we made several tests, the transmission and the static tests for the RF performance. And with this, we obtained operation of 12.5 gigabit per second per channel. This is both in back-to-back and after transmission in 20 and 50 kilometers fiber with quite good dynamic extinction ratio, and also the VPI in the range of 3 volt. This structure is 1 millimeter long for the electro-optical phase modulators. So what's the conclusion? That these photonic ICs, they work, and they work pretty okay. And some more examples. So another example that can be used in such a network is an AWG-based laser. So how does this device work? So we have here a right waveguide grating that is integrated with an array of semiconductor optical amplifiers. And this AWG, it acts as an intracavity filter, which means it determines the lasing wavelength of the device, depending which SOA we will activate. So by activating each SOA, we activate the lasing wavelength, and we can simultaneously generate several wavelengths. If we additionally place a booster amplifier in such a structure, we can increase the output power. An example of 8-channel device designed in this way, it's presented here. We designed the circuit for 100 gigahertz channel spacing, and you can see the spectral characteristic of this chip, which is only a few millimeters squared here. The output power per channel was up to 5 dB for this circuit with very high side mode suppression ratio. Another example of a multi-wavelength transmitter, also for access network, is this device. As I mentioned, it uses DBR grating as partially reflective and partially transmitting mirror, and also AWG as an intracavity filter. So here in this laser cavity, we basically have 2 filters that will provide us with a single mode operation. And additionally, having those flexible mirrors here, we can determine how much light will be outcoupled from the laser, and for example, directed into Mach-Zehnder modulator and later to the output of our circuit. And we did some experiments already with this device. It has very good performance, both in terms of the lasing wavelength, single mode operation, but also for the line width of the laser itself, which is in the range of 275 kilohertz. We also performed dynamic measurements of this device. These were made at 10 gigabits per second per channel, so we can easily obtain a error-free operation, both at back-to-back transmission and after long-distance transmission for 50 kilometers. Another example of a laser, this time it's a Fabry-Perot type of structure, very compact laser that can be used for multiple applications as an optical source, also integrated with other components on the photonic integrated circuit. And this laser is actually very simple. It has just a gain section and MMI reflectors, which are made as 2-port MMI reflector, which will provide the reflection of the signal from one input port to the output port, and then, if needed, to the output fiber, or to other part of the circuit on your chip. The performance of the laser, so the threshold current is less than 30 milliamps. It also, this threshold current depends how long gain section you will implement within your circuit. Also, the output power of this kind of structure is satisfactory, and it's in the range of few milliwatts. Another type of laser that was recently developed within our group. It's a ring laser with this 3-stage asymmetric Mach-Zehnder interferometer. And what's very specific or extraordinary about this laser, it's its tuning range, which is in the range of 60 nanometer. This tuning range is done actually thanks to those 3-stage MZI. The circuit itself is not very large. It's just 4 millimeters by half millimeters, but it provides very good spectral characteristic with a very good side mode suppression ratio. This ring structure has a length of this device of 18 millimeters, which corresponds to 5 gigahertz free spectral range. The threshold current of this device is also reasonably low. It's below 50 milliamps. Another photonic integrated circuits, which is high count photonic integrated circuits in terms of number of photodetectors integrated within one chip, because there were 100 photodetectors that integrated here, is presented here. This was done on Fraunhofer Henrik Hertz Institute, and the designer was Bright Photonics. The first initial measurements of this device, they showed that there was no failure in any of those photodetectors. So this device is also a very good example of complex photonic integrated circuits that can be done on a generic platform. Another example for other application is the frequency discriminator that was done using ring-loaded Mach-Zehnder interferometers and photodetectors. The designer of this circuit was VLC Photonics and made on the HHI, also Fraunhofer HHI platform. Another type of structure which might be interesting because it has the widest optical coherent spectrum reported so far is this mode-locked laser. It also was designed for sub-picosecond pulse generation, and this sub-picosecond pulse generation is in the range 900 picosecond with the chirp of 350 gigahertz as far as I remember. And this circuit is composed of semiconductor optical amplifier and saturable absorber. The length of the cavity is just 4 millimeters. Another example, this time the detection example for vapor, water vapor, was done at Fraunhofer Henrik Hertz Institute. The chip itself is quite simple, but it allows for terahertz operation. It's composed of 2 DFB lasers, slightly detuned in terms of the operational wavelength because they differ in 8 nanometers, which means that when we detect it using antenna, phase array antenna, it provides us a terahertz operation. This device is only 5 millimeter long and was also developed on a generic platform. Some more examples, this time from JePPIX technology, which offer very high quality passive waveguides, also thermo-optic phase modulators and spot size converters. So few of examples of those. So here we can make all kind of ring resonators for tunable lasers or programmable splitters, or kind of ring resonators for biochemical sensing, also ultra wideband and low loss delay lines, and all kind of chips for optical beam forming network. And of course many more, because all of those applications and all of those photonic integrated circuits, they are limited only by the designer's imagination, so only limited by you. And so basically you are very free to use those components to make your photonic integrated circuits. So how does it look when we summarize how many chips we designed so far on those generic platforms? It's quite some. We have very high contribution for development of photonic integrated circuits within 2 European projects. It's a JePPIX and Paradigm, and also lot of kinds of R&D prototypes. And since 2014, so since this year, we also offer semi-commercial access to those platforms, so everyone can actually join multi-project wafer run and have its photonic circuit developed. So, as a takeaway, you could see that there are many photonic integrated circuits for many different applications, and they work okay. And you can make them via cost sharing, which means they are low-cost devices that can be fabricated thanks to the open access to fab facilities. So how you can get those access to all of those fabs, so the fab of Henrik Hertz, Oclaro, Smart Photonics, and Lawniczuk, you basically should contact JePPIX, or you can just mail me, and keeping in mind that we can do multi-project wafer runs on all of those fabs, and the prototype in MPW run, which is usually between 5 and 10 chips, which you will get, it's actually not that expensive. So for a small chip, you can expect the price of 5,000 euro for those 5-10 devices, and for a big and complex chips, you may expect up to 35, but this is very high price already. Per millimeter square, it's actually very cheap, between 50 and 100 euro, and the typical chip sizes are in the range of 36 millimeters square, which means per wafer, 3-inch wafer, we can do up to 200 chips for you. And when we compare those prices with the silicon, they are very comparable and competitive, in my opinion, but we offer, as indium phosphide, quite some more functionality in terms of lasers, amplifiers, integrated on chip. So how you get started? You basically, if you want to have fabricated chips with us, you should reserve your spot at the next multi-project wafer run, and here you can see where our next multi-project wafer run are scheduled. If you wish to have more inside knowledge about how to design your chip, you can join JePPIX training on photonic integrated circuits design, or you can have a support from a design house. If you send your design on time, they will be fabricated and sent you back also on time. You're also very welcome to become a JePPIX member. It's for free. You just need to fill in the application form that is available on the JePPIX website and send it back to me at coordinator@JePPIX UE. So for now, we got funding from several projects. That's why we could develop those high quality and mature platforms. And this was mainly Paradigm, which provided generic processes and access to multi-project wafer runs. But now we can also offer for SMEs reduced access to photonic integrated circuits, or provide them with the financial support within the ActFast project that has an open call for SMEs to join the project and have their innovative ideas elaborated. So if you are an SME, or if you know the SME that would like to join this project, then feel welcome and contact either me or representatives of this project. Another opportunity is to join the Line Jumps project. It's also focused on SMEs and have basically photonic integrated circuits elaborated for them. And within this project, you can have business cases or business plans elaborated for SMEs and how they could actually contribute from photonic integration. Another interesting approach which you may forward, it's a new SME instrument in Horizon 2020, when the small and medium-sized enterprises can also contribute from this instrument, financially contribute. There are two phases of those programs. The phase 1 is focused on the feasibility study, and with this amount of money, it's up to 50,000 euros. The company can actually apply for a second phase, where they can have their product also developed, and within phase 2, the SMEs can apply for around 2.5 million euro, even to have their innovative ideas developed. But if you still feel like having your own chip fabricated by yourself and by your process, or just try the fabrication by yourself, then the NanoLab at TUE is one of the places. where you can do your fabrication. Since we have a clean room there, state-of-the-art clean room, which is placed at the TUI campus. It has 800 meters square of equipment for making not only photonic integrated circuits, but all kind of photonic structures and components. And one of the examples of the chip that was made in the nanolab is this 16 by 16 photonic package switch. It combines more than 400 components, including SOAs, MMIs, Peters combiners, and also specific microbands for whispering gallery purposes. This chip size is 14 millimeters by 5 millimeters and was fabricated using 4 edge levels. I will come in a minute what does it mean. So this 16 by 16 photonic package switch, it is composed of several actually blocks. The block of 2 by 2 switch, the 4 by 4 switch element, and 2 by 2 switching element. And here you can see that it combined more than 190 SOAs within the whole 16 by 16 array. So its fabrication was very similar to the one I presented in the beginning of the presentation, but new element was introduced in this processing, which are the ultra-deep edged waveguides as the one presented here, and this is for the purpose of very tight bands that you may wish to have on your photonic integrated circuit, so a more compact device. As a takeaway from the foundry performance, so with indium phosphide you can have basically all components integrated on chip, including lasers and amplifiers. It has high-speed detectors up to 40 gigahertz with very low dark current, less than 100 nanoamps is guaranteed, with high-speed modulators up to 12.5 gigabit per second and relatively low VPI. We now also work on the technology platforms that will provide you with up to 40 gigabit per second modulation on such a generic platform. You have also their tunable structures, like tunable DBR gratings. They can be tuned till 9 nanometers, and also low-loss waveguides. And for example, for the indium phosphide platform, we go below 2 dB per centimeter, and in triplex technology platform, you can even have less than half dB per centimeter. The costs to join such a platform, they are very comparable to the one that you may expect in other platforms, like the Silicon Photonics, but you keep in mind that we have integration with active elements, which might be beneficial for your application. Also, this kind of approach, it provides us with a fabless business model. So basically, the company, SME or design house, does not need any more expensive clean room facilities. It can basically contribute and develop their ideas using existing infrastructure. And also, this kind of approach opens new market directions, new application directions, since you can basically make prototypes for different purpose, just using multi-project wafer runs. As one of my last slides, I would like to acknowledge my few group members that contribute to development of those technology platforms, and also I would like to thank project partners from Paradigm, ActFast, Lightjumps, and also Memphis. And also thank you very much for your attention. And if you're interested in a JePPIX training, we have 2 events ongoing this year. The one is very close. It's in June, 16 to 20. It's in Boston. We offer their photonic IC design training. It's a 5 days, very intensive training, how you can your chips fabricated. And the next one, it's in Eindhoven, in the Netherlands. It's a 2 weeks training, mainly oriented on photonic IC design, but also on very basic performance of photonic components. Thank you.
Any questions?
You mentioned 16 by 16 switch. Is that on one chip or
It's on one chip. It's one chip, yes.
But the typical chip size is on your slide is 36 square millimeters. But that chip seems like 80 millimeters square.
Yes, indeed. As I mentioned, we have also NanoLab at TUE. It has its clean room facilities, and this chip was actually made in the NanoLab as an example that you can also make the chips by yourself with our facility. But if you would need bigger size for your photonic integrated circuits, then you just can contact me and we will see how much space we can allocate for your specific device. But this is an example of PIC that was just done individually. It's also possible if you wish.
But what's the two vertical yellow line on your chips?
Could you repeat?
There's two vertical yellow line.
You mean this one? These are SOA gates. Here. This one.
Yeah.
Maybe some alignment. I'm not sure, but it's for sure one chip.
One chip. Okay.
Yes.
Okay. Thanks.
It's not that it's glued. No.
Okay, first of all, I'd like to thank you, Katarzyna, for accepting this invitation and coming here. I think it's very important having someone speaking about JePPIX and MPW efforts like you and Ronald, especially after all the talks we had during the summer school with fabrication technologies and all different components. I think it's a very nice for a conclusion, as a conclusion talk. So I have a question. If someone participates in one of your academic MPWs, is there a possibility also to do some packaging in that framework or not?
Yes, there is a packaging. For now, we offer packaging of Lincra. It's an Italian company. It provides with the package of the whole photonic integrated circuits, and you can have there 4 RF connections, up to 48 DC connections, and up to 2 optical fibers for alignment. And we can package their chips in the sizes up to 6 by 6 millimeters. This is one of the examples. Another is a Dutch company that we also collaborate with. It's Technobis. It offers also packaging purposes a bit lower count in terms of the number of DC ports. But it's also but it's possible. Yes.
Okay, thank you.
Hi, I have a question about your detector building block. You say it's up to 40 gigahertz. So what kind of possibilities is it with waveguides and stuff into that? Is it single mode or multi-mode? What kind of response do you expect from that?
From the photodetectors itself?
Yeah, what kind of response from I mean sensitivity-wise?
Maybe Ronald, you remember the sensitivity. It's your device.
Is the microphone working? Yes. The fast detectors are not the one I showed, but they have typically less than 5 nanoamps dark current. I think a noise equivalent power of about 150 femtowatts, if that's what you mean with sensitivity.
I mean how much current you get out of from the optical power.
The responsivity.
Yes.
0.8. And for the balanced version, 0.6.
Could you please comment also on the yield of your fabs? I mean, I understand it's depending on the fab each time, but do you have, an estimation or a range where what is the yield?
Yes, we still work with this, and we want to improve, of course, the yield, because we see that sometimes the performance might differ between devices, but it's not that critical, I would say. It's what we usually measure around the wafer. It's within the validation criteria that the foundry provides.
Any numbers?
I don't have number now.
Hi. I especially like the WDM transmitter that you showed there. I have a question. When you're operating all these lasers at the same time, do you see thermal crosstalk, like one laser is changing the wavelength of another one or something like that?
They are relatively spaced among each other because it's more than 300 microns. So for these purposes, we tested it also for the AWG laser and also for the DBR, and we did not observe such a thermal crosstalk. But yes, we do those experiments while cooling the device. So it's on the tech and under tech control.
And are all lasers having the same tech, or is there an individual control for every laser?
They are all placed on one single tech.
Okay, thank you.
I found very interesting the integrated mode logging laser that you did, and I was wondering what's the channel spacing of the pulses?
It was 20 gigahertz.
20 gigahertz. All right. Thank you.
May I also ask, how do you implement the Mach-Zehnder modulators that you have there? You're running them electrically, I suppose?
Yes.
And what's the material structure that you use there?
It's also quaternary indium gallium arsenide phosphide. So these are basically the layer stack of this electro-optical phase modulators is the same as for the passive waveguides with this respect, but also with the contact layer on top, so we could drive them electrically by reverse bias.
And what's the speed that they can reach?
It's 12.5 now, gigabit, yes.
So now the last talk will be given by Sonia Garcia-Blanco from University of Twente, and this will be on integrated optical amplifier technologies.
Thank you very much, Nikos, for the introduction, and thank you also for the organization to invite me to this beautiful summer school. I have really enjoyed all the beautiful presentations, and I have learned a lot, and also have enjoyed very much the beautiful food in this city. So yeah, I think I'm gonna go back with a few more kilograms. But anyway, this is the last presentation of the summer school, so I hope I will not torture you too much. And I would like to keep it interactive, so if you have any question, just please interrupt me and just ask me, so like this we don't fall to sleep, okay? So I'm gonna talk today about integrated optical amplifier technologies and the work we are doing at the University of Twente. I would like to introduce first where the University of Twente is. So you can see here, if I manage to figure, this is Netherlands, and here is where the University of Twente is, in a town called Enschede. And this is the photo of the campus, and here is where our facilities are. You can see that, this is the campus of the university, and it's very nice because around the university there are a lot of spin-off companies. And you can see, for example, around here is where Phoenix Software is, and here in this building there are a lot of spin-off companies. So it's a very innovative environment, so there is a lot of interaction between the university and the companies. And this is our Mesa Plus nanolab. We have a 1,250 square meter facility of clean room that is also an open facility. So anybody that wants to go and fabricate their own devices, you can come. And we are basically focused more on silicon nitride, silicon oxynitride-based technologies and CMOS technology. So we're not doing indium phosphide, that is done in Eindhoven. Here is more like passive devices. Within the Mesa Plus Institute, we are embedded within the Optical Sciences Chair, and this is our group, our people, and the little arrows show our subgroup, which we are the Integrated Optical Systems Group. And two of the members are here in the audience, so I want to acknowledge their work. And what do we do? So we are basically doing research in two main areas. The first one is plasmonic-based integrated optical devices, basically waveguides and nanostructures, like, for example, SER sensors and things like that. And here I show two examples of recent research that we have developed in the last couple of years. The first one is a plasmonic waveguide in which we introduce some amplifier material to try to compensate for the propagation losses. And in the bottom picture is ongoing work in which we introduce thin metal layers underneath the electric waveguides, and with that we managed to reduce very much the losses in sharp bends. So the performance of these bends are better than if you don't have the metal. So that was something very interesting, because normally the performance of the plasmonic waveguides, well, the losses are always worse, but in this case the bend performance is better. So we're trying to figure out what we can do with that. And in the second research line, we are working on active devices and on the integration of these active devices on passive technology platforms. And we are basically working with two passive platforms, a silicon nitride-based platform, and this is the technology that is developed by Lawniczuk under the name of Triplex. And we're also working with silicon on insulators, so we would like to provide gain to these platforms. And in particular, we are working on a rare earth doped-based material, and I will explain later why we're using this material and what advantages can it have for the active devices. But this is basically our concept. We will introduce into a passive photonic motherboard our gain material, and then we can make amplifiers or lasers. Okay, so I'm going now to the outline of this presentation. I will start with a brief motivation why we want to do this. And then I will give a little overview on waveguide amplifiers, what are the main types, and also the integration schemes, how we can bring these amplifiers into different photonic platforms. And then I will focus on what we are currently working on, and is a technology that is very, very freshly being developed now. So I will show the preliminary results, and I will explain what we are doing and how we're doing it. So what I would like that you take from this lecture, these are the learning objectives. So I would like that at least you learn that there are different types of optical amplifiers, waveguide amplifiers, and that they have different characteristics and different advantages and disadvantages. So depending on the application, you may want to use one or another one. There is not, as we have seen through the summer school, there is not an ideal, absolute, perfect platform. I will try to describe what is this gain material, KYW, which sounds quite funny, but it has some advantages. I would like also to give you some idea of what are the different integration schemes that we can use, and how we fabricate high contrast waveguides in this material, because that's something quite novel. And the final point is some methodology to the design of adiabatic couplers, because we have seen very much through the summer school as well that to transfer the light from one waveguide to another one, you need to do some sort of couplers. And it's very difficult to find design rules or even methodology in the literature how to do it. So we have defined some simple steps that I would like to explain here, so that if you want to design one of these devices, it's very simple. You can just do it very fast. So hopefully it works. Okay, so let's start with the motivation. You have seen all these pictures already during the summer school. And basically, we have learned that if we want to overcome the limitations that the electrical interconnection have, we need to move to optical domain. And there is a lot of work in optical PCBs. And here are examples from the connectivity, Fraunhofer, TTM, all the photos that have appeared during the presentations. And we have also learned that as we want to increase the performance, we need to go closer and closer and closer. I don't know where the processor is, but closer to the processor in the PCB. And the latest step, what it will give us the ultimate performance, is if we go on the chip. So that's the closest you can go. And we have seen also a presentation where actually the waveguides were embedded within the transistors. So that is the ultimate closeness. So I put here 2 photos. I thought that was original because I put this one, but somebody already showed it yesterday, so I'm a bit disappointed. But anyway, so as you can see, as you increase the amount of optical components of the chip, at some point you're going to have losses, optical losses. And maybe you want to have a little bit more power for different reasons. Maybe you want to be able to put more functions on the chip, so then if you run out of optical power, then you cannot do anymore. So maybe you want a little optical amplifier that can amplify your signal, that probably at that moment is quite a high-speed signal. So you would like to just pass it through the amplifier, amplify it. Or maybe you want that the chip, the output of the chip has higher power so that you can have longer reach. I don't know, maybe you have other reasons. But maybe there is you need to have an increase in the power. So you need some on-chip gain. And this gain has some requirements. For example, you want it to be high gain per unit length. So that if you have a very high gain per unit length, that means that you can make short devices. Of course, you want to amplify high bit rate signals, so that you don't need to separate your signals into smaller speed signals and then have a lot of amplifiers and then combine them again. You want to do direct amplification. Also, you want the amplifier to have high saturation output power, and of course, low noise figure. So what kind of amplifiers can you choose at the moment? We have seen in the previous presentation already a lot about 3.5 based in indium phosphide. But you can also have erbium doped materials, and probably you're very familiar with that as well. And here is a bit the energy levels and how the 2 different amplifiers work. But as I said before, there is no perfect material. So all have advantages and disadvantages. For example, the semiconductor amplifiers, they are electrically pumped, so that is an advantage. Although that doesn't mean that that is more energy efficient. That has to be calculated because, yeah, optical pumping could be also very efficient. Normally, they have high gain per unit length, and that means that the devices are quite short. But they have a problem with the gain patterning effects, so that limits the speed of the signals that can be amplified. And typically, the semiconductor optical amplifiers were the ones that they were thought that were the useful ones to do on-chip amplification, because especially the high gain per unit length that makes them very small. Because in the case of the erbium-doped waveguide amplifiers, typically the gain per unit length is quite low, and this is especially true when you are doping it into amorphous materials, as I will explain later. And that leads to a typically long devices length. And another disadvantage is the optical pumping, that you need to pump them optically, which if you have some efficient coupling from for example, a diode pump, and the diode pump they are normally quite efficient, then maybe it's not such a disadvantage. But they have the advantage that they have a long excited state that can be milliseconds. So provided that you are working in the small signal regime, then you can have a very stable gain. So you can amplify very high bit rate signals. So that could be a very nice advantage of this kind of amplifiers. And that has been long time being demonstrated and used in the EDFAs. And there has been also quite a lot of work in the erbium-doped waveguide amplifiers. Although, as I said, normally these erbium-doped waveguide amplifiers are the erbium is doped into amorphous hosts, such as, for example, silica, phosphate glass, polymers, aluminum oxide, and these kind of materials. And because they are amorphous, the erbium, if you put too much erbium, it can cluster, so then you have a lot of gain degrading effects. And therefore, you need to limit the amount of dopant that you can put, and the gain is low. But they have some advantages as well, because it's an amorphous material like silicon dioxide phosphate glass. Normally, they are deposited by typical wafer-level deposition techniques, such as co-sputtering or PCVD. And those techniques are typically CMOS compatible, so you can, that's kind of interesting. And you do wafer-level patterning by photolithography, so that is also, you can do a lot of devices at the same time. And this is an advantage because it is amorphous, then the bands are wider, so you have a larger bandwidth. So the gain has a larger band. But disadvantages, as I already, that I didn't say yet, is a small cross-section and limited concentration because this clustering possibility, because it's amorphous material, and that leads to typically long devices. You can also dope the rare earth ions into crystalline hosts. For example, garnets or vanadates, silicates, and in our case, we're working with double tone states. And having a crystalline host has some advantages. Because it's crystalline, you have a larger transition cross-section. That means that you absorb more the pump and you emit more the signal. It has reduced energy transfer up conversion and this kind of gain degrading processes. So that means that you can put higher dopant concentration into the material, and therefore you can achieve higher gain. And this is due to the crystalline structure. The dopants go into the lattice sides, so they are well separated. In the case of the KW is around 0.5 nanometers, so it's a fixed distance. So that means that you don't have clustering, and that is the advantage. And because you can put higher dopant concentration, that means that you have higher gain, and therefore shorter devices. Another advantage of the crystalline material is that they typically have higher refractive index, so you can have more confined structures. And also, they have higher thermal conductivity, and we have seen that having better thermal conductivity is good, especially when we are dealing with high power. Disadvantages is narrower bandwidth, but still is not that narrow. It's like, for example, for ytterbium is like 55, 60 nanometers, and for erbium is a bit wider than that. So it's not as wide as if it is in aluminum oxide or silicate materials, but it's still quite wide. And because it's crystalline material, it's more difficult to integrate. You cannot just deposit it like with PCVD or sputtering, but you need to do some sort of heterogeneous integration. We have been doing in our group a lot of work on erbium-doped aluminum oxide, and this is the work of Sergio Vázquez, who is a PhD student in the group, and he had done this kind of spiral amplifier. Let me remind you, the aluminum oxide is an amorphous material, and therefore the gain per unit length is relatively low. But here you can see that this is the total internal gain in dBs, and this is the propagation length or the length of the amplifier. And you can see that you have an optimum point around 24, 25 centimeters. So he made this spiral, and in this spiral is that length. It's like 40, I think it's 24 centimeter length, and he demonstrated a 20 dB total gain on this device, which is 1 centimeter side. So it's a big device, but it still has quite a large gain. And the limitations, why can this device not be made smaller, is again because of all these quenching centers. So if you want to make it smaller, you need to put more erbium, and then the erbium begins clustering, so then you have quenching of the luminescence, so that's no good. And you also have these energy transfer conversion processes, and also limits the gain. Therefore, the typical length is around 10 centimeters. We are also working, as I said, in crystalline material, and this is what I'm going to be focusing for the rest of the presentation, well, after the integration part. And I just wanted to highlight here what are the advantages of this material. You have a longer site-state lifetime, so you have very stable gain, and you can have high bit rate amplification. Okay, this is not just for the crystalline material, but well, that's an advantage of using rare earth doped KW. Because it's crystalline, you can really dope it with a lot of rare earth ions, so you have higher modal gain. And we have so far demonstrated in ytterbium-doped KYW, ytterbium, the emission is around 1 micrometer wavelength, and we have demonstrated around 1,000 dB per centimeter of modal gain. So that means that you can make quite short amplifiers. And the gain is quite broadband. For the erbium, goes all over the C-band. And in the case, for example, of the ytterbium doped, we have demonstrated a laser that was tunable with decent performance, more than 55 nanometers. You can achieve high laser output power. Like we have done some lasers in this material. And for example, in a laser that we have demonstrated recently in thulium-doped KYW, thulium emits around 2 micrometers. We have demonstrated, I think it was 1.6 watt of output power with 80% or 85% slope efficiency. So that means that is quite interesting. So you can have quite high power out of these devices. And also in the ytterbium doped, we have demonstrated close to 1 watt. High efficiency, as I said, that laser had 80% slope efficiency, and the ytterbium one had 70% or around 70% slope efficiency. And you can achieve also narrow line width. And the material is very stable. It's not reactive to the environment. It's really stable, which is also a difficulty when you want to etch it because it doesn't react to anything. So I will show later how we do the fabrication of the waveguides in this material. I have plotted here a very nice picture of the material, but also has some disadvantages, of course. It's anisotropic. It has 3 optical axes, so you need to deal with the birefringence. And also, because it's crystalline, you need to you cannot just do monolithic integration. You need to do some more complicated integration schemes. Okay. So far, we are advancing through the presentation. So we have learned that there are different types of optical amplifiers that we can use. One is the semiconductor optical amplifiers, which probably are more well known. And the other type is rare earth doped waveguide amplifiers. And probably most of you know the erbium doped waveguide amplifiers based on amorphous materials. And what I have showed you is that the amplifiers in crystalline materials have also very interesting properties, so maybe are worth investigating. And that is the point too. So far we have 2 messages. And let's look now at some integration schemes. So we have some different amplifiers, and we have a passive photonic platform. How can we integrate it? You can have different types of integration. You can have, for example, monolithic integration. And this is quite advantageous because you can do it at the wafer level. So from the economic point of view, it's quite good. It's very manufacturable. So basically, it's based on the direct deposition or growth of the amplifier material on the wafer, like in the same wafer, and using as one of the steps of the fabrication process. And for example, this can be done with the rare earth doped amplifiers on amorphous material. And this is an example of a work in our group in collaboration with the University of Ghent, where we did aluminum, erbium doped aluminum waveguide amplifier coupled to a SOI waveguide. And of course, there is also the monolithic integration that you can achieve with the indium phosphide, where we saw in the previous presentation that you have the active-passive integration. So they have a method that they can have some parts of the chip that are active, and you can have with amplifiers and lasers, and others are passive. But they are also, it's not like so simple either. There is, as we saw before, there are a lot of fabrication steps. You can have hybrid integration, and we have seen that also in the previous presentations. And in this case, we have a finished chip, for example, a laser or an amplifier, and we want to put it in our passive platform. So, for example, we have seen already this picture from CIP, now Huawei. And basically here, there is a silica on silicon board, where we have the silica waveguides, and then there is some silicon and some indium phosphide components that are all finished and bonded into this silica motherboard. That has the advantage that you can test each of the individual components independently, and then just assemble the non-good dies into the motherboard. So that has some advantages. And in this case, they have cavities in the motherboard because they chip the components like that upside down. So in order for them to fit, as I show in the previous here in the next photo, here you can see the cavities. So the little, where is it? Here, this kind of components will go head down here, free chip bonded. So the cavity gives some space for the bigger components. And that is hybrid integration. And then there is something that is a little bit in between, which is the heterogeneous integration. And basically what we do here is you bond the material prior to processing. So you bond it into the wafer that you are processing, you thin it to the correct thickness that you want, and then you can build your devices there. So here is an example of a laser made using this heterogeneous integration. So you have a silicon waveguide here, and you have a aluminum gallium indium arsenide kind of device, or indium phosphide, yeah, I don't know exactly what it is. It's a 3.5 laser on top. So basically, by controlling the width of the silicon waveguide with respect to the 3.5 waveguide, you can send the mode up to the active material and then send it back down. And the process has these steps. You have here the SOI waveguide wafer in this example, and then you have the 3.5 unbonded dies. It's just like piece of material. They don't have lasers or amplifiers or anything yet. You bond them somehow onto the SOI waveguide wafer, and then you thin it, and then you do the processing of your devices. And you can use two main processes to do the bonding. The first one is to do adhesive bonding, and you can use different types of adhesive. And this is in the work of Ghent University. They use BCB, which is a very famous material. So basically what they do is they clean the sample, the passive waveguide platform, and then they coat with the BCB, and then they bond the 3.5 material, and then they do the processing. But you can also do a direct bonding, which is basically bonding without any intermediate material. And this is the technology that has been developed by the University of Santa Barbara, the group of John Bowers. And in that case, what they do is first, they clean the device, and they deposit a layer of silica, and then they planarize it very, 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 very well so that it's atomically flat. I think it has to be less than 1 nanometer flatness. That's not atomic, but it has to be really, really, really flat. And then they put it in contact. Maybe they do some plasma activation depending on the materials, and the two materials bond together very strongly. Then they thin it, and then they do the processing. And with this kind of heterogeneous integration, you can even bond different materials into the same wafer and then processing them all at the same time. For example, here in this example, they have bond different type of 3.5 materials, and they just fix them all together, thin them at the same time, and then they do the final die. Okay, so we have now learned a little bit at the basis of the different integration schemes. And if you have any questions, please feel free to ask. Just interrupt me, okay? Because otherwise we're going to end up all sleeping. Okay, so now I'm going to move to a little bit more our work and what we see. We're thinking, okay, this KW has a lot of advantages, as we saw before, so why don't we try to integrate them on passive technology platforms to develop this technology and have another available building block that can be used for niche applications, or maybe not so niche. Maybe that's going to be the next breakthrough technology, who knows? But anyway, so that is the technology that we are working on at the moment. I have said that we try to fabricate and develop high contrast waveguides in this material. And why is that? So far, the work that we have been done before is in low contrast waveguides. And basically, what we had was an undoped KW substrate, And on top of that, we grow a layer of doped KYW. And it grows because the KYW substrate is crystalline, so you need a lattice-matched process, so it's epitaxial growth of lattice-matched material. So you need to be very careful and make sure you select the correct components so that you don't have cracks in the material. So that limits a little bit the refractive index contrast. So your waveguides are quite big. So this is an example of the mode. You can see this is 2 micrometers. So the waveguides, I think they were like 5 or 6 micrometers wide. And with these low contrast waveguides, we demonstrated this is the modal gain in dBs per centimeter as a function of the launch pump power. And you can see that for 40 or 50 milliwatts of pump power into the device, we demonstrated close to 1,000 dBs per centimeter modal gain. So it's quite high. And in this case, we benefited of being able to dope with very high concentration of ytterbium. That's why the gain is so high. What happens if we manage to fabricate high contrast waveguides? As you know, when you have a high contrast waveguide, you can make a much more confinement of the light, and therefore you have a much more intense field inside the waveguide, and that means that you need less pump to invert the material, so you can make more efficient amplifier. If you have the same material with the same amount of dopants, then you need less pump power to invert it. Or if you have enough pump power, then you can increase the dopant concentration up to the limit where you begin having these problems of nonlinear processes that degrade the gain, but normally that could be quite high. So we could investigate going, for example, in the case of ytterbium, 75% or more, and we will have enough pump power to invert it all. That was what was limiting us in this case. And that means that we, in principle, could have very short amplifiers. So how do you do high contrast waveguides? And this is the work of Mustafa, that you have it sitting here in the audience. So if you have any questions, you can always ask him later. He's the expert on that. And how do you make it? So he has been developing a process to bond the KYW into SiO2. And we decided to develop the bonding onto SiO2 because the platforms that we're going to be working on are based on SiO2, either silicon nitride platform or silicon on insulator. Once it's bonded, the bonding has to be very strong because the next step is thinning, which is done by lapping and polishing, and we thin it to the required thickness. So depending on our design, we thin it to 2 microns, 1 micron thick. And after that, we need to define our channel waveguides. And as I said before, the KYW is very stable material, so it doesn't want to be etched. So we need to use either focused ion beam or ion beam etching, so basically some physical process that kind of removes the material. Okay, so how do we do the bonding? These are the steps. The first thing, of course, you need to clean very well both materials. And the very important thing is to do an oxygen plasma cleaning to activate the surface of both surfaces that you want to put together. Then you spin coat the adhesive material. In our case, we're using a UV curable adhesive, a NOAA-based adhesive, because we don't want to have a high curing temperature, because we were working with BCB and the temperature was producing some cracks due to the CTE mismatch. So we decided, okay, let's go to the safe side, and we use the NOAA, at least for the moment. And so the NOAA is spin coated on the KYW sample, and then flip chip bond onto the KYW using a fine-tech lambda, which has a precision of positioning of 0.5 micrometers. So here is the KYW with the NOAA, and then we flip chip bond it. And when you do that, normally you apply a little bit of pressure, so you have a little bit of glue that comes around. And for the further steps in the integration, we don't want that. So that's why the next step is to strip the adhesive material using oxygen plasma. So the sample becomes like this, very, very clean. And after that, we do the curing of the adhesive with UV exposure. And this is a room temperature, or more or less room temperature process. The next step is the lapping and polishing. So we're using a Logitech PM5 precision lapping and polishing system that you can see here, and we have seen also in one of the presentations. I don't remember if it was the first day or the second day. Here is our bonded, our KYW bonded into the glass, and we apply a little bit of the alcohol wax all around to protect the edges, because the edges are kind of fragile. So if you don't protect them with the shear force in the lapping, you may kind of destroy the edges. So that gives very nice results. And this is a photo of, this is the silica, and this is a thin layer, 2.5 micrometers thick of KYW on top. And it's very interesting that the end facets have been defined by dicing. So after bonding and thinning, we diced with the dicing blade, and you can see the layer survived. So that was kind of like a good milestone, because we were a bit scared about that. So it seems that the bonded thin layer survives the dicing. So that's very important. Here you can see, so this is the as-diced sample, and here is a photo of the end facet. So you can see that this is not very nice, because, yeah, it's just as diced. So what we did is to develop a polishing process of the end facet using the focus ion beam. And after that, you can see that the end facet look very nice and soft. So, yeah, this will be the planar waveguide in KYW, but we wanted to do the channels. So by using FIB as well, we fabricated this waveguide. So I don't know if the contrast is very good. I don't know if you see it very well, but here is the core of the waveguide. This is the 2.5 thick KYW layer, and this is the thickness, and this is the adhesive, and this is the SiO2. Here you can see a bit more from the top. This is the waveguide, and this is also the material that we didn't remove, because the FIB is a slow process, so we want to remove as little material as we need around the waveguide. Here you can see much better the end facet of the waveguide. Here just overview of the different waveguides that we have fabricated, but they are just fabricated last week or the week before, so we are just about to test them, so I cannot give you some results of the performance of the waveguides. And we're gonna test the losses by the Fabry-Perot method, and that's why you can see here that at the end of the waveguides, we did this cavity so that the reflectivity of the front and the back of the waveguide is the same, so that we can analyze easier the results. So hopefully next time we will be able to report some nice losses. And this is the mode profile of this particular waveguide architecture. We have not gone through the whole KYW in this case, and this is the mode profile. And these are the refractive indices at 1.55 micrometers. And we realized the simulations with the Field Designer software. Okay, so now we know how to fabricate high contrast waveguides in KYW. Now we need to integrate them into the passive platform, and how we're going to do that. So this is what we propose in this project. So this is the silicon nitride motherboard, where in this case there is only an input waveguide, because it's for the demonstration. Well, this is also a drawing, but in the chips that we're gonna fabricate, we're just gonna have input waveguides like that. But in the final devices, we will have a lot of passive circuitry all here in the motherboard, and then we will come with our amplifier, which is in this carrier chip, flip chip it, and we will end up with something like that. Okay, so what we propose to do is that we do this heterogeneous fabrication of the amplifier on the silica carrier, like I described before, and then we're going to do some polymer couplers that are going to permit us to very efficiently transfer the light from the silicon nitride waveguide that comes here to the coupler, and then we do back coupling into the amplifier. And we want to do that because we want to have a lot of optical power in the amplifier from the beginning, so that we can invert the material from the start. Because if the material is not fully inverted, then it absorbs. So we want to avoid that. So that was the idea behind this concept. So I'm going to describe now the work of another student, Jinfeng, which is also in the audience, that has been working on the design of these adiabatic couplers. And this is the concept of our couplers. We have the input silicon nitride waveguide here. Here is our coupler region, and here is our amplifier. So the width of the input silicon nitride waveguide is chosen so that it matches as good as possible the mode of the fiber. So we have a very good coupling between the fiber and the silicon nitride chip. And here, in the coupler, probably we need a different width to do an efficient transfer of the light to the polymer waveguide. So therefore, in between the input silicon nitride waveguide and the coupler region, we have this adiabatic taper. Then we introduce the polymer. So here we put the tip of the polymer as thin as narrow as possible. Okay, but we are limited by the we are limited by the technology. So I will show later what it is. And then you start increasing the width of the polymer. And here you go to the maximum width, so that here, as you taper the silicon nitride, all the power is on the polymer. And then maybe the width of the polymer that you end up with is not the one that you want to match the mode of the KYW amplifier, so you need another taper. Okay? So this is just a 3D view of the polymer region. So here is the silicon nitride waveguide, and here is the carrier chip where you have your silica carrier and then the polymer waveguide. And we have omitted the part of the amplifier. We just focus in this drawing on the polymer coupler. And then by flip chip bonding, you put them together. So very precisely, you align them. But as you know, the adiabatic couplers have quite a good tolerance if you have some misalignment in the in-plane direction. So the important thing is that the polymer waveguide and the silicon nitride have to be in very good contact. So you put them in contact, and then in order to make the thing stay there, we put an underfill material to stick them together, basically. Oh, that's the idea. Okay. So as I promised you, we have defined a methodology that permits us to design these adiabatic couplers in a very efficient way. And basically, the methodology has 3 steps. In the first one, we define this interface here that we call O2, because overlap 2, because we had overlap 1 before, but then for the coupler, we only need this one, so I still call it overlap 2. And in this case, you have the start of the polymer taper, and as I said, needs to be as narrow as possible. But we're limited by the technology. So 0.5 micrometers is the smallest we can go, because we are planning in using the nanoscribe 3-dimensional writer machine. And that one can go a little bit better, but just in case we cannot go to the ultimate resolution, we said, okay, 0.5 seems to be a safe parameter for the design. And the thickness of the polymer is 2 micrometers to match the amplifier. So in this cross-section, you have the silicon nitride waveguide coming, and then you introduce the polymer. So you calculate the overlap between the mode of the silicon nitride waveguide and of the complete structure with the silicon nitride waveguide and the polymer. And you want that the overlap is the maximum as you can, so that when you introduce the polymer waveguide, the mode is not disturbed. Okay, so in this cross-section, you maximize the overlap with the silicon nitride waveguide. And to do that, you vary the width of the silicon nitride, and you will find what is the width of the silicon nitride that gives you the best overlap. Then you go to the end of the coupler, and in this case, you can vary the width of the polymer waveguide. And what you want here is that the overlap with the polymer waveguide is maximum. So the overlap between the mode of the coupler, which consists of the polymer waveguide and the thin, the narrow silicon nitride waveguide, and the mode of just the polymer waveguide is maximum, so that most of the power is into the polymer. So that means that you have an efficient transfer to the polymer waveguide. And for that, you can vary the width of the polymer. So once you have maximized this overlap 2 and overlap 3, that means that you have the width of the silicon nitride waveguide at the beginning, and you have the width of the polymer waveguide at the end. And the multiplication of these two overlaps will give you the transmission of the coupler. But that assumes that the angles are so slow that they are adiabatic. So then we need to find out what are the angles that are adiabatic. So for that, we do a 3D BPM. For a range of angles with these parameters, and we find the adiabatic condition. And normally when you have the adiabatic angle, it's a very small angle, so your coupler is quite long. So then we try to optimize the design so we can make the coupler a little bit shorter. And for that, we have also defined some methodology that we are hopefully testing in the next month or so. But simulation-wise, it works. Okay. So, as I said, in the overlap 2, we want to maximize the overlap between the input silicon nitride waveguide, which it looks like that. So this is the silicon dioxide, and there is a thin layer. I don't know if you see here because it's very thin. It's around 70 nanometers thick of silicon nitride. Then there is the underfill material that we are putting to keep everything together. And here is the silicon dioxide of the carrier, okay? And here is the introduction of the polymer tip, which has the polymer that the width is 0.5 micrometers. Here is still the silicon nitride waveguide, and the rest is the same. So we want to maximize the overlap between the modes of these two structures. And at the output here, we want to maximize the overlap between here you have the polymer and the silicon nitride is very narrow here, is 0.8 because that is the minimum that we can do with the optical lithography. And here is just the polymer waveguide after the silicon nitride stops here. And we want to maximize also this overlap. We need to decide what thickness of silicon nitride we want to use. And as I said, because the silicon nitride is going to be the same thickness in the whole waveguide, you need to consider also that for the coupling to the fiber, the optimal thickness of the silicon nitride is 65 nanometers. So we cannot go too thick because otherwise then we will lose all the light trying to couple into the chip. And here in these graphs, you see for the overlap 2, this is the value of the overlap 2 as a function of the thickness of the silicon nitride in this axis, and in this axis is the width of the silicon nitride. And this is for 980, which is the pump wavelength, and this is for 1550, which is the signal wavelength. So what do we see here? We see that for this overlap, ideally, you will want to have a very thick silicon nitride. And why is that? Because you want to optimize the overlap with the mode in the silicon nitride. So the thicker the silicon nitride is, the more the mode is going to be confined in the silicon nitride. Okay? But that's not good with this. And also, we can see that we want to go to wide silicon nitride waveguides. And in this case, it's okay. So, but then we need to look at the other overlap. And in this case, the trend is the opposite, because now you want that the mode overlap with the polymer is bigger. So if you have a very thick silicon nitride, the mode is going to want to stay in the silicon nitride. So if you make it too thick, then it's bad. So you need to find a compromise. So considering all these parameters, the fiber waveguide coupling, that here you want to be thick and that here you want to be thin, we decided that 70 nanometers will be kind of the ideal compromise. So then we plot these values of overlap so that we can choose what are the widths of the silicon nitride in this side and the polymer in this side that will maximize the overlaps. So these are the graphs that show that. So we have here the silicon nitride width as and here is the overlap 2 and the overlap 3. So we can see that the green dots is for the pump, the blue dots are for the signal, and we want to maximize the overlap. So we go, for example, here is like a good compromise. We don't want to go too wide, because if you go too wide as well, that means that remember the input taper that transfer the width from the one that is good for coupling to the fiber to the one that we select here, that will make the device much longer. And if you see in this axis, varying from here to here, it only varies from 0.95 to 0.97, no, 0.965 to 0.97, so you don't gain so much. So we choose this value around 2 micrometer. And in this case, we go here, it's quite optimal. And in this case, you can see that we really need to go for the maximum because the variation is quite much larger. It's from 0.75 to 0.85. And as I said, if you multiply the O2 by the O3, you kind of get the theoretical losses that you will have in the coupler. So I have multiplied this value by this value and this value by this value, and you get that you're expecting some losses at 980 for the pump of 0.6 dBs for the coupler, and for the signal, 0.2 dBs. So we're quite happy with the performance. Of course, we need to verify it experimentally. But this is, of course, assuming that there is no losses due to the tapers, like that is in the adiabatic condition. And here I just want to show the modes of the pump and the signal at the different interfaces. So once we have selected the width of the silicon nitride and of the width of the polymer, now we can simulate that preliminarily optimized structure in 3D BPM, because 3D BPM is quite costly, like resource costly, so it takes quite a long time to do the simulation. So you don't want to do all the optimization in 3D BPM. So now we just need to do 3D BPM with these parameters for several angles to find what is the angle that gives us the adiabatic condition. And this is plotted in this graph. You can see the loss of the coupler in dBs as a function of the taper angle. So you can see that this is for the pump and for the signal. So around below 0.5 degrees, you are reaching the adiabatic condition. And if you remember from the previous slide, the losses that we calculate with the 3D BPM in the adiabatic conditions are quite similar to the ones that we calculate just with the with the mode solver calculation. So that makes us quite confident in the results. And the difference probably is due just to the grid that we can use in the 3D BPM to manage the simulation time. Okay, so now we have selected the adiabatic condition that we know the angle for the tapers. And now we have a certain linear taper. So we thought, okay, let's try to optimize the length of this taper a little bit to make the couplers a little bit shorter. So I'm going to describe how we did that. So basically, the first thing that we did was to divide the taper, the linear taper, into n slices. You can have 20, 30 slices. For each slide, I'm going to put everything. For each slide, we calculate the mode overlap between the coupler mode of the slide I and the one slide and the next one, basically. So you calculate the mode of the coupler here and the mode of the coupler here. And you calculate the overlap between the two modes. And basically that gives you the losses of the mode when it passes from this cross-section to this cross-section. And then we say, okay, we want to keep the losses below a certain value. We said, okay, we want to keep the propagation losses below 0.1 dBs per centimeter. So with that, you can calculate what will be the angle in each section that will permit you to keep the losses below 0.1 dBs per centimeter in our case. And from that, you have the angles, you have the widths, and you have the length of the different sections, and you can plot the normalized taper angle, which is, where is it here? The angle divided by the maximum angle versus the normalized width. And with that, you can see that you have a certain profile. That means that at the beginning, you need to have the angles quite slow as a function of the taper, and then towards the end of the taper, you can go faster. And this is what the result is. If you do the calculations, you have the linear taper that will be 170 microns, like that. You start from the beginning till the end. Those are the width at the beginning and the one that we calculated at the end. And the optimized taper has this profile. First varies slowly and then goes faster. And you can reduce, by using this method, the length to 36% smaller length. So that saves quite, especially if you have a lot of these devices, could save quite a lot of space in the chip. Okay, so this concludes the final thing, the final subject that I wanted to deal with, that is the methodology for the design of the adiabatic couplers. So we have learned different types of amplifiers, waveguide amplifiers, the advantages of each type of waveguide amplifier, and why we think that investigating or developing the technology for erbium-doped KYW amplifiers could be advantageous or could have some niche applications. Then we learn how to fabricate high-contrast waveguides in these new materials, and how we propose the integration scheme as well as the design of these adiabatic couplers to integrate them into passive technology platforms. And we are considering the silicon nitride platform as well as the silicon-on insulator. And thank you for your attention.
And so I've seen that you have this gain section, and the waveguide looks sub-micron in width. Kind of, I didn't really understand from the scale in the picture, but it looked like below 1 micron in width. The mode, I mean. Isn't it?
Yes.
Okay. So, but when you mentioned that you are planning to do some flip chip bonding, and with an accuracy which is half a micron. So how do you plan to solve this accuracy issue?
Because when you are, you see the amplifiers in the middle, and then you have the couplers. So even if the amplifier could be as small as that, like it was actually like 100 nanometers, I think, the couplers are going to be bigger to transfer the light from the silicon nitride.
There is some polymer on top, because it was not very clear where is the polymer compared to this waveguide. So
So the polymer is in both sides.
Okay.
And also I didn't show, but you can have like more than 1 micron misalignment and still have good performance of the coupler.
So when you bond these gain sections to your substrate, to bond it with some BCB or something, I'm just wondering that thickness. How is the uniformity of that over the bonding over the whole die?
You mean the uniformity? Okay, we spin the adhesive, and you mean when you bond it, how is the uniformity? We had not fully characterized that because we just bonded a few chips, and in the ones that we have, I think across the chip there was, I think, 1 micron difference, or 1 micron and a bit difference across 1 centimeter. So I think we need to improve that, but we had not had yet the time to improve it. So every time we do a new assembly, we try to improve the things, but it's still not perfect.
So what can you do to improve it?
We were thinking in trying to find some stops, because the way I don't know if you're familiar with the Fintech lambda flip chip bonder, the way it works is like you go down and there is no stop. So the adhesive is not hard, so it could kind of dip a little bit, so you could have a little angle. So what you could do is to have a gimbal tool and have some stops outside, of course, the good area that you want to bond, so that if those stops are very well controlled, then you just apply some force and you will get very perfect planarity. And this is equivalent to when you bond chips, you can put these little glass beads, so the kind of same idea, and that gives you planarity that is basically 100% planarity. But you cannot put glass bead because the adhesive is going to be in the optical path, so you need to do some defined glass beads.
for the adiabatic coupler in the polymer part, which fabrication process you use?
We are planning in using nanoscribe, which is a 3D writing system from nanoscribe, but you could also use lithography. But yes, we think because we're having the amplifier, and we were not sure at the beginning if we're going to have to do some sort of the photonic wire bond. We thought, okay, maybe we should try it with the nanoscribe, and then we can for sure connect it. But of course, it will be easier if we could do it with lithography. But we're trying first with nanoscribe. But we have not started yet. That will start when we come back.
I have 2 questions about your comment on high power laser that you can build. What is, or is there actually also wavelengths at 1550 available with like 1 watt output power?
No. The 1.6 watt was doped with thulium, so the wavelength of emission is 2 micrometer. And the one that we demonstrated at 1 micrometer had almost 1 watt and was limited by we were pumping with a tie sapphire, and we didn't have optimized the coupling, so we were limited with the power that we could pump it. But we never have developed yet waveguide lasers in erbium doped KW. So that's why I don't have any data of what is possible with the erbium. So we have done the work with the ytterbium, because we decided to work with ytterbium to get a very high gain. And we work with the thulium because in a project we wanted to work in trace gas analysis. That's why we were working in thulium. And now, only now we're starting to work in the erbium doped. So hopefully soon we're going to have some results.
Okay, and second question would be, what would be the footprint of such a high power laser?
Let me think if I remember. For the I don't remember. The thulium was, for sure, it's less than 1 centimeter long because the samples are smaller than 1 centimeter. I don't remember if it was 6 millimeters, but no, I don't. You can check our papers. It's from this year. Post deadline in Clio last year, I think was. We're just submitting it to optics letters. But
the active region we are talking about, how big? Like the gain region that is between the tapers? How big is that region? Because is it in the on scale in the images?
No.
Okay.
It's not in a scale. The tapers are the length you saw at the end, like 100 or 200 micrometers, and the amplifier could be up to 1 centimeter.
Okay.
So the amplifier is longer.
Okay.
So this has been now actually the closing of this summer school. I really hope you enjoyed all these days here in Thessaloniki, as well as the talks and the presentations that were made. So I would like to thank once again all the speakers that came here. We have thanked them several times so far. I would also like to thank here all the members of our group here in Thessaloniki, and especially Stella for contributing so actively in the successful organization of this event. But I think that this is it. Yeah, but I think that now it's the time also to have to thank all of you actually for being here. So actually, thank you very much for supporting this event. I hope to repeat it soon in the future. So thank you very, very much.